Is now starting. All attendees are in listen-only mode.
Hi, everybody. Wanted to welcome everyone as people are filing in virtually here to our 21st NROW. It's a little different than we've had in the previous years, but we are really excited for a really good 2 days here that we got lined up. This is Brian Frugis. I'm the NROW committee chair here at National Weather Service Albany, and yeah, we're going to be getting into it. I'm going to first introduce our MIC, Ray O'Keefe. He's going to have a few words, and then after Ray's done, I'm going to go over a little bit of our webinar logistics and some of our, how we're thinking of how we're going to do this thing, even though it's a lot different than what we're used to. So I'm going to toss it over to Ray and let him welcome everyone to our 21st NROW.
Thank you, Brian. Just want to check. Can you hear me?
Yes, you sound great, Ray.
Okay, good. Yeah. So yes, so welcome everyone. It's been a challenging world for the last 8 months here in COVID, and it's changed many things. It's changed NROW in one way. This is a virtual NROW. It's not our first virtual NROW, I believe. It was Sandy perhaps resulted in a virtual NROW. But in any case, one thing it hasn't changed is the quality of the presentations. I was looking over the agenda, and it's a really diverse agenda, has a lot of excellent presentations lined up. So I don't want to take much more time before we jump into the presentations, but I did want to, right here at the outset, take a moment and thank the WFO Albany, National Weather Service Albany team for putting together this unique NROW. So first, Brian Frugis, thanks to him. He's the steering committee chair, and on the team with him is Steve DiRienzo, Mike Evans, Basile Kalecki, Christina Speciale, Neil Stewart, Dan Thompson, Joe Villani, Tom Wasuler, and Ingrid Amberger. So my thanks to everyone here at National Weather Service Albany, and I look forward to an outstanding NROW 21. So with that, Brian, I'll turn it back to you.
Okay, thanks, Ray. We're going to be starting off here at 9 o'clock, and we're going to have each speaker is going to have 20 minutes in total for their talks, including questions. So for the speakers, we probably aim to have you talk for about 16, 17 minutes to leave a good 3 or 4 minutes for questions. All attendees are going to be on mute, but if you do have a question, there is the raise the hand option there. It should be on your little control panel. You'll see a hand with a green icon. If you click that, it'll notify that you have your hand raised. And so when it's question time, we'll unmute you and you'll be able to ask your question. As an alternate, there's also the chat option. You can always write a question or a comment on there, and either me or one of our session chairs that'll be joining us through the 2 days can relay that and bring that up. So we definitely, even though this is a not in-person conference, we're still really wanting to have that type of collaboration and going back and forth, and the communication that we've always enjoyed from NROW in the past. So we're still trying to definitely have that. So feel free to please try to get your questions in, and we'll definitely go with those. We do want to try to stick to the time as best we can, though, since a lot of people here are either working shifts or have other commitments. So we're trying to stick to the times on the agenda as close as possible. We do have a little flexibility around some of the breaks and lunches if necessary, but we really do want to try to stick to our times as best we can. If anybody has any technical problems, you can feel free to either use the chat, or if you're having other problems, you can send an email. I think we have the email on the NROW page. You can send us an email, and anybody here on the steering committee can try to get back to you. So we're hoping no technical issues. We know sometimes with these virtual things, people get confused with the mutes and unmutes, and we're hoping here with the way the GoToWebinar, it's really a great system. It'll try to alleviate some of the issues that sometimes people have had with those type of things. So we're really definitely thinking that things should work out pretty good for us here today. So I know it's a few minutes early, but I think I'd like to get started. So let me unmute Jay, because I know Jay's our first speaker, and it's going to be a really great start here with our session A, our hydrology section. So I'm going to be our session chair for this first session, and then we have some of the other steering committee members chairing the sessions for later in the day. So let me just get Jay unmuted here, and then we're going to send it over to him. So Jay, are you there?
Can you hear me?
Yes, we definitely can. All right, so I'm going to give you
Excellent.
control if you're ready.
All right. Share screen.
There we go.
Just trying to figure out how to share my screen. Sorry.
That's okay. You should have a box pop up. All right. So yeah, whenever you're ready.
Okay. Just for other people, you may have some security issues before being able to share your screen. So you might want to test that out before it's your turn. All right. So thank you for scheduling me first. It's a pleasure to present once again at NROW. I think it's been maybe 5 or 6 years since I've presented. Today, I'd like to talk about ice jams on the Pemigewasset River here in central New Hampshire. It's a pretty common occurrence here on the Pemigewasset River. What you're looking at on the title slide here is the Pemigewasset River Center looking south. And you can see it's full of ice. And the upstream area here, this is a golf course, is flooding. And this occurred in 2017. It was actually one of 3 ice jam floods that we had in 3 consecutive years.
Hey Jay, I'm sorry to interrupt you.
Yeah.
Do you have like a dual monitor setup? Because we're only seeing like a white screen here.
You're seeing it now? Yes.
Let me see. There we go.
All right, I killed the dual monitor. Is this working?
Let me see here.
We're still a couple of minutes before 9. Figure out the case.
Yes. Okay. Yes, it looks great.
Okay. I maybe I had it in presenting mode. Maybe I'll just keep it here in window mode.
Okay.
I don't have any animations or anything like that. So let's see. All right. So those of you who couldn't see, this is the title image that I was talking about. It shows the Pemigewasset River looking south. It is full of ice here in February of 2017. The ice jam head is not pictured, but it's about a mile downstream or further south. And the upstream locations in the golf course are flooding. And behind us in the picture would be Plymouth State University on campus in Plymouth, New Hampshire, and also Holderness, which also experienced flooding during this event. Right, so ice jams and associated flooding have occurred with some regularity, as I mentioned, in 2017, 18, and 19. The 2017 ice jam and associated flooding did cause some damage to student parking on campus and also closed a number of roads locally. And you can see that the ice jam in 2019, this is the same parking lot photographed. It also flooded. However, we did not lose any student vehicles. And there were some changes in the way in which the university operated following the 2017 flood that may have mitigated damage in 2019. The flood in 2019 was actually interesting because the floodwaters actually froze in place, and that water is that ice is 1 to 2 feet thick. And in order to open up that parking lot in February, they did have to go in with front end loaders and break up a lot of that ice. So this motivated some research at Plymouth State University through the Center for the Environment, and it was, what are the hydrometeorological characteristics of ice jams and their flooding that may provide situational awareness for future events? Pretty broad, overarching question. So the presentation today is based on one of my master's students, Matt Sanders, who did a thesis in 2019, and we went on to publish that thesis in the Journal of Hydromet, and it appears online in their early online release today. So a little bit of background, ice jam flooding is responsible for the highest natural hazard risk alongside severe winter weather to the region. That's from our hazard mitigation plan locally. Ice jams occur on the river during mostly breakup of riverine ice in the spring, but also during periods of thaw throughout the winter. Very rarely does the river remain frozen throughout the entire winter. It usually, and anecdotally, 3 or 4 times will it melt and refreeze. The ice flows of broken river ice can become lodged due to channel characteristics downstream. Here, as you get closer to the town of Ashland, New Hampshire, farther south along the river, there are steep slope banks. The river narrows, there's a sharp bend, and there's a pair of railroad and road bridges, and that's usually where the ice accumulates, and then the flood backs up upstream. It's almost a tidal flood as it reverses and heads north. The ice jam head in 2017 was, again, located in Ashland, and it produced flooding in Holderness and Plymouth. And the image at right is actually some drone footage overlaid on Google Maps from the USGS showing that the ice jam and related flooding was 4 miles in length. Ice jams are really common in river reaches in the Northern Hemisphere. Some previous work has identified that 60% of rivers in the Northern Hemisphere may be susceptible to ice jams. And there are a lot of known cases throughout Canada and also the Northeast US as being an ice jam susceptible region. North America is the highest. And in the US, there's about $300 million annually in damages attributed to ice jams and related impacts from flooding. The Army Corps of Engineers in their Cold Regions Lab in Hanover, New Hampshire, does maintain a database of known ice jams dating back to the late 1700s. So not all ice jams, but at least known ice jams. There have been over 4,000 of them in New England plus New York since that time period. And in a more modern period from 1981 to present, there's been almost 2,000 ice jams recorded in the database. We focus on the Pemigewasset River at Plymouth, New Hampshire, which is located in the center of this domain region that we considered, where there's been 20 ice jams on the Pemigewasset River since 1981. So for our study in Matt's thesis and our paper, we looked at 2 case studies from 2017 and 2018 and really overviewed all of the pertinent ingredients to those ice jams. And then we took all 20 events that have occurred since 1981 and we made some composite analyses. And today I'd like to just present those 20 member composites with comments on individual events. Our data consisted of diverse observations across the region, and those were complemented by the NCEP CFS reanalysis and operational analysis datasets. The image on the left here highlights some of the observations, including ASOS sites in Plymouth, New Hampshire, Laconia, and Concord. Laconia and Concord and Plymouth are considered valley locations, and Laconia and Concord were necessary to capture observations going back into the 1980s and 1990s, since the AWAS in Plymouth, New Hampshire was only installed in 2005. We have river gauges located just upstream on the Baker River in Rumney, on the Pemigewasset River in Woodstock, and also here in Plymouth. We have instrumentation in the Hubbard Brook Experimental Forest, namely a snow pillow site, which gives us information on snow water equivalent. We use the grid point here centered over the southern White Mountains at 44 north, 71.5 west from the CFS for time series of atmospheric data. There is a co-op site in Pinkham Notch, which has daily temperature information, dew point information, and snow going back to the 1930s, which was useful in this study. And Mount Washington, of course, has daily records of lots of meteorological parameters up at between 800 and 830 millibars, or 6,200 feet. So the observations are diverse in elevation. Mount Washington is our highest site. Pinkham Notch is located at about 2,000 feet of elevation, and our valley locations are around 500 feet above sea level. And in our composites, we use, in order to reduce smearing of composites in time, we use a time of maximum IVT, or integrated vapor transport magnitude, in order to lock all the composites together. So that's anchoring our composites on a synoptic parameter, which hopefully gives us a little bit more insight into some of the magnitudes of previous events. And the reason why we chose IVT is because we found a linkage to atmospheric rivers, and IVT is a common ingredient in identifying ARs. So for 2017 and 2018, some of the common features, both of them featured robust synoptic scale flow patterns with enhanced moisture transport characteristic of ARs. These produced an environment conducive to rain on snow, snowpack ablation, and rapid increases in stream flow. Even though the synoptic patterns were similar, there were differences in the antecedent conditions leading up to the ice jam. In 2017, we found that there was a long melting period with several days of temperature and dew point temperatures between 5 and 20 degrees Celsius, right, in February. But there was a relatively low precipitation event that culminated with the ice jam, only 10 to 15 millimeters across the region. However, 2018 had a much shorter melting period where those aforementioned temperatures above freezing only lasted for about a day, but there was high precipitation of about 50 millimeters, and we saw lots of snowmelt during that period as well. So we hypothesized early on in our study that ice jam events would share similar synoptic characteristics, but feature some combination of antecedent conditions that culminated with the ice jam. So we start our composite analysis here at Pinkham Notch, at 2,000 feet ASL. We're looking at a long period from 4 weeks before the day of the ice jam to 7 days after the ice jam to sort of diagnose the large scale antecedent conditions. In the top chart, the blue line is the snow depth in Pinkham Notch. The red line is the daily temperature, and the dashed red line is the climatological mean temperature. The blue, red, and yellow dots represent statistical significance of the daily temperatures with respect to climatology. The gray shading here between days -10 and day -12 represents a period of relatively cold temperatures where we saw an increase in snow depth prior to the ice jam. In the week leading up to the ice jam, we see a regime transition that produces a transition from cold temperatures to much above average warm temperatures. And coinciding with the peak in warming temperatures at Pinkham Notch, we see approximately 50% decrease in the snow depth at Pinkham Notch, suggesting that we have snowmelt occurring, or at least an increase in the density of the snowpack, presumably ripening and then melting out. If we look at the bottom panel, we see daily snow accumulation in gray and the equivalent liquid equivalent precipitation in blue. And what we notice is that all of the blue bars are complemented by gray bars in the 4 weeks leading up to the ice jam. That means that most of the precipitation was in form of snow. But if we look at day 0, the day of the ice jam, there is a lot of liquid equivalent relative to snow, suggesting that we saw mostly rain at this mid-mountain level elevation. So there's our suggestion that rain on snow is leading to at least some snowpack ablation, which is going to increase stream flow downstream. Our second composite analysis evaluates a more synoptic period from T-5 days to T+2 days surrounding the ice jam. The top chart, the black line, is the valley location temperature, and the dashed gray line is the valley location dew point temperature. The solid red line is Mount Washington's temperature, and the dashed pink line is Mount Washington's dew point temperature. The key here is in this gray and pink shaded region, where we see valley locations feature above freezing temperature and dew point temperatures for approximately 46 hours, or the dew point temperature above freezing for about 20 hours. And Mount Washington had a similar increase above freezing in both T and TD for 13 and 8 hours. This suggests that the environment is not only conducive to a ripening of the snowpack, but we also see the potential for condensation flux, or basically fog eating snow and directly depositing liquid into the snowpack. If we look at the middle panel, this is a box and whisker analysis of the integrated vapor transport magnitude from the CFS, and it shows an increase in the water vapor flux magnitudes over central New Hampshire to an IVT value on average, excuse me, greater than 600 kilograms per meter per second, with some maximum values over 1,000. These are representative of environments that could be atmospheric rivers. And coincident with the atmospheric river conditions, we see an increase in the precipitation rate from the CFS. And observations from these events suggest that the CFS precipitation rate is fairly accurate. Finally, we look at maps of the synoptic maps at the time of maximum IVT for each event. The upper left is the 300 millibar analysis and ice attacks. Panel B is the 500 millibar heights and absolute vorticity. Panel C is the 850 analysis with temperature and winds. And the lower right panel is mean sea level pressure, integrated water vapor, and IVT vectors. The location of New Hampshire is in an optimal location for dual jet street configuration forcing for ascent at 300 millibars. We see a negatively tilted trough and inferred cyclonic vorticity advection at 500 millibars. We have decent warm air advection with 850 millibar temperatures between 3 and 6 Celsius. And we see a poleward extension of integrated water vapor and high IVT values in the warm sector of a cyclone over the Adirondacks. This is characteristic of an atmospheric river over New England. We wanted to explore some of the case-to-case variability, specifically with respect to atmospheric rivers. This is a thumbnail plot of all 20 cases at the time of maximum IVT magnitude, showing IVT magnitude in vectors. The magnitude is shaded in the colors, and anywhere orange or red is greater than 1,000. 19 of the 20 events visually identify as atmospheric rivers with minimum IVT magnitude and spatial characteristic requirements. The one event not meeting the definition of an AR is in late March 1993. But it did feature the largest antecedent snowpack by greater than 40% of all events studied. And that makes me wonder, does anyone recall anything big happening in early March 1993 that could have led to such a large snowpack? Interestingly, some ARs contain positive tilts with southwesterly flow and some contain negatively tilts with southeasterly flow. This could influence low-level water vapor flux direction and orographic precipitation in the White Mountains, which are largely oriented southwest to northeast. So if we take a look at some of the precipitation characteristics, this is 48-hour precipitation on the day of the ice jam and surrounding. Precipitation is shaded here in millimeters across New England. Generally 25 millimeters of precipitation across much of the valleys, with as much as 50 millimeters of precipitation across the White Mountains in our study domain. If we average the precipitation within 100-meter bins of elevation using a DEM, we come up with the orographic gradient. And the orographic gradient is about 22 millimeters per kilometer, and recognize that Mount Washington is about 2 kilometers high. That orographic gradient is pretty consistent across most events, but this also highlights that some events here in March 1990, February 2017, and December of 1991 featured very little, if at all, any precipitation. And so what gives? In February 2017 and March 1990, we saw that there were extended snowmelt periods of almost 4 days with temperature and dew point temperatures greater than 0 degrees Celsius. And there were very long durations of AR conditions, which may have helped release more water from the snowpack, making up for the lack of precipitation. And in December 1991, there was only about 24 hours of temperature and dew point temperatures greater than 0 degrees Celsius, but it was preceded just 3 days earlier by an atmospheric river and precipitation event. So I had Matt come up with a schematic of the ingredients for ice jams from the hydrometeorological perspective. That's shown here at the right. Our observations suggest that there is antecedent snowfall often in the weeks leading up to an ice jam. However, it should be noted that snowfall is not a requirement for an ice jam to occur. Temperature and dew point temperatures are commonly exceed the freezing point, allowing for that condensation flux, which I mentioned. For the 1 to 2 day period before the ice jam, there's usually orographic enhanced precipitation of 1 to 2 inches across the state, and we do observe on average a 50% decrease in the snowpack. The synoptic scale environment is characterized by strong synoptic scale forcing. There is orographic forcing with an AR that contains variable direction IVT, mainly out of the south. 95% were ARs, and we found that the marginal events feature some compensatory antecedent conditions, like the big snowfall event from the superstorm of '93, or a previous precipitation event a few days earlier. And so finally, this is our summary. Characteristics of ice jams and flooding in central New Hampshire. The ice is a requirement for an ice jam, yes, and snow to lose, although that's not necessary. We do find all events feature amplified synoptic scale patterns, anomalous warp, robust QG forcing percent, and abundant moisture. ARs summarize the necessary but sometimes insufficient environment for these. Valley and mountain temperatures do increase to above freezing, allowing for rain on snow and condensation flux, which can lead to ripening, melting, and decreases in the snowpack. We do find orographic enhanced precipitation plays a role, and low precipitation in non-AR events featured compensatory antecedent conditions. And I mentioned earlier that this study is now at the Journal of Hydrometeorology if you want to read more about our study. Thanks.
All right, well, thanks, Jay. Does anybody have any questions? If you could hit the raise the hand or write in the chat. I'm not sure if I'm seeing any yet. So, but that was really interesting, Jay. I really like that composite you have there. I think I can see that being really useful to some of the forecasters when assessing that potential. So definitely some useful, operationally useful information there.
Yeah, and I'll just add that I was in touch with the folks from GRAY and also the Northeast River Forecast Center. And the idea that atmospheric rivers contribute to the environment preceding ice jams is not uncommon. They're well aware of it. However, using the atmospheric river terminology and the breadth of a lot of the studies that have come out of the West Coast in the last couple years, it does provide a framework for potentially identifying these cases from, in a modern way. That is not to discount some of the Maddox et al. Synoptic typing that also is very similar to the synoptic pattern.
Oh, and I think we do have one more question from Christina. Let me unmute her. She sent it here in the chat, but I'll let her talk. Oh, Christina, if you unmute, I think you could ask your question.
Thanks, Brian. Thanks, Jay, for your presentation. I found it very interesting and very useful for operational meteorologists. I noticed you mentioned the importance of above freezing temperatures and dew points, which will assist in melting snow. That's something that I actually have been trying to pay close attention to when we're anticipating potential breakup jams. Do you have, in your research, have you discovered, or do you have like a best practice for kind of keeping an eye out for the number of hours needed for dew points specifically to stay above freezing before maybe maximizing their efficiency at melting snow? I think there was one case we had locally in the Albany area, I believe it was February 2018, in late January, and our southern Vermont areas had very, very terrible flooding as a result of a breakup jam. And I believe I did a little quick study looking at some of the ASOS temperature gauges temperature sensors nearby. And of course, southern Vermont, we don't have too many, but we did have a few. And I found, I think it was about like 30 hours where the dew point was at least 35 degrees, if not more, leading up to the event, which contributed to melting snow. But that was just one case. I didn't really do a thorough study, but I did notice you mentioned it in your study. So did you have maybe like a best practice for maybe kind of a range of hours that dew points need to stay above freezing to really maximize their efficiency at melting snow?
I do not have a specific answer. The idea that we have a number of hours above freezing was derived mainly from our two case studies in 2017 and 2018. We didn't specifically look at the number of hours across all of our composite members, but that would be an interesting statistic to compute. My guess is that somewhere between 12 and 36 hours is probably some type of minimum amount. but I'm not familiar with any research that links the two specifically.
Okay, thank you.
All right, thank you very much. So we're going to go on to our next speaker here. So we're going to have Neil Strauss from the Northeast River Forecast Center, and he's going to be talking about some record-breaking floods from the very big Halloween flood event from last year. So Neil, can you hear me, and can you unmute yourself?
I can hear you. Can you hear me?
Yes, we can. I'm going to
Great.
make you presenter, so you should get a box pop up, and just hit OK, and then you should be able to show your screen and take it away.
Okay, so can you see my screen now?
Yes, we can.
Great. Okay, thank you. Hi, I'm Neil Strauss, Hydrometeorological Analysis and Support Forecaster from the Northeast River Forecast Center. Welcome to the record-breaking floods presentation from October 31st to November 1st of 2019. The NERFC provides river forecast guidance, quantitative precipitation forecasts, quality assurance of precipitation estimates, additional products and support for 200+ river forecast points, covering most of New York State and New England. First, I want to thank my manager, David Valley, for providing some initial feedback on this event. Also, thanks and acknowledgement to Christina, Britt, and Victoria for a thoughtful discussion on this event. So the topics we'll go over include the introduction, and then we'll go on and look at the antecedent conditions, including past precipitation, stream flows, and the Palmer Drought Index. Then we'll take a look at the hydrometeorological overview and meteorological forcings. We'll also examine the flood reports and overall verification for this event. And we'll follow up with a summary, including the hydrologic impacts. So we had a widespread significant flood event for October 31st to November 1st across northern New York into northern Vermont. Preceding this event, we had 1 to 3+ inches of rain on October 16th and 17th, and that helped moisten the antecedent conditions, increasing to wetter than normal leading up to this event. We then had another round of significant rainfall quickly occurring in the same areas on October 31st to November 1st. In total, 22 river forecast points reached or exceeded flood stage. We had 15 points with reached or exceeded moderate flood, 8 which reached or exceeded major flood, and 5 points had record flooding, which we'll go into more depth about. The average lead time for these flood locations was 16 hours. Probability of detection was 0.85, and the false alarm ratio 0.06. Taking a look at the Palmer Drought Index, an indicator of a longer-term soil moisture content from past weeks to months, we noticed that moderately moist to extremely moist antecedent conditions led up to the flood event across northern New York State and into Vermont. In fact, we had much above normal precipitation during October of 2019. And the overview from past weeks to months, January to September, featured near normal to above normal precipitation across most of the Northeast. And in fact, if you look at the Adirondack region into northern Vermont, we see that we've had much above average precipitation for that time frame. And well above normal to near record October 2019 precipitation totals were reported over a 125-year period of record. St. Lawrence County set a precipitation record for the month of October. The NERFC precipitation estimates, well, we had well above normal precipitation observed during October, 4 to 6 inches above normal in central and northern New York and into northern Vermont. 9+ inches of rain accumulated in these same areas, or many of the same areas. So we had a significant rainfall event on October 16th and 17th. The 24-hour Advanced Hydrologic Prediction System analysis above indicates a 1 to 4 inches of quantitative precipitation estimate within 24 hours across eastern New York State and in New England. This helped moisten the antecedent conditions prior to the following October 31st to November 1st rainfall event. Now, the Advanced Hydrologic Prediction System precipitation analysis is actually derived from the RFC's MPE, or Accumulated Multi-Sensor Precipitation Estimates, with observed 24-hour totals ending at 12Z. The mean aerial precipitation, or gauge-based totals, were the highest across the Hudson River Basin into southern New England. The gauge-only precipitation totals, or MAP, is the typical default which is used for river modeling in the fall and the winter months. And then we had the significant rainfall event on October 31st to November 1st, which fell in a 6 to 12-hour period mostly. The quantitative precipitation estimates range from 2 to 5 inches across northern New York into northern Vermont. The mean aerial precipitation gauge-based totals were the highest from the upper Hudson Valley, the Adirondacks, and the Champlain Valley of New York and Vermont. Taking a look at the daily stream flow conditions and snow water prior to the event, we see that the stream flows were above to much above normal across most of central and northern New York and into Vermont. And there was no snow and no snow water equivalent available for additional runoff. The hydrometeorological overview for the upper levels, the 300 millibar wind speed, or jet max, was nearing 150 knots for this event, which is quite substantial. The upper level low, which was quite vigorous and compact, quickly tracked across the Great Lakes region, while we had a 500 millibar ridge, which remained across the western Atlantic. At 850 millibars, we had a strong southerly low-level jet observed up to 70 knots, providing quite a bit of warm air advection for this event. The 850 millibar standardized anomalies were 3 to 4 standard deviations above normal, according to the Ensemble Situational Awareness Table archives. And the 850 millibar temps were approaching 15 degrees Celsius, even as far north as New York State and New England, which is quite mild for the time of year. The surface analysis and infrared satellite image shows a strong cold front arriving in western New York, separating continental polar air from very moist subtropical air. And the dew points were in the 60s ahead of the cold front, with dropping off into the 30s behind the cold front. And we see that the infrared image shows some cooler cloud tops from the mid-Atlantic region to the northeast. The precipitable water and water vapor transport anomalies were quite impressive. The global ensemble forecast system mean precipitable water values, or deep layer moisture anomalies, were 3 to 6 standard deviations above normal across the NERC area. And the NAIFS integrated water vapor transport values were 4 to 8 standard deviations above normal. In fact, we're seeing values as high as 1250 and 1500, which is quite impressive. An atmospheric river event likely occurred. What's an atmospheric river? Well, it's typically a few hundred miles wide and can span well over 1,000 miles long from the subtropics or the tropics poleward. It's typically associated with the warm conveyor belt, and just ahead of the cold frontal low-level jet. It's responsible for the majority of moisture transport across the mid-latitudes and can typically lead to significant precipitation events. Now, I've listed some of the threshold values here per study of Ralph et al. And it's important to note from the study that the threshold values were found across the northern Pacific Ocean. These threshold values are simply a guideline and can vary per time of year, sea surface temperatures, and different areas around the globe, different latitudes. Taking a look at the NERC QPF bias compared to the gauge-based MAP quantitative precipitation estimates, we see that the QPF had a low bias of up to 10 to 50% across portions of the upper Hudson Basin and the Lake Champlain Basin. We did have a QPF high bias of 10 to 50% observed in the St. Lawrence Valley region. And looking at the QPF versus observed MAP, we do notice that there's significant variance with the higher QPF amounts. The river flooding for both of these events, October 16th and 17th, we had 5 river points which reached minor flood stage. And then the following event, significant river flooding, was concentrated mostly across central and northern New York State and in Vermont. In fact, there are 22 points overall. There were 3 points which reached flood stage for both of these events, including the Sacandaga River at Hope, New York, West Canada Creek at Cass Bridge, and at Troy, New York, the Hudson River at Troy. And then we had 5 points which experienced record flood levels on October 31st to November 1st, and we'll go into that shortly. Now, the NERC issues a daily flood outlook product, and we had an area advertised on October 31st of likely significant river flooding from the Mohawk Valley to the upper reaches of the Hudson River in the Adirondacks of northern New York. In yellow, we had a possible significant river flooding, mainly across the Champlain Valley region of New York and Vermont. And when we talk about significant river flooding, it means the criteria of reaching moderate flood stage or higher at our river points. And we did have 15 river points which reached moderate flood stage or higher, many of them in New York, and we also had a handful of them in Vermont. Taking a look at the NERC forecasts and the record flood at West Canada Creek at Cass Bridge, we see that in the gray dotted line is the sharp rise on October 31st of the river stage, and then the solid lines there, multicolored solid lines, are the issued NERC forecasts. And we do notice a sharper rise than some of our forecasts had indicated. And there are a few reasons for this. One is that the QPF amounts were underestimated in portions of this region. Secondly, in the hydro model, our precipitation forecasts are basin average over a 6-hour time frame. Thus, if heavy rainfall occurs in a shorter period or overlaps 6-hour time frames near synoptic hour times, the rises can be underestimated. And the third factor is that evapotranspiration is calculated within the hydro model per temperature input and time of year. The October time frame is typically when the evapotranspiration decreases due to many kinds of vegetation becoming more dormant. Thus, less absorption of water is possible, especially without any snowpack. And we see here the Sacandaga River at Hope, New York reached record, beating its previous record in February of 1981. And the approximate annual exceedance probability according to the USGS was around 0.5% or greater than the 200-year flood recurrence interval at this location. The NERC guidance lead time was 11 hours to flood stage. And I should also notice that, point out in that at Cass Bridge, you also had the flood was also around 0.5% annual exceedance probability or greater than the 200-year flood interval at that location. We'll skip ahead to the next one here. West Canada Creek at Hinkley Dam reached its record value on November 1st, beating its prior record on April 28th of 2011. The NERC guidance lead time was 16 hours to flood stage and 2 hours to major flood. The Mohawk River at Little Falls, New York reached its record on November 2nd, beating its previous record of on June of 2006. A lead time was 37 hours to flood stage and 3 hours to major flood. And the Missisquoi River at North Troy, Vermont reached a record flood stage on November 1st, beating its prior record in June 12th of 2002. Our lead time was 13 hours to flood stage and 1 hour to major flood. Again, you notice the sharp rise in the river stage a little quicker than some of our forecasts had indicated. Taking a look at the verification table, the overall table of the river flood points for this event, the average lead time, as I previously mentioned, was 16 hours to flood, 4 hours and 15 minutes to moderate flooding, and 1 hour to major flooding. Here is a look at the 18 New York and 8 Vermont County disaster declarations due to flood and wind impacts, impacting especially the southern Adirondack region, where upslope southerly winds helped enhance precipitation totals, and in northern Vermont. So the hydrologic impacts in summary: very moist and to extremely moist antecedent conditions developed, especially due to the October 16th to 17th significant rainfall event. We had 2 to 5 inches of rainfall, which accumulated during the October 31st, November 1st event. And it occurred in a short period of time, 6 to 12 hours across northern New York and northern Vermont. We had an anomalously deep moisture plume with significant moisture transport, and that was an important contributor to this event. In addition, the heavier rainfall totals in a short duration led to some sharper and higher than forecast rises. These factors had helped bring record flooding to portions of northern New York State and northern Vermont. As I previously mentioned, there were 22 river points that reached or exceeded flood stage. We had 15 river points which reached or exceeded moderate flood. 8 locations reached or exceeded major flood, and we had 5 locations experiencing record flooding. The West Canada Creek at Cass Bridge and the Sacandaga River at Hope had reached their 200-year flood recurrence intervals. Several additional points along the Upper Hudson River, Mohawk River, and the East Branch of the Osable River had reached 25-year or greater flood recurrence intervals, according to the USGS. As I mentioned, we had 18 New York State counties and 8 northern Vermont counties, which were declared federal disaster declaration areas due to wind and flood damage. We also had significant road and bridge damage and closures, which occurred in these areas. And numerous evacuations had occurred in northern New York and northern Vermont due to flooding. And there was 1 flood-related death that occurred in Herkimer County, New York. So that is the end of my presentation. If you have any questions or comments, thank you.
Okay, well, thank you, Neil. That was really interesting, and we're getting close on time here. So I think we'll go to the next talk, which is about the talking about the same event. So we can move on to Victoria and Christina. And I think you guys should be able to just unmute, and I think Victoria, we're showing your screen, right?
Yep.
Okay, let me make you presenter. All right, so it should be going over to you.
All right, can we see my screen?
Yes. Yep. And you can just go and you can, if you can just go into present mode there, you can just hit the, so it's full screen and everybody can see everything. And then we should be all set.
Okay.
You can take it away.
All right, so good morning. My name is Victoria Zenobio. I am an undergraduate student at SUNY Albany. And today, with previous help from Christina at the National Weather Service in Albany, I will be giving a meteorological review of the events and factors that led to the historic 2019 flooding in upstate New York. So briefly, I would first like to discuss why we are interested in this case study in the first place. Well, the unusual amount of rain that fell from October 31st to November 1st led to multiple river gauges across the southern Adirondacks to reach record-breaking crest levels. The topography of the southern Adirondacks, along with the southwesterly flow or orientation of the winds, aided in additional lift of the system, and the quickly rising waters from the flooding rivers covered major roadways and filled the streets of small towns. Unfortunately, there was one fatality that occurred in Herkimer County as a result of the extreme flooding. Several counties in eastern New York also experienced widespread power outages due to strong winds during and after the cold front had proceeded through the area. The severity of damage due to flooding or severe winds prompted our Governor, Andrew Cuomo, to declare a state of emergency in multiple counties. So we all have heard the saying that a picture is worth 1,000 words. So let's take a look at the extent of the damage caused by this event. This first one was taken in Herkimer County on Route 28 and is just one example of the multiple downed trees and power lines that occurred through much of the state. We will see later on that downed trees and power lines caused approximately 92,000 power outages across the state. Next up in Fulton County, we see the rising waters of the East Canada Creek spill into the village of Dolgeville. It is estimated that 344 dwellings were damaged. Therefore, the Red Cross actually stepped in and housed those displaced by the floodings. Lastly, we have these photos taken in Saratoga County, which shows the extent of the damage done to multiple roadways due to flooding waters. So for the weather overview, I will begin with the synoptic features along with the anomalous occurrences that resulted in such an impressive severe weather event. I will then analyze two soundings taken in Albany just before the passage of the cold front. Lastly, I will discuss the severe weather that took place along with the impacts it had on multiple communities. So before jumping right into the weather analysis, let's take a look at the county warning area, or CWA, for the Albany National Weather Service. We can see that our area of interest, which is the southern Adirondacks, is quite elevated. We will see later on that this topography does play a role in the total rainfall amounts in this area. So beginning at the surface, we see a development of a low pressure system in the Ohio Valley at 0 UTC on the 31st. The cold front proceeds northeastward as the low matures, which is indicative by the stronger pressure gradient seen at 12 UTC on the 31st. In the bottom left-hand panel, we have 0 UTC on the 1st, and we see that the cold front has reached the periphery of the southern Adirondacks as the low matures to 992 hectopascals. The low becomes occluded by 12 UTC when the cold front exits the Albany CWA area. So moving on to the 500 millibar maps, we see what once was a positively trough in the 0 UTC map on the 31st begins to close off by 12 UTC, which signifies that the cyclone is intensifying and that strong southwesterly winds will continue just downstream of the trough. By 0 UTC on the 1st, we see that the trough becomes negatively tilted and is closed off while being positioned over the Ohio Valley. This is going to put New York directly in the area of favorable upper level divergence at this time. By 12 UTC on the 1st, the trough has tracked away from New York and follows along the St. Lawrence River Valley. So at 300 millibars on the 31st at 0 UTC, we see an impressive jet streak that reaches up to 150 knots. And as the trough becomes more negatively tilted by 0 UTC on the 1st, we see two distinct jet streaks become more prominent. Western New York is therefore located in an area of enhanced lift due to the coupling of the two jet streaks. This will also coincide with the location of our strengthening low pressure system. Moving to 700 millibars, we see that the trough definitely dips down southward towards the Gulf of Mexico at 12 UC on the 31st. So along with the very strong southwesterly flow we see, strong moisture is able to be carried northward towards New York. And finally, at 850, we see strong warm air advection increasing between 12 UTC on the 31st and 0 UTC on the 1st as our trough amplifies. And this is going to create a strong forcing for further ascent. And with the winds increasing to 60 to 80 knots at 0 UTC on the 1st, additional warmth and moisture was able to reach New York. Lastly, at this time when Albany was still in the warm sector, Albany had reached a high temperature of 75 degrees Fahrenheit for that calendar day. So exactly how much moisture was present at this time? The loop demonstrates the high value of moisture that was evected away from the Gulf and towards the usually cold and dry New York fall day. We can see a significant amount of moisture present in the upper levels before the cold front even reaches New York. The precipitable water values, or PWAT, began at 3 standard deviations above normal on the 31st at 12 UTC, before increasing to 4 standard deviations above normal by the 1st at 0 UTC. On the right, we have the anomalously strong upper winds that we can thank for infecting this moisture northward. In this diagram to the right, we can see the mean wind speeds, which showed standard deviations of 3 to 4 above normal at 500 millibars. So as a result of the combination of strong southwesterly winds and an abundant amount of moisture in the troposphere from the Gulf, the combination allowed an unseasonably large amount of moisture to be evected into New York. At 18 UTC on the 31st, the moisture flux was 4 to 5 standard deviations above normal, before quickly exceeding to 5 before the passage of the cold front by the 1st at 0 UTC. So now that we've had a look at the anomalous values that occurred, let's take a look at the impact on Albany at this time. So from a sounding at 12 UTC on the 31st, we can definitely see Albany is still in the warm sector of the low pressure system. We also immediately see deep tropospheric moisture, which is represented by the PWAT value of 1.73 inches. Lastly, we can see that there is relatively low CAPE as the environment appears to closely follow the moist adiabatic lapse rate. Jumping ahead to 0 UTC on the 1st, just shortly before the passage of the cold front, we still have veering winds, which is indicative of warm air convection. The dew point also increases to the mid-60s as the ambient air grows closer to saturation. The wind profile to the right shows significant speed and directional wind shear in the boundary layer and lower troposphere. Although we see the continuation of a high shear, low CAPE environment, the 6.4 Celsius per kilometer lapse rate was sufficient enough to produce thunderstorms at this time. More notably, Albany had a PWAT value of 1.88 inches, which was an all-time high for October 31st. Last but not least, we see that the warm cloud depth reached 3,000 feet, which alerted forecasters that this environment could be favorable for extreme flooding. So the outlook of the storm from the Storm Prediction Center had an enhanced risk area for the mid-Atlantic, with our area of interest, the Southern Adirondacks, residing in the slight risk region. The very high anomalous synoptic winds during this event put our area of interest into the 15% area for the wind outlook. Lastly, this graph here shows the areas where a severe thunderstorm watch was issued. So how did the day actually play out? In this loop, we unfortunately missed the beginning round of precipitation that occurred in the Adirondacks from 4 to 12 UTC on the 31st, but we do see the bulk of precipitation that resulted in extreme flooding which begins at 18Z on the 31st. A linear band moves through the area around 1 and 4 UTC, bringing strong thunderstorms with it. The precipitation appears to end around 8 UTC on the 1st, and although the precipitation has moved out of Albany's CWA area, we will see severe winds continue throughout the region. So this map is going to show the rainfall total amounts through Albany's CWA area. We can see that the Southern Adirondacks, due to the persistent rainfall, receives 2 and 5 inches with an isolated maximum of 7 in Hamilton County. With the southwesterly orientation of the winds, it caused the very moist, the tropical air mass to move up and over the higher terrain, causing the total rainfall in this area to be much higher. Next, we have a mesonet loop of the winds that occurred. We can see with the tight pressure gradient that had developed just ahead of the strengthening cyclone caused strong winds to reach gusts of 30 to 50 miles per hour just before the cold front and even before the thunderstorms happens. Due to the high shear low cape environment that we had, sufficient instability along the convection allowed strong winds aloft to mix down to the surface. So in the next 2 maps we have here, we will see the wind speeds after the passage of the cold front. On the top left, we see maximum wind gusts just after, which gusted, with winds gusting 40 to 55 miles per hour through eastern New York. On the bottom right, we see the continued duration of the strong winds, where strong winds remain due to that mixing. In these 2 maps, these are demonstrating power outages through New York. We see that at 7:45 a.m. on the 1st, there were approximately 10,000 outages, and shortly after, only 3 hours after, we see that the continued strong winds most likely caused trees and branches to fall, only causing more outages to occur through the area. As far as severe weather damage goes, this local storm report shows locations where there's damages due to wind and flooding. We can see multiple flooding reports clustered in Herkimer County. Herkimer County, in fact, saw such high numbers of flooding reports and rescue operations that a flash flood emergency was issued, which would be the first since 2013. And briefly, I know Neil had discussed this, but I believe it's important to take note of the pre-existing conditions. So from October 16th to the 17th, we had 2 to 3 inches fall in the Southern Adirondacks. This would have made the soil very moist before the Halloween event. In addition, the end of the growing season was the 5th, which indicates that vegetation may have become dormant at this time. If plants, especially trees, are not absorbing as much moisture into their roots, then substantial runoff may have increased the intensity of the statewide flooding. So the main takeaway from this event was that a low pressure system resulted in anomalously strong winds, which was able to evac a moisture plume northward into New York, which resulted in the intense rainfall. winds aloft after the passage of the corresponding cold front mixed down to the surface, causing reports of severe weather damage. Lastly, the previous conditions of moistened soil may have played a role in the amount of runoff that made it into river basins. So that is going to conclude my presentation. So I will leave the last few minutes for the audience to ask any questions.
All right, well, thank you very much, Victoria. We do have a few minutes, so if anybody has any questions, we can take them. Either hit the raise the hand or put it into the chat or questions option there on the dashboard there. So let's see. All right, I don't think any questions have come in yet. Definitely really good job, Victoria. It's definitely a really interesting event, and I mean, we have 3 talks on it, so I know it's definitely been one of the bigger events in the last few years to get that much attention, but definitely really good job. All right, so I guess we'll go on to our next speaker, who is Britt. So I'm gonna unmute you, Britt, and give you control. All right, you should be unmuted there, Britt.
All right, can you hear me?
You sound a little low.
Hang on, let me try. How about now?
Yes, that's definitely much louder. Thank you.
Okay, thanks.
Okay, so all right, you should have the box pop up and just hit OK, and then should be able to have your screen come up. Yep.
Computer's thinking really hard about showing this slideshow.
Yeah.
Can you see my title slide?
Yes, we can.
Perfect. All right. Well, thank you, Ryan. As Brian said, my name is Britt Westergaard. I'm the Senior Service Hydrologist here at the Albany National Weather Service. And I want to echo what Neil said, which is I really appreciate, with 3 of us working on the presentations on one event, I really appreciate the discussion and collaboration to make sure that we were covering everything we could possibly cover with as minimal overlap as possible. So I think we're doing a great job of telling the story here. So here's the plan. To kind of dovetail on what Victoria was talking about, now that she's covered the meteorology, I'd like to talk about the rainfall amounts and then the resulting flooding. So I have some hydrograph reviews that we'll talk about, and then I'll climb on my soapbox a little bit about how, how geography affects hydrology, and then I'll finish up with a brief discussion of some of the Albany NWS operations and challenges that we saw during the event. So as Neil and Victoria both mentioned, I'm not going to get too into the weeds with this, but it was a very wet October leading up to this event. So as you can see, there's portions of the Western Adirondacks. Is there a tool here where I could be dangerous, like in person, with a laser?
I'm not sure. I think if you show your mouse, will that go over or not? Or I'm not too sure.
It says I have the spotlight highlighted, but it doesn't actually seem to be. Can you see my mouse at all when it's moving around?
Yes, we can see your mouse at least.
Oh, okay. Well, I'll go with that then. Thanks. So yeah, as you see here in the Southern Adirondacks throughout the month of October, and I think Neil highlighted one major event earlier, but as you'll see when we do the hydrograph review, there was actually just a little blip of an event with maybe another inch adding to the total just before the event at the end of the month. So yeah, a solid like 6 to 8 plus inches for the month, which is not too shabby. And so this will look familiar because this is the same map that Victoria showed, which is a map of the rainfall totals. You'll notice that there was a secondary maximum in addition to what happened in the Southern Adirondacks. there's a secondary maximum in the Catskills too, and you'll notice that when we go through the results in terms of what record, what forecast points saw flooding, they'll be highlighted as well. But what I'd like to draw your attention to here is you can see there's a number of sites reporting in the 5-inch vicinity. We also had one 7-inch report, which came in after the event. So it was a CocoRa's report that came in the following morning. So excellent for post-event analysis, not so terrific for real-time situational awareness. But what was terrific for real-time situational awareness were these ones that I've underlined in yellow here, the 5.05 and the 5.19. 5.19 was the Pasico New York State Mesonet site in Hamilton County, and then 5.05 was the Cold Brook Mesonet site in Herkimer County. And so these New York State Mesonet sites report 5-minute rainfall data, and so that was superb in terms of trying to get a handle on what was happening in real time as we're getting in reports of flooding as well. So let me move forward and talk about, so that's what happened as a result of the heavy rainfall. This was your totals. So let's look at some of the hydrographs. Oh wait, just kidding. I threw this in here too. Speaking of the Mesonet, this is really excellent because you can actually see this is accumulated rainfall throughout the event. And with apologies to the researchers among us, this is in inches because I'm not an operational hydrologist, and so this is how my brain works. But you can see both Cold Brook and Pasico that I called out in the previous slide here. This is the accumulated rainfall. And what's interesting to note is that, as Neil kind of alluded to in his discussion, things get complicated with the river models when you start bisecting these synoptic periods with your heavy rainfall. And so you can see the bulk of the heavy rainfall fell between 0 and 6 Z on the 1st, but there was a non-trivial amount, like 1.5 inches or so, depending on which station you're looking at, that fell before 0 Z. And so the river models, you'll see, have an interesting time trying to sort that out. And so as a result, this is sort of what we saw as far as flood crests. So orange are the minor flood locations, so Canajoharie, Troy, Meadowee at Granville, and Mount Tremper. We saw moderate flooding on the Hudson at Fort Edward, Hadley, Riverbank, North Creek, also Delta Reservoir, and then finally the major and record flooding that happened, which was both at Hinckley, at Gasbridge, at Little Falls, and also up here in southern Hamilton County at Hope. So diving a little bit deeper into those hydrographs of the floods is something that I'm so excited to do that I keep thinking that's the next slide. So as a summary of the event, what we saw was a total, in the previous map, you saw a total of 13 flood crests at river forecast points. You saw 4 major/record floods, 5 moderate floods, 4 minor floods. We issued 2 flash flood emergencies, which Victoria mentioned. We unfortunately had 1 fatality. We also, and I'll talk about this more in the operational consideration section, we had 2 Condition B declarations, which is a potential failure declaration at a dam, one on the West Canada, one on the East Canada Creek. And so we issued flash flood watches for those. And then we also had a number of high flow alerts from various dam operators. We had 6 of those. In addition, I wanted to call, Neil mentioned the return interval of some of these record peaks. I also think it's interesting to note, kind of like when you're looking at climatology, it's not very exciting if I break a snowfall record, and I've only been observing snow for 2 years. But much like that, the river gauges that broke these records, these 4 right here that are listed in the blue box, this is a very long period of record for a river gauge to have in the vicinity of 100 years. So very impressive amount of water to be breaking 100-year records. So this is the part that I was so excited to get to, because of this excellent archive that we have at our regional headquarters of these AHAPS graphics. you're actually able to go back and pick hourly hydrographs out. And I made sort of a little flip book here. And what you're looking at is hourly clips of our public website, our public forecast. And so the blue on the left of the, to the left of center is the observations, and the purple line to the right of center is the forecast. And then the lines that you're seeing, the yellow, the orange, the red, and the purple, those are flood levels, so action level, minor, moderate, and major, and those are defined by location. So each river forecast point has its own definition of what constitutes minor flooding, moderate flooding, major flooding, and those are determined locally in collaboration with emergency management. And so this is where you can see the forecast very much catching up as it climbs. In any case, those flood levels are determined, they're site specific. And so they're determined by impacts. So each one will be different. So let's move on to the next one. And similarly, you can see here, so the previous one was Hope, so that was sort of in the eastern portion of the heaviest rainfall. And now we're looking at sort of the western Mohawk area, which is West Canada Creek here at Hinkley Dam. And you can see we came down off of a previous event. And we're coming up here again. Like I said, we had, it wasn't anything terribly significant, about an inch, but when you keep having these rainfall events over and over again that don't let the reservoir drain too terribly much, you're setting yourself up for, much like with the wet soils, you're setting yourself up for an event where rainfall can accumulate and put the reservoir to a point where it's going to spill. And so I believe at this point, the minor flood stage is set at the point where the reservoir starts spilling. So you can see this is the forecast goes to moderate flood stage here, but as conditions change and we get a handle on the rainfall, we go to record and then even above record. You can kind of see that record line is above major, that extra black line there. So hydrologists don't really get excited too much about the recession line, at least this one doesn't. So we'll move on here. And then this is where things get really wild, because the West Canada Creek at Cass Bridge is downstream. And you can actually, we'll take a look at the map and you can see why things got a little hairy here, but this is always a very fast responding creek, and this event is absolutely no different. And so you'll see things take a turn from, you know, a forecast of minor to blasting through major flood. This is also downstream of the previous hydrograph series we were looking at, so it's downstream of that reservoir. And so the other thing that we'll see as we go through here, here's your first forecast of minor. I'm hoping you're all seeing these graphics.
Yes, you're looking good, Britt.
Okay, good. Because otherwise my narration might make no sense at all. All right, so we're climbing up to moderate, and you can see it blasting right past moderate there within the period of a couple hours and heading straight for record. And so this second peak is also really interesting, because this second peak is the release from the reservoir. And so this is part of my, you know, soapbox to let forecasters know that you have to think about what story the hydrograph is telling you. The other interesting part of this is that that area where it kind of flattened out, where you thought, oh, maybe the second peak isn't going to be so bad, was actually water getting dammed up by a home floating downstream and damming up against a bridge. And so the water backed up, and then eventually that dam released, and that's where you saw that second crest. And so finally we'll go downstream from there. And so again, you'll see the sort of double crest of the water making its way from Cass Bridge, but it's attenuated a bit because this is the main stem Mohawk as opposed to one of the tributaries. Again, you're seeing this event from the 27th and 28th already holding the river up. Not leaving as much room as if it had been dry. So you can see that first forecast for minor. And then as we start to get a handle on what's coming from upstream, you can see the forecast go up from moderate to major to record once we start getting a handle on the upstream inputs. And then there's that second rise from the reservoir releases that you also saw at Casperidge. And a bad data point pocket there. All right, so this is the part where I really climb up on my soapbox. I stole this from a presentation I gave at our staff meeting too, so those in the office will be familiar with this, but this is where it really pays to know your service area. And so the blue lines are streams, the rivers, streams, creeks, and I'm going to flip back and forth between this and the next slide is the rainfall totals. So you'll forgive my, hopefully you'll forgive my sort of cartoon drawing of this orange watershed divide. But when I added all of the river basins on there, the map was completely unreadable. So I'm hoping to simplify this discussion a little bit. And so this is the drainage divide. Everything to the west of this sort of orange squiggly line drains westward and then eventually south into the Mohawk River and then back east again. So it sort of takes one way around, let's say the counterclockwise way to Albany. And the other side of that drainage divide, so the creeks and streams that drain into, for example, Hope up here, HOPN6, that all flows westward and then down the Hudson and eventually southward to Albany. So it sort of takes the clockwise way to Albany. And so if you keep that drainage divide in mind and look at the next map where I've kind of attempted to sketch the same drainage divide in here in blue, you'll see that one of the challenges we saw was the heavy rain sort of bisected this drainage divide. So it's important to have awareness of which way, not just how much rain fell, but which way it's going to go. So some of the rain affected the Western Mohawk and took the counterclockwise way, and the rest of it took the clockwise route. And so knowing which is going where is non-trivial in an operational setting. The other thing that I wanted to point out back on this Google Earth map is this sort of red highlighted area that I have over here, which operationally is problematic for us for several reasons. Number one, it's called the Cincinnati Creek, and it flows in to the West Canada Creek above Cass Bridge. It's unregulated and also ungauged. And so trying to understand how much water coming in from here is a huge question mark in understanding how much water is going to show up at the Cass Bridge forecast point. And also, just to add another layer of operational complexity, these white lines here are the boundaries of our county warning area, so the boundaries of our service area. You'll notice that there's no rainfall total, for example, on the next map for that area because that actually is part of Binghamton's county warning area. And so we have rainfall that's sort of, appearing as if by magic on the borders of our county warning area that we need to be aware of how much there is and where it came from. And that's something that's also can be very tricky in an operational environment. And so just kind of as a summary of what our operations sort of looked like, we had a flood watch that was already issued on Wednesday afternoon. We had a number of flash flood warnings, including lead time on the very first one on the evening of the 31st, with, as Victoria mentioned, that 11 p.m. upgrade to the flash flood emergency. We had river flood warnings based on those forecasts that Neil was showing you, with on average over 4 hours to flood stage and about 13 hours to crest, though as you saw, well, we'll talk about the challenges in a minute. We were using the New York State rainfall monitoring in real time to help us with situational awareness in addition to the reports that we were getting from spotters and emergency management. Operational staff also had direct contact with the New York State OEM Watch Center as the warning categories increased. Because another operational consideration is each time we were seeing the forecasts change categories there on those lines in the graphs, each one of those changes requires a new flood warning because, presumably the severity of the event has increased. So we need to alert the public to that. And so there was direct contact with the Watch Center about those. I liked our shift log description of the increases, which were listed as rapid/insane, which I think is accurate. We also let them know there was very nearly flooding of the New York State Thruway out on the Western Mohawk. It came very, very close, and we're monitoring it through the event for the possibility of closing it because of the rainfall. And that was in our flood impact statements. And so folks were taking a close look at that. Another great thing that happened was right after the event, as things were still winding down, one of the members of our web team posted an event website, which was fantastic. If you want to check it out, there's the link, but it was really great in terms of answering questions that we had coming in pretty rapid fire. So we were able to add rainfall totals and flood crests and all sorts of other information as we had it to answer public and media questions. And finally, as far as challenges, as Neil kind of mentioned in his talk too, the rainfall was under forecast. So while we had an inkling that there was going to be river flooding, with a 10 to 50% low bias in the QPS, we did not have an inkling that there was going to be record flooding at 4 forecast points. So as you saw in the hydrographs, I think, we were playing catch up for a good portion of the event as we were trying to understand the magnitude of the rainfall. The magnitude of the rainfall was very difficult also because right here in the second bullet, the heaviest rainfall that we had was in one of the least populous portions of our county warning area. Hamilton County is, heart of the Adirondacks, minimal population. And so that 1 7-inch report and the 5-inch reports from the Mesonet, I would wager, if anybody's, doing donut bets these days, I would wager a donut for sure that we had more than 7 inches in some locations up there to see the level of rise that we saw. We also, had those multiple condition B declarations, which require flood watch issuance. It could be a little dodgy operationally, especially the one that was the West Canada Creek shares the border, as I mentioned, with Cincinnati Creek challenges with Binghamton, and so there was one point in time where Binghamton and our office actually had a shared Google Doc open, and we're just trying to make sure that we had the same wording going out in our flood watches for this event to make sure that the notification to the public was streamlined and that we were saying the same thing. The severity of evacuations varied. This was also a difficulty for situational awareness. There were some places where evacuations were made to literally get people immediately out of harm's way. There were other locations that we found out later that evacuations were really because people's egress from their homes or neighborhoods might have been affected, but the homes or neighborhoods themselves weren't in harm's way. And so trying to get a handle on the difference between those two things is challenging operationally. And then finally, things are always hard to get a handle on when the flooding happens overnight and when there's additional weather hazards, as Victoria mentioned, with the wind that we saw along with this event. So with that, I think I will take any questions. Otherwise, I will turn it back over to Brian.
All right, well, thanks a lot, Britt. That was really good. I love those animations of the hydrographs. It's just so wild watching those those changes with that.
Yeah, I'm a bit overly enthusiastic about myself, as you may have noticed.
Okay, we do have a question from Sarah Jamieson. So Sarah, let me unmute you. And yeah, Sarah, you can go ahead and ask your question.
Hey, Britt, I loved your presentation. Just kind of a follow-up about working such a significant event, and you mentioned some of the challenges, with the magnitude of the event, but how did that task the resources of the operations and actually forecasting such a diverse hydro event?
Yeah, I came in, I'll confess I came in to back cleanup on the overnight, so I wasn't there for the hairiest portion of it. It sounds like it was absolutely, all hands to battle stations, trying to get a handle on what was happening in real time. Yeah, I don't want to speak more than that to that because I wasn't there to experience, I guess. Was that sort of your question? I'm not sure if I answered your question.
Yes, in preparation for trying to prepare for such an event, we always try to look at staffing profiles when we're accurate enough to know we're going to get that kind of rainfall and subsequent flooding. But I do know that the workload is just exponential, not to mention phone calls and social media and everything. So it would be interesting to hear how it played out for your forecasters.
Yeah, and we definitely try to make sure that we're properly staffed for flooding, and in fact to try to make sure that if there's going to be river flooding and flash flooding, that we actually separate those out as operational duties and tasks, because we found that trying to maintain situational awareness on those two things requires sort of different data sets that you're looking at. So yeah, absolutely, it's always challenging, and like I said, I was on the overnight because the timing is always challenging on when the heaviest stuff is going to happen. And then often what happens is if you've underestimated the magnitude of the event, you underestimate how long it's going to last too. So that can be a challenge for staffing. Thanks, Sarah.
All right, well, thanks, Britt. And I think that brings us to our first break. So we're gonna take a short break, and we'll be back at 10:40. And when we come back for 10:40, then we'll have some of our NWP and modeling talks. So we'll see everybody back here at 10:40 Eastern Time.
Do I need to do anything to give you back control, or you can just take it?
Yeah, I'll do that right now.
Okay.
Okay, it's 10:40, and we're going to get into session B here. So our first speaker in this session is Matthew Seymour from the University at Albany. And Matt's going to be talking about the sensitivity of forecast precipitation type to WRF boundary layer parameterizations over complex terrain. So Matt, you just have to unmute yourself, and I'm going to give you control.
All right, can you see my screen?
Yes, we can.
Sounds good. All right, so thank you. I'm doing a talk on the February 6th to 7th, 2020 winter precipitation event that happened across eastern and central New York. Special thanks to Nick Bozzo from the Mesonet for assisting me in analyzing the data from there, as well as Mike Evans from the Weather Service in Albany for helping me pick out cases to study that have inherent uncertain precipitation type. So my thing isn't working here. Hang on a second. There we go.
It looks
all right. So
sorry, Matt, but it looks like we see both your current slide and your next slide.
Interesting. Okay.
Yeah.
Give me 1 second here.
Sure.
All right, is that better?
Let's see. It still looks like still white screen here.
It says not showing anything.
Yeah.
Let's see here. There we go.
Yep, that looks perfect. Great.
All right. So technical difficulties aside, so some motivation for my project. So of course, precipitation type forecasting is a challenge, especially when you have temperatures near freezing. You have synoptic features as well as mesoscale features that can help shape the thermodynamic profiles that make different precipitation types possible, from snow to freezing rain to rain. And you have mesoscale models that can help forecast winter precipitation type. But as we know, models are not perfect. You have inherent uncertainties and boundary layer processes, and these are magnified in complex terrain, as well as in situations where the temperature is near freezing. And a great example of that, of course, is here in eastern New York. We have the Mohawk and Hudson Valley, surrounded by the Catskill and Adirondack Mountain regions. And here on the right is a figure from IKEDA 2017. This is an example of this precipitation type uncertainty. Here you can see the circles, of course, of the ASOS observations. There's in this case, the model, which is the background color, is predicting rain up along those eastern Appalachians in the state of Virginia, whereas the observations here are indicating freezing rain. This is likely a cold air damming event, but it's just showing that you can have this precipitation type uncertainty, especially in areas with complex terrain, such as the mountains of the Mid-Atlantic, as well as here in the Mohawk and Hudson Valleys. So some research objectives that I'm looking into. So this particular study, looking into how uncertainties and boundary layer processes affect the predictability of these uncertain precipitation type forecasts. So basically I'm looking for cases with inherent forecast precipitation type uncertainty, conducting WRF simulations on these cases. In this particular study, altering the boundary layer scheme within the WRF model, analyzing the observations from the event, and then finally comparing them with the WRF output and looking into if and why the WRF is biasing towards a precipitation type that was not observed during the storm. So today we're going to look into the 6 to 7 February 2020 winter precipitation event that occurred in eastern New York. So getting into some data and methods, for the WRF model, I used WRF version 4.1.3, configured it similar to the HER, and used 3 nested domains at 9, 3, and 1 kilometer grid spacing. The respective locations are at the figure at right, and initialized the model using RAP analysis data. For this study, I tested 3 boundary layer physics schemes, the MYNN, the MYJ, and the YSU. I chose those 3 as they're well represented in the HREF suite of ensembles, HREF suite of models, I should say. And to diagnose the precipitation type and WRF, I used a decision tree approach with thresholds ranging from temperature, rain and snow accumulation, as well as the model microphysics. And then for observations, of course, the main data source I used here is the New York State Mesonet, which in the figure at right, the circles represent mesonet locations. As you can see, there's a wide range in elevation represented by the mesonet stations. I also used ASOS observations, which are nice because you have the precipitation type discriminator right on the station. However, ASOS has a bit of a disadvantage as to the spatial coverage. And then, of course, radiosonde observations from the Weather Service here in Albany to get a better view of the thermodynamic profile of the atmosphere. And I also used MPing reports. For those of you who don't know, MPing is a crowdsourcing precipitation type or crowdsourcing app that you can report precipitation type on. And then for the New York State Mesonet, I diagnosed that P-type using a similar decision tree approach, except using temperature, precipitation accumulation, and snow depth change thresholds. So looking into the event, I kind of broke this event into phases. So the first phase had some light to moderate snow occurred north of Albany, and then light snow changing to freezing rain occurred near and south of Albany into the Catskills and Lower Hudson Valley. The second phase of the event basically consisted of light rain and light freezing rain, depending on the surface temperature area-wide. And then the third phase, which is going to be the phase I'm going to focus on for the rest of this presentation, is when things got interesting. So we had moderate freezing rainfall from the southeast Adirondacks to near and just north of Albany. Plain rain fell near Albany into the lower Hudson Valley. And then behind an approaching cold front, a strongly forced band of heavy snow fell in the western Mohawk Valley in the vicinity of Utica and Syracuse. Then as that cold front moved east, we had an area-wide transition to snow between 15 and 18 Z, and the precipitation ended altogether by 0 Z that evening. So just looking into synoptics, some synoptics of the storm. So at 500 millibars at 15 Z on the 7th, you have a digging trough advancing into the eastern United States. You can see that Albany is well placed in the left exit region of a nice strong jet streak. It's well over 150 knots at that point, and the trough is increasingly becoming negatively tilted at this point. So we have favorable conditions for cyclogenesis at the surface and precipitation to occur across the region. So now zooming into the northeast in the box highlighted in the right, we're going to look at 850 millibar temperature advection. So ahead of this cold front, you have strong warm air advection occurring. It's going to intensify this warm nose aloft that's common with freezing rain setups. And then you also have strong chronogenesis back well to the west of Albany over the western Mohawk Valley, western Catskills, and even to the southern Adirondacks, which will help provide forcing for that aforementioned heavy snow band. And then further zooming into the eastern New York. So looking at some surface observations from the New York State Mesonet, this is at 14 Z on February 7th. You can see that we have mostly freezing rain occurring kind of near and north of Albany with rain south. Here you can see the freezing rain is best represented by stations that are below freezing, have a significant amount of precipitation accumulation, and are not increasing in snow depth. So from that, you can infer that there's likely freezing rain falling at those stations. And then back to the west, behind the cold front, you have snow accumulation. And in the western Mohawk Valley into the southern Adirondacks, 6 to 12 inches of snow ended up falling in that region. And then quarter to a half inch of ice in the southeast Adirondacks, as well as the northern portions of the capital region, then lesser amounts as you go further south. Going forward a few hours to show the approaching cold front a little bit better, you have now the northwest winds behind the cold front, and an increase in snow going on across portions of the eastern Mohawk Valley at this time. Still some freezing rain in the southeast Adirondacks, Saratoga County in particular, and still a little bit of rain down south in the lower Hudson Valley. So looking at the Weather Service forecast versus observed snowfall. So you have the forecast on the left and the observed snowfall on the right. You can see that the forecast was for, in the southern Adirondacks, you had 6 to 12, 4 to 6 as you get closer to the capital region. Here in Albany, 1 to 3 inches was forecast, and south of Albany, little or no snow was forecast. And on the right, you can see the observations matched up fairly well with the forecast. However, there were some slight biases, as shown by the bias map on the left. You can see that there was a slight low bias in the forecast, especially up into the Adirondacks and the upper Hudson Valley and portions of the Helderbergs as well. Most of the rest of the region, the forecast was about spot on. And then looking at ice accumulation, you have on the left, of course, the forecast, on the right is the observed. And from this, you can see that the observed ice was greater by about 1/4 of an inch across the southeast Adirondacks into the upper Hudson Valley again, and then greater than the forecast by about 1/10 of an inch in the Albany area as well as south of Albany. So looking into the WRF model, so the main takeaway that I found so far is that there's a sweet wide warm bias that develops in phase 2, most pronounced in phase 3, and it results in a precipitation type error. So here we have a map of each of the 3 model runs I did, the background color being the WRF output, and the colored filled dots being the mesonet observed precipitation. So here's the precipitation, of course. We can see that there's a bit of a wet bias, sweet wide, area wide as well. And the heaviest precipitation is displaced east of what the New York State mesonet observed. And then looking at temperature, the black circled area is the area that saw the greatest rain versus freezing rain precipitation type error. You can see here that most of the mesonets are reporting below freezing temperatures, denoted by the downward pointing triangles. And there's also a bit of a westward bias in the warmth in the WRF model, indicating a potential frontal timing error. So of course, temperature bias manifests itself as a precipitation type error. So here we have the 3 models once again, background color being the WRF diagnosed precipitation type, triangles representing MPING reports, and circles representing ASOS precipitation type reports. So in the west, you have the western box, you have kind of some freezing rain, some rain versus observed snow. So that is potentially indicative of the frontal timing error once again. However, in the eastern box, you can see that there's some rain versus freezing rain precipitation type error going on here. In particular, in the MYNN and the YSU, you can see that there's a report here just north of Albany of freezing rain, and the MYJ happens to be the only model here that's picking up on that freezing rain, having the colder area a little bit further south in the Hudson Valley as compared to the other 2 models. So now we're going to look at a time series from Schuylerville, New York. Here, of course, there was a precipitation type error during phase 3. You can see that the observations observed temperature stayed below freezing during the entire phase, whereas 2 of the models in particular, the MYNN and the YSU, climbed above freezing, causing a rain versus freezing rain precipitation type error. Even the MYJ kind of poked above freezing a little bit as well. So why the warm bias? So there's a few theories that come up with revolving around boundary layer dynamics and radiation. Here I'll discuss the boundary layer dynamics, including things such as mixing processes as well as altered terrain modified flow. So some hypotheses, so the mixing, if you have factors such that influence the strength of the mixing, so for example, stronger wind speeds or a warmer warm nose aloft, creating more mixing will lead to a warm bias, as well as the terrain modified flow. If you have southerly winds that are modeled versus if the observed winds are northerly, that could potentially lead to a warm bias as well. So looking at some soundings, so here we have at 12Z February 7th at Albany, we have the warm nose aloft is a little bit stronger, a little bit warmer, I should say, between about 900 and 800 millibars as compared to the observations. Temperatures near the surface are slightly warmer than the observations as well. Now you'll note that the precipitation type at this time is all rain. However, one, Albany is the only place we have observed soundings for in eastern New York. And two, I feel that this is well representative of the environment at most locations in the mid and upper Hudson Valley where this freezing rain precipitation type error occurred. Going forward 3 hours at 15Z, you can see that precipitation has picked up a little bit at this point. The observations have cooled. The models is sticking out quite much warmer than the observations here. Again, with the warm nose aloft, and you can also see that the wind direction at the surface in particular, and just above the surface, is northerly in the observations as compared to southerly and strong southerly at that in the models. Then another 3 hours later, now the winds have flipped more northerly in the models at this point, but it's still consistently warmer than the observations at this point, with the rain just changing to snow at this time at the Albany airport. So looking at some of the take-home points from this, so warp winds at the surface, like we just saw, were stronger and more southerly during the event. The MYJ run was slightly weaker with the winds and also slightly cooler. However, it was still warm biased. And then we have stronger southerly winds aloft that potentially led to enhanced warm air advection aloft as compared to the observations as well. And then those observed low-level north winds that we saw at 15Z potentially suggest some level of Hudson Valley terrain influence, considering the models produce a consistent southerly wind in the valley. The winds over the higher terrain observed have more of an east, even a southeast component. And the warm bias in the valley, as we just saw, is significant, especially in that rain versus freezing rain precipitation type error, where the observations were below freezing and the models were above freezing. And not shown, but also the New York State Mesonet LiDAR observations from both Albany and Red Hook suggest these channeled winds northerly observed versus southerly modeled as well. So wrapping up, as shown, suite-wide warm bias, mostly in phases 2 and 3. And then, of course, the rain versus freezing rain precipitation type error that resulted. This warm bias is likely caused by WRF producing, in particular, errors in synoptic forcing, such as the excess warm air advection aloft, boundary layer mixing parameters, causing warming to mix down to the surface, and then weaker terrain channeling as well. And then the MYJ cooler than the rest of the suite, but again, still warm biased. And none of these factors have been directly attributed to causing the warm bias. However, it may just be most of these factors combining to create a significant warm bias. And for future work, like I was just saying, questions yet to be answered, what factors contribute most or least? And is there something else at work that I have not looked at? And I also plan to do more initial and boundary condition testing using GFS output to investigate more uncertainty in synoptic scale conditions, as well as stochastic parameter perturbations to investigate more local influences that occur within physics schemes. And then I also want to look at other events that have different precipitation type errors and look for similar uncertainties as to what I'm seeing here. And with that, I may have gone just a little bit over time here, but I will take a question or two.
All right, thanks, Matthew. Yeah, we have probably have time for one quick question. If anybody has one, you can do the raise the hand or send us a quick chat. Let's see. All right, I guess no questions. Doesn't look like any. Well, anyway, if anybody can think of something, you can always send you an email. See, your email address is there. So thanks a lot. That was really good.
Yeah, thank you.
All right, so we're going to go to the next talk here in this session. We're going to have Brennan from the University of Albany, and he's going to be talking about modeling convective mode changes in complex terrain in the Northeast US. So let me just unmute you, Brennan. All right, so you should be able to unmute yourself now, and I will give you control.
Yes, hello.
Yes, we can hear you.
Okay, are you able to hear me?
Yes, yep, and we can see your screen. Just go into a present mode, and you should be all set.
Okay. Hello, everybody. My name is Bren Stetzer. I'm a second-year grad student at the University of Albany, and today I'm going to be presenting a portion of my C-STAR research, which is similar to Matt's research in that it's about complex terrain in the Northeast US, but we're going to be looking at warm season phenomena, specifically looking at changes in convective mode. I just wanted to acknowledge my advisors, Brian Tang and Rob Favell, as well as my NWS focal points, Tom Wasula from the Albany WFO and Joe Delacarpini from the Boston WFO. So the motivation for this project largely came from August of 2019, which was an unusually active period of severe weather for the Northeast. During this month, we had 11 days in which there were either reports of tornadoes, hail, or damaging winds. And if we look at the entire state of New York, there were 263 reports in August compared to a climatological value of 76 reports. These severe weather days often had pretty weak synoptic forcing, low vertical wind shear, and moderate to high CAPE. And if we look back at Matt Vaughn's C-STAR research from 2017, on the left here we have a phase space of 1,000 to 500 hectopascal shear and CAPE. And so Matt Vaughn found that these low shear, high CAPE environments often had the lowest predictive skill for severe weather in the Northeast. And so that's in the bottom right-hand quadrant of this phase space. And so while I was analyzing these cases from August 2019, I noted that often the convective mode changed from discrete cells to multicellular or quasi-linear convection as the storms came down off of the Catskills into the Hudson Valley. And these days often had weak synoptic forcing. Some of the cells that I analyzed had quasi-stationary or back-building behavior once reaching the Hudson Valley, and this increases the risk of heavy precipitation and flooding. And when I talked to forecasters from the Albany WFO, they commented that forecasting convective mode changes, and specifically looking at when and where the changes in convective mode will occur, is a significant forecasting challenge. So I wanted to just go straight into a case study from one of these days from 2019. And so we're going to look at August 21st, 2019. And so I was going to start out with a radar loop from this day, but I just wanted to introduce the domain first. And so on the left-hand panel here is going to be the radar loop domain that you'll see. And in the shaded gray is topography. And so we can see the Mohawk Valley running across New York State, and then Hudson Valley running up the eastern half of New York State. And so once I play this radar loop, what we're going to see is that there will be a line of discrete convection that will move eastward across the Mohawk Valley and the Catskills. Once it reaches the Hudson Valley, there will be new cells that will begin to initiate on the southern side of existing convection. And this line will propagate south down the Hudson Valley. And this coincides with a change in mode from discrete to quasi-linear convection. So if I play the loop here, you can see that right now with this convection over the Mohawk Valley, and right about now as it reaches the Hudson Valley, we see some back building occurring. And so if I zoom in and make this loop a little bit slower, now we've kind of zoomed in on Albany and the upper Hudson Valley. And so you can see at this time is where we start to get this back building behavior with that convection in the north. And then the convection farther south in the Hudson Valley catches up to it. the whole thing becomes quasi-linear and it moves out of the Hudson Valley. And so I will let this loop play through one more time so we can all get a good image of it. And you can see that backbuilding occurring at this time. And again, the whole thing becomes quasi-linear and moves out of the Hudson Valley. And so in terms of the SPC outlook on this day, the SPC had given a slight risk warning for Eastern New York and New England. And so if we look at the reports on this day, on the right-hand side here, these blue dots are damaging wind reports, the green are damaging hail, and then the red are tornadoes. And so if we look at when these reports happen chronologically, we can find that there's kind of this branching pattern that happens. And so we start out with these reports to the northwest, kind of between Saratoga and Utica. They move into the Hudson Valley, and then it kind of branches with some cells going off to the east, eventually creating that tornado in Vermont, and other convection moving south down the Hudson Valley, past Albany and almost to Kingston, before moving out of the Hudson Valley to the east. And then these damaging wind reports farther to the south are in connection with that second wave of convection that we saw a little bit later in the loop. So in terms of the synoptic conditions for this day, we had fairly weak synoptic forcing. And so on the left, we have 300 millibar heights and isotachs, and on the right is 500 millibar vorticity. And so we can see on the 300 millibar map, the strongest forcing related to that jet streak was far off to the northwest here. Kind of the closest forcing to Albany is in the Aquare word exit region, which is actually going to be forcing for convergence and downward vertical motion. And really the strongest forcing that would contribute to this convection is seen at 500 millibars, where we have this weak shortwave trough that came through. And so maybe a little bit of cyclonic vorticity advection to help force some ascent. If we look closer to the ground, we can see that there was a weak low over the Great Lakes with a warm front that stretched across northern New York. We had pretty high values of surface pressure in the warm sector of this cyclone, getting up to around 1,012 millibars. And we can see that there's onshore flow evecting moisture into eastern New York and New England around this time. So if we look at the CAPE and shear values on this day, these CAPE and shear values are from the HER 0-hour analysis at 18Z on this day. And so we can see on the left-hand panel that there's locally high values of CAPE in the Hudson Valley, around 2,500 joules per kilogram. And if we look at the shear values, we can see that there is around 15 to 20 meters per second of shear, with the direction of the shear vector pointing to the northeast. And so this puts us in the poorly forecasted quadrant of that shear CAPE phase space that I showed in the motivation. So this next plot is from the New York State Mesonet 5-minute snapshot. And I have zoomed in here on the Hudson Valley in this box on the right. So I'm outlining the Albany County right now, and then the Hudson Valley goes down to the south. And so if we first look at the values of surface pressure as recorded by the Mesonet, we can see that there's a significant pressure difference between the southern Hudson Valley and the northern Hudson Valley. Or to the south, the surface pressure was up around 1,012 hectopascals, and in the northern Hudson Valley, the pressure was around 1,010.5 hectopascals. And so this difference of just 1.5 hectopascals is enough to create terrain channeling in the Hudson Valley. And so we can see that with these blue numbers showing the wind speed. We have locally high values of wind speed within the Hudson Valley. And it doesn't show the direction, but I will tell you that the direction in the Hudson Valley is all southerly winds at this time. And then we can also see that there are locally high dew points within the Hudson Valley, with these dew points getting up near 74 and 75 degrees, as opposed to the high 60s and low 70s that we see to the west. And if we look at the Albany LiDAR on this day, this plot has the wind direction and magnitude in the barbs, and then the shaded fill is for vertical wind speed, with red being upward vertical motion and blue being downward vertical motion. And so we can see from 18 UTC to around 2020 UTC, we have southerly winds at the surface and not much strong vertical motion. And then right at 2020 UTC, you can see that there's a very strong burst of upward vertical motion, and then the wind turns northerly after that, and that shows the cold pool from this convection passing over Albany. And so I did a WRF simulation of this case, and so I used WRF 4.03 with HER-like physics. I used a triple nested domain with 9, 3, and 1 kilometers in the smallest domain. And I initialized this simulation at 6 UTC using HER analyses. For these next couple of plots, I'm going to be showing these 3 panels. On the left is max reflectivity. On the center panel, the max reflectivity is in those red fill, and then the contour is equivalent potential temperature at 150 meters. And on the right, the fill is still max reflectivity, and the contours are vertical motion at 1250 meters. The green is going to be upward vertical motion, and any purple colors is downward vertical motion. And then the last thing I wanted to point out is this black contour that you can see on all 3 of the plots, and that is roughly outlining the Hudson Valley. That contour is at 225 meter topography elevation. And so we can see at this time at 1920 UTC, in the simulation, we have these discrete cells over the upper Hudson Valley and the Catskills. We move forward to 1940 UTC, we can see this convection starts to intensify in the upper Hudson Valley and eventually starts to form this coherent cold pool. And we can see a gust front starting to form on the eastern edge of the convection. Right now, the gust front is orientated from southwest to northeast, and we can see that the strongest upward vertical motion is starting to occur on the southern edge of this cold pool. If we move forward to 2020 UTC, at this point, the cold pool has started to change its orientation, and so we can see that with the equivalent potential temperature, where now the gust front associated with this cold pool has orientated itself across the Hudson Valley from west to east. And so as this happens, new cells start to initiate on the western edge of this gust front. And so we can see that with the vertical motion, where we have this strongest vertical motion on the southwestern side. And then as we move forward there, these cells are going to be trained to the northeast, parallel to the line of convection. And so at this time, the convection starts to meet up with other thunderstorms to the south and will eventually just move out of the Hudson Valley. And so if we look at some cross sections from this case, on the left, the fill is potential temperature and the contours are vertical motion, with the solid contours being upward vertical motion. And on the right, the fill is horizontal vapor flux and the contours are meridional wind. Both of these cross sections are from south to north within the Hudson Valley, with south being on the left-hand side of the plot and north on the right. So we can see at 20 UTC, at this time, the cold pool is still fairly weak, but we do have some vertical motion on the southern side of the cold pool. And if we look at the horizontal vapor flux, we can see that the vapor flux is maximized between 500 and 1500 meters and coincides pretty well with the strongest meridional wind. If we jump forward to 2050 UTC, once the the cold pool has gotten a little bit stronger now, and so we can see that there's more vigorous motion right on the southern side of the cold pool. And this has also coincided with a increase in the vapor flux just ahead of the cold pool. And there's good agreement between the largest values of horizontal vapor flux and the largest values of meridional wind. And then by this time, once it starts meeting up with that southern convection, we can see that the convection has been cut off from those southerly winds associated with the terrain channeling, and so the vapor flux is decreased, and the gust front has become less defined. And so if we look at the storm totals from this case, on the left here is the simulated total reflectivity from that simulation that I had just shown. And then on the right is the observed total precipitation. And so you can see on both of these plots that there are swaths of increased reflectivity and precipitation that run parallel to the multicellular convection. And this was due to these new cells that were initiated being trained along the line of convection by the 0 to 6 kilometer shear vector. And so to summarize what I found from this case study, I found that discrete convection descended into the Hudson Valley and began intensifying and forming cold pool. The channeled flow up the Hudson Valley that was created by that terrain channeling was able to increase the low-level moisture flux just upstream of the cold pool. This caused new cells to initiate when high theta E air was lifted over the gust front, and the cells were trained along the squall line by 0 to 6 kilometer shear vector, which reinforced the cold pool with evaporatively cooled air. This allowed the squall line to produce localized maxima of precipitation, with those maxima being around 40 millimeters or 1.8 inches of rain in Saratoga County. And so moving on to what my current and future work will be for this project, I still have some questions that I would like to answer. I would like to know what combination of environmental characteristics are conducive to this type of convective behavior, and if there are some threshold values that forecasters could use in order to forecast this type of convective evolution. And so to that end, I've been compiling area averages of surface variables from the HRRR analyses within the Hudson Valley. I've started by using the month of August from 2016 through 2020, and I've been making maps of severe weather indices using these HRRR analyses to gain some context. And so this map is an example of one of those plots. And so in the fill is the surface-based cape. The vector is the 0 to 6 kilometer shear vector, and then the contour is MSLP. And so we can see on this day, which is the case study that I showed, we can see that the localized cape in the Hudson Valley is higher, and that also is the same area where we have the strongest shear, and the MSLP difference was able to create that terrain channeling that increased that vapor flux. And so that is all I have prepared for today, so I can take any questions if anybody has them.
All right. Well, thank you, Brennan. Does anybody have any questions? Oh, I think we do have one here. Let's see. And the question is, was your WRF configuration one-way nested or two-way nested? And if one-way nested, did you compare the 3 and 1 kilometer forecast for this event?
So it was two-way nested, and I did some WRF simulations where I did not have that 1 kilometer nesting and just using the 3 kilometer nested, since that's the resolution that operational forecasters are able to look at. And I did have some success in simulating a squall line that had this back building behavior, but I wasn't able to pick out those mesoscale features within the Hudson Valley as well with that 3 kilometer simulation.
All right, thank you. Any other questions? Okay. All right. Well, thanks, Brandon. We're gonna go on to our next talk, which is from Craig Schwartz, who I didn't mention. He was the one that did ask that question, but Craig is now gonna present here for us. So let me get him unmuted and give him a control. And so Craig comes to us from,
can you guys hear me?
yes, we can hear you.
Cool.
So Craig's from NCAR, and he's going to be talking about the precipitation forecast sensitivity to horizontal grid spacing and convection allowing models over the East Central United States.
All right, thank you. So yeah, I was the one who asked that previous question. Kind of dovetails with my talk here. I'm assuming you can see my screen, and if you can't, just someone yell at me. So this is a very different talk from the last two. This is a statistical analysis looking at a large number of cases. And the idea is to compare 3 and 1 kilometer forecasts over the central to eastern United States and to focus on precipitation in this particular talk. I know this is a conference about the Northeast, and I will talk about some region-specific behavior, but I'm also going to focus on model performance to the east of the Rockies. So the motivation for this talk is really just some ambiguity that persisted in the literature about resolution requirements over the central to eastern United States for next day forecasts, so in the 18 to 36 hour range, somewhere in there. And there were several studies done, 5 to 10 years ago that suggested that 4 kilometer forecasts were comparable to 1 and 2 kilometer forecasts in terms of precipitation forecast skill. But a few studies since then suggested some improvements from 1 kilometer grid spacing, and it was unclear why there were these disparities. So one thing we thought about is, could relatively small sample sizes have anything to do with these differences? And I think that was a fair question because a lot of these studies only had 20 to 40 cases. So to try to reconcile some of these differences, we ran 497 corresponding 3 and 1 kilometer forecasts over the entire conterminous United States. So these were all 36-hour forecasts initialized at 0 UTC each day from GFS initial conditions, and I also used GFS boundary conditions. And yeah, this 1 kilometer domain was really big and really expensive. It was almost 5,000 by 3,000 grid points. So the question is by using a lot of computing power, do we actually get forecast benefits compared to 3 kilometer forecasts systematically over a large number of cases? So we use the WRF model with 40 vertical levels, 50 millibar top. I'm not going to go through the physics, but basically it was the same as the legacy real-time NCAR ensemble that I think a lot of you are familiar with, that we ran in real time between 2015 to 2017. So we know how that behaves pretty well. And the important thing is that the 3 and 1 kilometer forecasts really were identical, except for the horizontal grid spacing and as well as the time step. So this experimental design really isolates forecast differences to the differences in the grid spacing. So to choose the cases, we consulted the Storm Prediction Center's Severe Weather Event Archive, and the SPC includes events in there based on many different criteria. And if there was an event in the archive between March 15th and July 15th, between 2011 to 2016, then we simulated it and produced 3 and 1 kilometer forecasts for those events. For the cool season, we were a bit more selective, and we tended to focus on events with more storm reports that looked like this. And even though there were events that looked like this in the SPC database, we did not simulate these. So overall, we have 497 forecasts, 279 were in the spring, which we called March 15th to June 14th, 140 were in what we call the summer, which is June 15th to July 15th, and then we had 78 in the cool season. I'm going to focus again on 1 hour cumulative precipitation forecasts from these next day 18 to 36 hour forecasts. This avoids a spin up from relatively coarse initial conditions. We'll verify compared to stage 4 observations. And I'm just going to show metrics from the fraction skill score. For those of you unfamiliar with the fraction skill score, the important thing to note is that higher values are better, and it also uses a neighborhood approach. And the idea of a neighborhood approach is to relax the requirement that forecast and observed events must match at individual grid points for the forecast to be considered perfect. And we do that by defining a neighborhood length scale, which I'm calling R. And basically, as you make R bigger and bigger, you're basically saying it's okay for the model to be incorrect over larger and larger scales, but still get counted for having a good forecast for being a little bit incorrect. For these initial stats, I'm just going to show fraction skill scores aggregated over this region, so the entire CONUS to the east of the Rockies. I do want to state that the terrain here is relatively flat. It's less flat over the Northeast, but these results really are looking at relatively flat terrain, and if we were in areas of really steep, complex topography, like to the west of the Rockies, these results could differ quite a bit. All right, so on to results. These are aggregate fraction skill scores for the springtime. So the fraction skill score is on the y-axis, and we have forecast time on the x-axis. Note that the forecast hour starts here at hour 19. We're looking at basically hours 18 to 36. And the fraction skill scores are for 3 different neighborhood length scales. The different colors are for different event thresholds. So 1 millimeter hour, 5, 10, 20, and 40 millimeter per hour thresholds. The dashed lines are for the 3 kilometer forecasts, and the solid curves are for the 1 kilometer forecasts. And the circles are indications of statistical significance. And the circles are placed on the line that has a significantly higher fraction skill score at the 95th percentile. And so an easy way to kind of just interpret these figures is just to count numbers of circles, basically. So a few things to note. As our neighborhood length scale gets bigger and bigger, fraction skill scores generally increase, and this is expected because as the neighborhood length scale gets bigger and bigger, you're basically saying it's okay to be wrong over a bigger and bigger area. And then as we increase our precipitation thresholds, the fraction skill scores decrease. And that's because it is more difficult to predict highly localized events, like 40 millimeter per hour precipitation, than broader, more widespread events. And again, higher values of the fraction skill score are preferable. So it's a pretty clear signal about what's going on in spring at all of these different neighborhood length scales. These solid curves for the 1 kilometer forecasts are above the dashed curves, which represent the 3 kilometer forecasts, basically for all the thresholds and for all the different neighborhood length scales. And moreover, these differences are statistically significant at the 95th percentile, as evidenced by lots of these circles that are on these solid lines. So in spring, it's pretty clear. Over the entire CONUS east of the Rockies, there are benefits to using 1 kilometer horizontal grid spacing. Now we'll turn to the cool season. And results over the cool season are very similar to the spring before hour 30. So if you look to the left of hour 30, again, we see the solid curves are above the dash curve and lots of circles on our solid curves, again, indicating benefits of 1 kilometer forecasts compared to 3 kilometer forecasts. But after hour 30, things change and we see far fewer circles. And when there are some circles, they're on the dashed line, indicating that the 3 kilometer forecast is sometimes significantly better. But the overall signal is that after 30 hours, there just aren't meaningful differences between the 3 and 1 kilometer forecasts. I don't think this is anything to get super excited about. We're in the cool season. Hour 30 is around 6 UTC. So we're well after dark. We've lost instability, lost CAPE, especially over southern areas of the CONUS. And in short, there's just not as much interesting weather going on. And toward the end of the talk, I'll show how CAPE is at least associated with some differences between forecast skill. So overall, between spring and the cool season, there's a pretty clear indication that 1 kilometer grid spacing is preferable. But when we go into summer, we get a different story. Just take a quick glance and you'll see there are far fewer circles, especially once we get down to the 5 millimeter per hour threshold and higher. And when there are some statistically significant differences, they are on these dash curves, indicating that the 3 kilometer forecasts were significantly better than the 1 kilometer forecasts. At the lightest threshold at 1 millimeter per hour, we still did have some indications that the 1 kilometer forecasts were better than the 3 kilometer forecasts. But compared to spring and the cool season, these differences weren't as big and not statistically significant nearly as often. And it's really hard pressed to find systematic benefits of using 1 kilometer grid spacing during the summer. So this was an interesting result. So what can explain some of these differences between the cool season in spring, where 1 kilometer forecasts were better, compared to the summer, where 3 kilometer forecasts were, say on average, just as good as 1 kilometer forecasts? Well, one thing that kind of showed up nicely was an association of forecast similarity and what's called the convective adjustment timescale. So the convective adjustment timescale, denoted as tau, is just the CAPE divided by 1 hour accumulated precipitation. So just assume we have a given amount of CAPE. And now let's assume that we have strong forcing. So if there's strong forcing, we're going to remove the CAPE and we're going to rain a lot. So the denominator is relatively big, and so this fraction is relatively small. So when we have strong forcing, our timescale is small. Conversely, for that same amount of CAPE, let's say that we have relatively weak forcing. In this case, we don't rain very much. Our denominator is small, and so our fraction is relatively big. So a bigger value of this timescale means weaker forcing. And this timescale here is what's plotted on the x-axis. So during the cool season, these orange dots, we see that we have relatively small timescales, which corresponds to relatively strong forcing. And then in summer, these black dots, we have relatively large values of the timescale, indicating relatively weak forcing. So this doesn't tell us anything we don't already know. We know that during the summer, over the CONUS, we have relatively weak forcing, and that during the cool season, we have relatively strong forcing. Nonetheless, I think it's pretty cool that this metric is able to pick this up. And what's even more interesting is how this metric correlates with what I'm calling forecast similarity on the y-axis. Technically, it's just the fraction skill score comparing the 3 and 1 kilometer forecasts directly to each other. And in this case, a higher value means that 3 and 1 kilometer forecasts look more like each other. So during the cool season, when we have relatively small timescales, which means relatively strong forcing, the 3 and 1 kilometer forecasts look a lot like each other, given their high values on the y-axis. And during the summer, when the timescale is relatively big, meaning we have relatively weak forcing, we have relatively low values of this forecast similarity. And then spring is basically just in the middle. So we can put everything together and put together this little cartoon. So each of these blue lines is just a generic measure of distance, one each for the summer, spring, and the cool season. So during the summer, we have relatively weak forcing, and during the cool season, relatively strong. And though I didn't show it, storm size is relatively small in the summer and relatively large in the cool season. So we've got larger features driven by the stronger forcing in the cool season. So if we look at the summertime, the 1 kilometer forecast and the 3 kilometer forecast looked least like each other. So there's a lot of distance between them. But there was not a clear benefit of 1 kilometer forecasts over 3 kilometer forecasts in the summer. So they're both roughly equidistant from the observations. And then the 1 kilometer forecast and 3 kilometer forecasts are relatively far from the observations because the fraction skill scores were lowest in the summertime. We go to the cool season. During the cool season, when we had relatively strong forcing, the 1 and 3 kilometer forecasts looked more like each other, but there was a clear benefit to 1 kilometer grid spacing over 3 kilometer grid spacing. And fraction skill scores were relatively high in the cool season, so the 1 and 3 kilometer forecasts are closer to the observations. And then spring is in between the cool season and the summer, where there was a clear benefit of 1 kilometer grid spacing compared to 3 kilometer grid spacing, but more distance between the two forecasts than in the cool season and less than in summer. So if these results about summertime seem counterintuitive, well, I don't think you'd be alone. Initially, I thought they were also, because intuitively we'd think, okay, the forcing is weak in the summertime. Maybe this is when higher resolution is going to be helpful. So we'll be resolving these smaller scale processes. Well, the reason why I don't think we see improvements this summer is because by 18 hours into a high resolution forecast over the US, predictability is essentially lost on scales less than 200 kilometers. And so if something is unpredictable, finer grid spacing is not going to help you. So I think there's some further evidence of this by computing fraction skill scores of the 3 and 1 kilometer forecast as a function of storm size. And so the x-axis is basically just an object size. And so what we see is that as the storms get progressively bigger as you move to the right on the x-axis. The benefit of the 1 kilometer forecast compared to the 3 kilometer forecast is relatively larger than at smaller storm sizes. And what this is just suggesting is that these bigger features are really what is driving improvement of the 1 kilometer forecast compared to 3 kilometer forecasts over the springtime. So these are your large MCS type features, these bigger, more predictable features where it seems that the 1 kilometer grid spacing is most beneficial. All right, I promised some regional verification. So in addition to all these statistics aggregated over the CONUS east of the Rockies, I used the NSEP precipitation verification regions and did verification separately in all 8 of these regions. So here are for the 4 southernmost regions: Southern Plains, Gulf of Mexico coast, Lower Mississippi Valley, and the Southeast coast. Again, look at circles. We see a lot of circles on solid lines, indicating that over these southern regions, the 1 kilometer forecasts tended to be better than the 3 kilometer forecasts. Now, if we look at the northern regions, including the Northeast coast, we see far fewer circles, both over the Northeast coast region and over the Appalachians, indicating fewer benefits of 1 kilometer forecasts over these northern regions. So there's some interesting regional results. And what explains it? Well, it's hard to say, causally what's doing it. But there did appear to be some modest correlation between instability and benefits of 1 kilometer grid spacing over the springtime forecasts. So the x-axis here is a domain averaged CAPE over each of the individual regions, and the y-axis is the difference between the 1 and 3 kilometer fraction skill scores. Because it's spring, 1 kilometer forecasts were better, so all of the values are positive. And if we just circle these 4 southern regions, Southern Plains, Gulf of Mexico coast, Lower Mississippi Valley, and Southeast coast, these have relatively more CAPE, which makes sense, but they also tended to have relatively high differences between the 1 and 3 kilometer forecasts. So there did appear to be some correlation between CAPE and benefits of 1 kilometer forecasts, and the short answer is where there's more instability and more potential for convection, that was where the 1 kilometer forecasts tended to have the greatest benefit. Finally, I just want to show some bias characteristics for the Northeast coast and Appalachian regions. Forecast hour is on the x-axis, and the y-axis is basically the proportion of the verification region with precipitation exceeding 1, 5, 10, and 20 millimeters per hour. And I'll draw your attention to these heavier rainfall rates. So the observations are shown in black. We see a clear diurnal cycle during the spring, and the models do a fine job capturing the diurnal cycle. But the 3 kilometer forecasts really overpredict the peak. 1 kilometer forecasts still overpredict, but not as much. And looking at different regions, including the Southeast coast, we see similar behavior. When you go further west and look in the plains, bias characteristics vary very much. So it's not enough to just look at bias over, just say, the CONUS east of the Rockies. You really do have to look region by region to see how these biases vary. So all of those details are presented in the paper in Monthly Weather Review that was published late last year. And at about 18 minutes, so I guess I'll just stop here and leave this up and take any questions. Thanks.
All right, thank you, Craig. I think we do have a question. Let me see. Let's see here. Yes, so it's from Justin Minder. Let me just maximize it here so I can read it. Okay, so Justin asked, have you considered using similar approaches to look at resolution-dependent model scale for mesoscale winter precipitation, such as snow bands?
The short answer is not specifically, no. I mean, we do have some of those. Well, I have to check our climatology. Oftentimes, at least sometimes when there was severe weather, say further south, there was snow in the Northeast. So we might have some events in our database that do have these winter type events. So Justin, if you're interested, send me an email and I can look through the data set, and we're happy to make the data available to folks who want to use it.
Any other questions for Craig? Yep, one from Massey here. Massey asked, he said, nice work. Do you think your results are sensitive to the choice of stage 4 for your observed precipitation data set?
Good question. My answer is no, not based on this work, but some other work that I've done over periods where I had, say, the MRMS data set for like a direct comparison. So I guess in short, when I verified against MRMS and stage 4 over a shorter time period, I didn't see meaningful differences in terms of the overall conclusions. It's a good question. It's something I'm looking into further, but as of now, no, I don't think it is.
All right, great. Well, thanks again, Craig. And we'll move on to our next talk here. We're going into session C, which are some of the C-STAR updates. And our first one will be from Brian Colley from Stony Brook. So Brian, let me just unmute you and give you control.
Hello, can you hear me?
Yes, we can hear you, Brian.
Can you hear me? Hello?
Yes.
Okay.
We can hear you.
I just want to make sure.
No problem.
The most nerve-wracking part of the talk is knowing if the technology is going to work here.
Yes. The worst part would be to give the whole talk and realize nobody heard or saw anything.
Yeah, I had a lecture in which I had 15 minutes where I didn't realize the students didn't hear me, so that was fun. Anyhow, can you see my full screen right now?
We cannot yet. It's still the white background.
Okay, let me. Can you? Can you try to share again? Just to.
Sure.
I may have missed the button. I'm sorry.
That's okay. Let's see.
So I'm not seeing anything come up on my screen right now.
Let me just change it back, and I'll go back to you. Okay, it should pop up for you.
Just looking behind my windows here, not seeing anything pop up. My Mac. So is there a special window that comes up? I'm sorry.
It's usually like a little dialog box, and it asks if if you're ready to show your screen. And you just hit OK.
Yeah, I'm not seeing a dialog box. Unfortunately, this could be not good. Yeah, I see I don't even have the little widget anymore of the little GoToMeeting. Is that where it's attached to?
It should just come up as like a separate box on the middle of the screen usually. Do you have more than one monitor? I know some of the issues that some people have had when there's two screens or something.
No, but I tell you what, I may just go out real quickly and back in. It just takes like 10 seconds.
Sure. Yeah, let's try that.
Because I just worry that maybe that's an issue. Let me just quickly quit this GoToMeeting.
Sure. All right, so we'll just wait for Dr. Colley to come back. This is some of the issues with the virtual conference, but we'll just have to try to work through these problems. We're dealing with everybody's computer at once, so it's we're trying to make sure we can count for all these different setups that people have. All right, let's see. So Brian just logged back in, so let me unmute him. And I'll send him the request here. Okay, Brian, we can see your screen. We just have you, you just have to unmute and then you should be good.
Can you hear me?
Yes, yes, we can.
Okay, wow, jeez. Sorry about that, folks. I knew something like that would happen. Can you see the full screen now?
Yes, we see your full screen.
Okay.
Great.
Okay, so let me minimize that. Can you still see full screen?
Yeah, well, it's just, it's he went out now, so it's, there it is, yeah.
Okay, yeah. Okay, sorry. Anyhow, let's get going, get my brain back into this. So today, yeah, I'm going to provide a C-STAR update. Our C-STAR here, the most recent one, has been focused on developing tools for ensemble output. And then more recently, we've been focusing on some of the communication issues attached to this ensemble data. And I'd like to acknowledge my co-authors here. Benjamin Keel is a C-STAR student currently working on the project. Special thanks to Rose and Ken Johnson, who you all know at Eastern Region, who really helped with the workshops, especially providing some additional resources for forecasters to attend these workshops, which I'll describe a little later. And then the team from Alda Center, which helped with the workshops that I'll talk about a little later. So yeah, we all know some of the issues given the audience here with ensemble tools or lack thereof to look at the growing number of ensemble data. It's getting a little bit better, but more tools are necessary to distill the forecasts and the possible scenarios and the probabilities. And this is all in the framework of limited time, right, to analyze all that data. So there's a lot of motivation from that side. And then also, we all know the predictability challenges. We all have our favorite case or two that in the recent past that may have caused issues. This is just one example. And this motivates the communication issues attached to these forecasts. You know, how best to interact with the stakeholders and what sort of graphics and tools to use for that. So our motivation C-STAR, we spent a lot of years, and I've given many presentations highlighting some of the tools and graphics that we've generated to try to distill some ensemble data. And that helps possibly with different scenario, distilling the data in terms of different scenarios or thresholds. I'll review a little bit of that here today, but given the emphasis of NWS for IDSS recently, there's a growing need for communication, as we all know. And so we did have a couple workshops that I wanted to highlight that discuss some of these questions, such as can an improvisational approach, which is the Alan Alda approach, help forecasters better communicate and engage stakeholders. So I'll discuss that. The basic outline, I'm going to provide a brief review of the fuzzy clustering that we do here at Stony Brook. I've done this before, but I think I wanted to do this because the clustering now is not only run here at Stony Brook, it's also run at WPC operationally, and I'll share that webpage. And then furthermore, we've teamed up with MDL to get the clustering merged in with the national blend of models. We're currently in a testing phase with that, so I want to describe that for a little bit. And then on the side, the C-STAR student is comparing the different clustering approaches. There's other approaches out there besides fuzzy clustering that may be of interest. And then ending with some communication workshops that we had involving about 15 forecasters. Okay, so just a brief background on the clustering, just to get everyone a little up to speed with this. We've been doing this for several years now, using the global ensembles of the GEFs, the Canadian ECMWF, and with the recent expansion of GEFs, we're up to 100 members now, using several variables in question here. The actual method or clustering is basically the way we run it at Stony Brook, at least, is using mean sea level pressure. And the idea, and I'll show you an example in a second, is we all know the ensemble spread and what that looks like, but the question is, can we break that spread up into two leading patterns, what we call principal components, that explain most of the variance attached to that spread pattern for a given forecast over a domain of interest. And so we use an EOF approach to do that. I'm not going to go into the gory details of that, but it's an efficient way of using all the members to get those two patterns. And once we have those two principal components, we're going to simply map on all the ensemble members onto those two principal components, and then use a fuzzy clustering approach to come up with our 4 or 5 different clusters. And once we have those clusters, then we can plot any variable of interest attached to that domain of interest. So just as a quick example, here's a case from several years ago, but we're all familiar with the mean and spread on the right-hand side here of what that looks like here for East Coast winter storm. And so the question is, the spread pattern is fairly complex. It looks to be shifted a little bit left or east or west, I should say, of the ensemble mean here for this 3-day forecast. And so what the EOF approach does is simply break up that spread pattern into the two leading dominant modes, or the principal components. And that's what's shown here, where EOF1 explains 42% of the variance, and EOF2 explains 25% of the variance. And so now we have a way to kind of separate out the two issues here with this forecast. The left one is that there seems to be a lot of members here that are somewhat either deeper or weaker shifted to the west of our ensemble mean location. A positive PC1 would be a deeper cyclone to the west. A negative principal component 1 would be a weaker cyclone to the west. And then EOF2 is a dipole pattern. So that suggests a displacement error relative to the ensemble mean, whether the cyclone's either to the northeast with a positive PC2 or to the southwest for a negative PC2. And so once we have these two principal components, we can map all the members onto this phase space of PC1 and PC2. And this is just a sample diagram here where the different ensemble systems are color-coded, and then the symbols represent the different clusters here. And there's 5 clusters. The middle cluster is actually the ensemble mean cluster, with the black dot being the ensemble mean of all 90 members in this example. And then we have the other clusters here. And you can see how the fuzzy clustering is simply trying to determine the minimum distance between members here, such that we can have 4 or 5 clusters in this phase space. And so you can see how it's kind of equally spread out among this domain. So once we have these clusters, then we can plot up all the variables of interest, whether it's precipitation or 500 millibar height, and given these sea level pressure clusters. To show you an actual example, this is a good chance to highlight what Bill Lambertson's done at WPC. If you're not familiar with this, he did put together a nice cluster page using our approach. The only difference is that he's clustering 500 millibars instead of sea level pressure. But he has 2 web pages, one day 3 through 7, where you can pull down, select what day you want, and there's another page for days 8 through 10. And the links are here at the top with the 100 members basically, and he's doing that EOF for principal component analysis over all of CONUS. So it's a fairly large domain which has some strengths and limitations, but it does provide an efficient way of looking at the full CONUS domain. So I just pulled up one example here of day 7 forecast from late last week, valid here later Thursday night. With our digging trough on the west coast, and then some ridging possibly on the east coast, and you can see EOF1 is focusing on the amplitude of that trough out west here in the day 7 forecast with that. So there's pages where you can view the different EOF analyses, and you can see this explains about 30% of the variance. And I'm not showing you EOF2 because I just want to jump to the different clusters, and where you can pull down and select what variable you want. This is simply the 500 millibar heights. And he does 4 clusters. He doesn't have an ensemble mean cluster, but he does have the total mean of all the 100 members here at the bottom. So you can kind of see, this is what you would normally see of the mean of everything. But the top 4 clusters are simply breaking up here the different possibilities. And you can see a couple of them are associated with deeper West Coast troughs and either a higher amplitude East Coast ridge or flat zonal flow, and then vice versa with weaker troughs out west. And what's nice about it is that he tells you with these numbers at the top how many members are associated with each of these clusters. So the T is the total number or percentage of members, and then the breakdown by each of the ensemble systems here in terms of Canadian, GEFS, and ECMWF. And so you can kind of get a feeling of how the membership is weighted here in each of these clusters. And the whole idea of this, by the way, is instead of picking ensemble system 1, EC versus GEFS or Canadian versus GEFS, the idea of combining these ensemble systems to generate these clusters is a little bit more ideal. So once we have these clusters, then you can plot other variables. This is just 24-hour precipitation, where you can look at the daily precipitation for each of these clusters as well. And you see the differences on the Pacific Northwest as well as the East Coast for each of these clusters. One research question is, which is better to cluster up to get precipitation? Should we be clustering the mass field and getting the precipitation from those mass field clusters like what I'm presenting, or should we be clustering the precipitation directly to end up with those solutions? And that's a question that we're currently looking into more quantitatively on the research side. So the other issue on the research, before I get more into the applications, is which clustering approach to use. We started with this fuzzy clustering approach, but there's other approaches that are used as well out there in the literature. And so this is just an example of another cyclone in 2012, where we have the analysis mean sea level pressure on the left, the total 90-member mean on the right of the different systems. You can see the ensemble mean forecast for this 3-day forecast, but that's just one solution here, and that's motivating the clustering of, what are the different scenarios that are leading to this ensemble mean. The fuzzy clustering, which is what we've been doing, is basically you tell how many members, or I should say how many clusters you want, and then it minimizes the mean distance between members in each cluster to determine the best setup here. And so these are the 5 clusters here based on this fuzzy clustering approach. And you can see the variance here in the numbers of members in each one of these. But each one of these could be viewed as a scenario, one of which could be much snowier and more hazardous than other scenarios. But it lays out nicely the different possibilities that may need to be communicated when thinking about the outreach and stakeholder interaction. But this is one approach, and this is using the 2 principal components that I just described. We can also use the 2 principal components in this agglomerative hierarchical clustering approach, which is a mouthful. It's another one that's out there in which, just written on the lower right-hand side here, it's using the closest pair of points are clustered together, and then the mean is taken as a new point, and then the process is just iterated until you get the total number of clusters that you want. So it's a somewhat different approach. The main point of this is not to go through the different approaches in detail, but you can see now I end up with somewhat different clusters, right? And different membership numbers, depending on, given this approach to what I did before. So the bottom line is that there's some uncertainty here in the type of clustering that we're using and the solutions that we might get that need to be looked at over many events, and that's what we're doing. These are using principal components, and someone could ask, well, why not just use the magnitude and displacement of the cyclone itself in a physical space, relative to the ensemble mean, knowing that distance and magnitude, can we cluster that way? And so we're attempting that as well, where we're using the actual SLP fields to cluster, and so that's what's shown in this plot. And once again, you can see somewhat different solutions, or at least number of members attached to these different clusters. And there's even a cluster that had 1 member, which is not really a cluster, so that it was eliminated here using this particular case or approach. But so there's work on the side here as part of the C-STAR students' effort to figure out what the pros and cons of these different clustering approaches. Okay, so given all this, in my remaining time, how can we better use this clustering for effective scenario and uncertainty assessment? And so this gets into the operational approach. And so one thing we wanted to do is team up with MDL to think about how to use this clustering within the national blended models, which I'll describe here in a second. And then this also motivates the workshops, is that if we have these different clusters and scenarios, maybe there's ways to merge that with the actual communication with stakeholders and so forth. So we actually just started a JTTI project with MDL a couple months ago, and in which we're taking those clusters which are being generated at WPC, and now the next logical step is that we can create a blend for each of those clusters. And so it just means we need to pass along the cluster membership to MDL, and they're going to create a blend for each one of those different clusters. And that's what we're currently doing. We're only a couple months into the project. The bottom plots are just a couple examples, excuse me, for wind speed, just showing the different solutions here in this very large domain and so forth. So, so the future is promising in terms of looking at these clusters. Okay, so with the blend, we can do a whole bunch of variables, by the way, and they have a very high resolution grid that they can run across CONUS to do that. Okay, so the last thing is our communication workshops, and I think last year I mentioned this briefly at the NROW, but the idea is, given IDSS, there's a couple things we wanted to try, and that is we wanted to try this ALDA center approach. And so the ALDA center approach, given Alan Alda, is more of a theater-based technique or improvisational approach to message design strategies. And so there's a whole essentials of how do you do that. And then there's how do you take that knowledge and apply it to stakeholder interaction. And so we had 2 workshops in 2019 with 15 forecasters, and we greatly appreciate their participation, and hopefully some of them are on the call here. But basically this, and a lot of those forecasters participated in the same 2 workshops, so they got to build on the knowledge of what was learned and so forth. And so here's just a couple photos of some group activities and brainstorming and presentations that we gave during this during these couple workshops. So each workshop was about 1.5 days long. The first workshop focused mainly on the essentials, as we call it, and so these improvisational techniques, they really emphasize connecting with your audience. Basically, activities that you're trying to distill a particular message, be able to understand your audience at all levels, and be able to communicate very efficiently in clear, vivid, and concise ways. And so there's activities of not only communicating basic things that you know and understand, but taking a scenario and being able to distill it in 2 minutes, 1 minute, and then even down to as short as 15 seconds. And so once you go through that exercise, it makes a 2 or 3 minute briefing seem a lot easier than 15 seconds or 30 seconds. And so a lot of essentials were done in the first workshop, and then that led into the second workshop, which was more of the stakeholder interaction, where we wanted to match that message more to the audience here by basically, we actually invited stakeholders from the emergency managers, transportation, and the media on day 2, and before that we rehearsed and we went through things ourselves, and then in separate rooms the forecasters gave presentations to each of the stakeholders to get feedback on whether that message is being communicated using not only orally but with a single slide to that particular audience. And so we learned a lot, and the stakeholders were really great in terms of providing feedback into the forecasters. In fact, we got a lot of positive feedback. This is just a couple examples. One forecaster commented, catching themselves making assumptions and how partners might interpret our forecasts. We really emphasize the one-page briefing, being concise, and so some forecasters are thinking about that now when they're giving outreach. And during high recent profile weather events, really emphasizing these well-designed graphics that are brief and relevant to the particular hazard. Sometimes these slides have a lot of hazards going on at once, and a lot of the message gets lost in the details of everything there. Okay, so in summary, the clustering is continuing, but now it's at WPC, and so hopefully everyone can take advantage of that. It's also leading to an effort with the national blended models, and so hopefully in the next year we'll have some a way for you guys to check that out. Meanwhile, we're testing some other clustering approaches because there is uncertainty there. And then the 2 communication workshops, which was pre-COVID, we were all together, and we're very successful. And so you can see here, I put a few more summary points where the participants really seem to embrace these exercises and presentation sessions. And forecasters have brought some of those methods back to the forecast office as a training opportunity, and the participants have demonstrated that a clear, concise messaging have been key to enhancing that connection with the partners of the National Weather Service. And with that, I'll stop, and if there's time for any questions, I'll take questions, but I think I burnt my time with other issues.
All right, well, thanks, Brian. I guess we do want to move along on time. I know Mike Jurowitz had a quick question for you, so I'll just read what he has here. He said, great presentation. Is there an archive of past events and the clustering approach?
Yeah, quick answer to that. We have 80 or 90 cyclones that we have that my other CSAR student, Minghua Zhang, has in a paper I can let you know in 2017, 2019 that we've used. So yeah, we have an archive that we can test this clustering approach with. And that's what we're going to be doing.
All right, well, thanks a lot, Brian. And I was sorry about the technical issues, but glad you were able to get it in there.
Yeah, thank you for your patience on that. I'm sorry about that.
Oh, no problem. All right, so we're going to move along to our last talk before the lunch break, and it's going to come from Rodney Chai from the Boston office, and he's going to be giving a CSAR update about assessing warm season model QPF in New England. So I will give you control, Rodney, and you just have to unmute yourself.
Right, can everyone see my screen and hear me?
Yes, we can see and hear you.
Awesome. Okay, good afternoon, everyone. So my name is Rodney Chai. I'm a forecaster at the Boston office. And, today I'm going to talk to you about my group's CSAR project assessing warm season QPF in New England. But first and foremost, I really need to acknowledge my co-authors, Todd and Matt from the Caribou office, Justin, Chris, and Mike from the Gray, Maine office, and my colleague Bryce from the Boston office. So once again, this is a CSAR collaborative project between the Boston, Gray, Maine, and Caribou, Maine office. So the problem that we aim to tackle here is, the background is that the warm season QPF or rainfall is one of the the most challenging numerical modeling challenge in operational forecasting. And the reason is because even with all the advancements in numerical modeling, the models are notorious for they have a tendency to overestimate and overforecast the rainfall, especially in the summer convection setup. And even if you get the amount of rainfall correctly, the location is often not correct. And with the increasing urbanization of the region, getting the rainfall amount and location correctly is important because it has a lot of implications on flash flooding, and it really doesn't take a lot to get flash flood in urbanized, low-lying areas. And from a personal experience, we had a lot of fun dealing with flash flooding at the Boston office over the summer. And so the goal is really to help forecasters possibly develop a guide. So when you come in for a shift, you're dealing with the possibility of flash flooding or heavy rainfall in the region, you're able to have a reference, have a quick guide that allows you to interact with the ensemble forecasts better and make more effective and accurate decisions. So a quick rundown of our method. There are 3 components. 2 of the 3 components have been completed so far. The first component is we identify the significant observed warm season QPF events during the last 5 years, so from 2015 to 2019, across New England. And the second component, and this is still ongoing, we identify the high-res ensemble forecasts of significant warm season QPF events, and this would either through the NCAR ensemble from 2015 to 2017, and HREF ensemble from November 2017 onwards. And this is still ongoing, and I have to acknowledge Brett Roberts from SPC for his huge help. And last but not least, we identified the National Weather Service headlines for the warm season QPF events during the same period. So those would be your flash flood and flood headlines, and that is completed. As for the sources of data, for observed QPE, quantitative precip estimate, there are 2 main sources. One is the NCEP stage 4 reanalysis, and the other source is through the AHAB's Advanced Hydrologic Prediction Service website through the GIS tool. So that the URL is water.weather.gov. And as for the model QPF, as I've mentioned previously, through a combination of NCAR ensemble and SPC HREF, depending on the time period. And last but not least, for the NWS headlines, we use the Iowa State Mesonet Archive. So for observed event, once again, we identified significant observed warm season QPF events during the last 5 years. And we aim to identify areas of about 1,000 square miles or greater, because the county sizes are so different. So we use 1,000 square miles as to make the analysis more uniform. And the 3 broad thresholds are more than 1 inch, 2 inches, and 3 inches of 24-hour rainfall. And of course, we recognize there are limitations with this, especially in flash flooding events. Sometimes you get 3 inches of rain in less than an hour, but just for uniformity purposes, we use a 24-hour rainfall. And we use ArcGIS to determine the maximum and mean rainfall over New England. And as well as we try to describe the synoptic and mesoscale setup leading up to the event. And so for preliminary results for the observed events, we have about 137 observed 1-inch plus rainfall event, and that averages out to be about 25 to 30 1-inch plus events per warm season. There's about 18 2-inch plus events, and then just a couple of 3-inch plus events during the 5 years. And in the bottom left corner, you see that in New England, the max rainfall typically happens in the months of July and August. That's the peak summer season. And as for the 1-inch plus events, 2017 and 2018, New England had more rainfall than the other years. So the second component of the project is still ongoing. That's the we identified a high-res ensemble forecast that corresponded with our heavy rainfall events that we identified. And this is still ongoing, and these are huge model data sets. And once again, we have to thank Brad Roberts from SPC for his help. And last but not least, for the NWS headlines, we identified the headlines for the events. And broadly speaking, those are divided between the area flood headlines and the flash flood headlines. So as a general rule of thumb, the flash flood headlines are generally for more flashy events that, and they're more applicable for low-lying urbanized areas. When you get a training storm, you can get rapid rises in creek levels, and because of the flashy nature of it, that's when we issue the flash flood headline as opposed to the area flood headline, when you can get the more stratiform rainfall and over a long period of time, or when the creek levels are higher. So that's more applicable for during times when you don't have drought. And just a quick look at the preliminary results for the headlines. You can see that, so on the left, we have the 1-inch plus events that I showed you previously. And then on the right, those are the flash flood watches and the flash flood warnings over the 5 years separated by months. And unsurprisingly, you see in July and August, we issue the most number of headlines because that's the months that we have the most number of heavy rainfall events in New England. I just want to show you 2 case studies. The first case study, that's, we have a negatively tilted upward level trough anchored to our west, very high P-watts value, and then we have a weak surface low over Gulf of Maine. So this was a mostly stratiform rain event, so there were no flood headlines for this event. On the right-hand side, that's the observed 24-hour rainfall total, and you can see a maximum rainfall of over 1.5 inches over the White Mountains of New Hampshire going into western Maine. And this is the probability match mean 36-hour accumulated rainfall simulation for this event, and you can see that that's the maximum stretching from the Tuck Hill Plateau in New York State into northern New England. And this is the probability of rainfall exceeding 2 inches. And so again, you can see that corresponds pretty well with the expected rainfall and observed rainfall. the second case study, we were able to use the href data. And so on the top left corner, that's the observed rainfall taken from the AHAB's website. And then on the top right corner, that is a graphic that we created using ArcGIS, and it matches up pretty well with the AHAB's image that we retrieved. And on the bottom right corner, that's the headlines issued by the Burlington, Vermont office on that day. So it was a very complicated setup with a stored frontal boundary leading to training storms over parts of northern New England. And then there was a stored front in southern New England, but that was associated with much less rainfall. And this is a quick look at the href data, and you can see it matches up pretty well with the observed rainfall. And this is the ensemble mean, the ensemble maximum, and then we have the probability match mean, which takes into account the amplitude of different members. So this is slightly more advanced than the ensemble mean that I showed you earlier. And finally, this is the localized probability match mean. So the next step would be to complete the review of the ensemble forecast data, and then ultimately we want to help the forecasters make better decisions, because as an operational forecaster, it is so important to be able to look at the data set and then make decisions. And sometimes you only have a few minutes on the fly. You have to decide whether to pull the trigger on a flash flood headline, and ultimately we want to be able to lead to better forecast lead times and have better forecast confidence. And we are aiming to develop these guides and conceptual models in time for the 2021 warm season. And finally, once again, we want to thank Brad Roberts from the SPC for all the help in obtaining the href data. And with that, that's the end of the presentation. And I will take any questions.
All right, thanks, Rodney. Does anybody have any questions? All right, I guess no questions coming in here, Rodney, but great job. And I'm sure if anybody can send you an email if they can think of anything. All right, so thanks. So that'll bring us to the lunch break. We're going to be meeting back at 1:40 p.m. Eastern time for the severe weather session. And I know you're definitely not going to want to miss that. We got some really good presentations this afternoon. So if you are interested in Northeast severe weather, this is definitely going to be the session for you. And we got some great speakers. We got the Mikes and Joe Dog and a whole bunch of others. So definitely come back at 1:40 after lunch and be prepared for some great talks. So we will see you then. Hi, everyone. Welcome back. It's 1:40, and we're going to be going into our next few afternoon sessions here with Session D, Severe Weather. I'd like to bring on Christina Speciali. She's a forecaster here at the National Weather Service at Albany, and she's going to be the chair for this afternoon sessions and introducing our speakers for the next two sessions.
Thanks, Brian. First up, we have Tom Wasula from the National Weather Service office in Albany, New York, and he'll be giving a discussion called A Multi-Scale Analysis of the 29 August 2020 Tornadic Event Across Eastern New York.
Just wait. Hey, can everybody see my screen fine?
Yes, we can, Tom.
Okay, great, Brian. That's one of the battles then. Thank you, everybody, for that introduction, and thank you, Brian Frugas, for the work he's done as a leader with a VR shear study and NROW study with tornadoes in the last 5 years. And this case study is one of several events we had this warm season with tornadoes across the Albany forecast area. And this particular warm season, we had 13 tornadoes and then an additional one on October 7th, and 11 of them happened in August, and 4 separate events. Mike is going to be talking about one on August 2nd with 4 tornadoes. I'll be talking about one. We initially had 2 EF1 tornadoes on the 29th, and then I just found out in the last 5 days that a microburst was reclassified as an EF0, so we had 3 on this event, which I'm going to be focusing mainly on the 2 EF1s. And the key question is what caused the tornadoes on the 29th and what was the convective environment? And this is a subset of some of the work at C-Star 7 looking at severe weather and complex terrain. There's a couple of great talks by graduate students earlier in the morning, and improving tornado guidance and using dual pole data. The outline of my talk is basically a review of the UFO Albany tornado climatology briefly, a brief synoptic overview of the case, mesoscale analysis using the SPC mesoanalysis data, the rapid refresh data, a brief review of the WFO at Albany tornado study, VR shear and normalized rotation studies, and a storm scale analysis of the EF1 tornadic storms using GR2 analyst and VR shear tool in ALIPS. This has been gone over earlier, but basically the Albany forecast area is in complex terrain. A third of the area is over 1,500 feet in elevation. The Mohawk Valley merges with the Hudson River Valley. The focus will be on the capital region into the upper Hudson Valley with this particular case study. What was the tornado climatology at Albany? Well, basically over the last 41 years, New York averages about 10 a year. Albany typically averages 3 a season, but in this particular season, we've had a total of 13 to the end of August. 2 occurred in May, 2 EF1s. We have 6 EF0s and 5 EF1s in August. So here we are tying 2003 and 1992. But what makes this season unique is that most of these are individual events and not the same event with multiple touchdowns like July 21st, 2003. In terms of by month, Albany typically has its peak in tornadoes in the late spring and into the summer in May and July. But August, we've been rapidly catching up. Prior to the 2019 season, we had 11 tornadoes recorded in August. We had 3 in 2019, and it was touched on by Brennan earlier, and we had 11 in 2020, bringing us to 25 in August over the past 41 years. So basically, there's been this rapid catch up in August the last couple seasons. In terms of intensity, Albany, out of the 116 events from 1984, Albany's had 100 that are EF0, F0, and EF1, F1. And that accounts for 87% of the tornadoes are usually EF0 and EF1. Only 5% are EF3 or greater, so that's where the majority of our events are. It's almost an even split this year between EF0 and EF1s. On August 29th, there was a slight risk across much of Eastern New York and most of Western New England, and then it was expanded in the afternoon to include all of Western New England and a large portion of Eastern New York. In terms of the probabilities, the main threat was perceived to be the damaging winds in the far right. There was a 5% chance for large hail, and then the 5% contour for tornadoes is across the capital region into southern Vermont into the upper Hudson River Valley. It seemed like almost every time this year we had a 5% contour, we had a tornado, and that's the kind of season it was at Albany. There was a severe thunderstorm watch issued at 19 UTC, which is 3 in the afternoon. Albany was flexible with a tornado or severe thunderstorm watch. We could have gone either way, and based on solid collaboration with SPC, Binghamton, and Burlington, we decided in terms of the messaging that damaging winds would be the main threat with an isolated tornado or two, and sure enough, we did get a couple of tornadoes. In terms of the synoptic flow, basically we had the strong mid-level trough approaching from south central Ontario and the Great Lakes region, pretty strong wind maximum with it, and then we had this short wave moving into the eastern Great Lakes and across upstate New York into New England. And there was a warm front moving through in the morning, and the remnants of Laura were passing east of the mid-Atlantic states, and some of the residual moisture was streaming northward into the northeast. In terms of the jet structure, the equatorward jet streak was moving, the poleward jet streak was moving away from northern New England and the Canadian Maritimes. But we had this secondary jet max with this kind of a split flow moving across into the Midwest and lower Great Lakes region with 100 knots. And this would area of upper level dive fluence over us, and this jet streak would be coming in during the late afternoon and early evening. In terms of the low level flow, there was a strong 850 millibar jet, 45 knots over Buffalo at 12 UTC. There's also a pennant of 50 knots over Greensboro. So basically, we had this pretty strong low-level jet of 35 to 50 knots at 850, something to look for as those pennants when you're thinking of a tornado day in the Northeast. At 18 UTC, 2 o'clock in the afternoon, there was some stratiform rain in the morning, and sure enough, we break out in the capital region with the warm front hung up over the Adirondacks into southern Vermont, the northern Berkshires around 2 o'clock, but the movement was further north, and then you had this initial wave and cold front moving in from the west. We did do an 18Z sounding this particular day. We got out into the warm air and the sun. The surface space cape was a little over 1,000. Mixed layer cape initially was a little low at 250 joules per kilogram. But the other thing that was interesting is the LCL heights were low. The surface parcel was 526 meters, or a little over 1,500 feet. And the mixed layer LCL was 870 meters, a little over 2,800 feet. So low LCL is an indicator for possible tornadoes. The D cape wasn't super high at 634 joules per kilogram. The mid-level lapse rates weren't terribly strong, but the 0 to 6 kilometer bulk shear and the effective bulk shear were both 47 knots. So supercells forming to align with the low-level veering in the low levels, and then the strong mid-level flow southwesterly looked like the main threat. Also, the 0 to 1 kilometer shear was 23 knots, and the storm relative helicity in the 0 to 1 kilometer layer was over 200, which is impressive in the Albany forecast area. Whipple of zero height was a little over 11,000 feet, and there are the 0 minus 20 C heights. The supercell composite parameter was almost 5, which is very high for our forecast area. Anything over 2 is notable. The precipitable water value is over almost 1.7 inches. The other thing to talk about is its clockwise veering photograph, the clockwise movement, again, favorable for tornadoes, and then how it got kind of straight. We actually had a few splitting showers or early thunderstorms early, but again, impressive sounding for a tornadic day. And then looking at the wrap, basically the mixed layer cape at 19 UTC was around 1,000 to 1,500 joules per kilogram west of the Hudson River Valley, with that shear of 35 to 45 knots. The supercell composite parameter was 2 to 4. Again, we had indications of this with the 18Z sounding, a little bit over 4 in parts of upstate New York. And then the bunker storm motion was generally about 30, 35 knots. Also at 19 UTC, the 0 to 1 kilometer storm relative helicity was 100 to 150 meters per second square from the RAP data. Again, the low LCL heights were 500 to 750 meters, and I put that in feet there. Very low, kind of a quasi-tropical type of environment. Precipitable water values were 1.5 in the shade of green to as much as 2 in the southern periphery or forecast area, so very high PWATs, with dew points in the lower 70 or upper 60s to lower 70s. One thing that was a kind of an inhibitor for widespread severe was that the D cape was stronger over west central New York with 800 joules per kilogram or greater, only about 500 to Albany in the early afternoon when that watch was issued, and the lapse rates in the mid-levels are weak. I think this is probably why we didn't have a super widespread severe one that was more concentrated based on the details of the tornadoes that we'll see shortly. And at 21 UTC, when severe weather was moving into eastern New York, the mixed layer cape across all of western New England into eastern New York was 500 to 1,500 plus joules per kilogram. The maxima was across eastern New York of 1,000 to 1,500 plus, with again the shear of 35 to 45 knots, so supercells likely. And the storm relative helicity in the 0 to 1 kilometer layer continued to be 100 to 200 meters per second square across eastern New York into western New England, with the storm motions of 30 to 35 knots. There's a peak up in the upper Hudson Valley into the Champlain Valley. But 21 UTC, the surface map, the warm front busted through the Adirondacks, is kind of still hung up near the Hudson, Champlain Valley, and into southern Vermont. But then we saw this prefrontal surface trough form. We have seen severe weather, tornadoes at times with this. We have southeasterly flow at Albany. Again, that backflow is indicated here near the capital region. And then you can see westerly flow here at Poughkeepsie. Dew points are in the lower 70s, and that's a good setup for possible supercells and tornadoes. Looking at the New York State mesonet, you had channel southerly flow coming up the valley, but then notice how it turns southeasterly in the capital region near Albany. Again, this back surface flow. The LIDAR data I don't have in here, but basically Red Hook and Albany showed the channel southerly flow coming up. We're seeing here a little bit of this backflow of the southeast. Then looking at this 2130 UTC, which when I showed the radar data, it was around tornado. Touchdown occurs in the capital region. Again, you see the areas in the green here is low-level convergence, and you can see a little bit of a pressure fall here. And again, this is going to be, this general area right here is where we'll be looking at the radar data very shortly. Nomogram of showing gate-to-gate shear versus mesocyclone rotational velocity for a number of cases in the Albany area from past work. Basically, as you get into regions 2 and 3, the mesocyclonic rotational velocity goes on the right. The shear on the x-axis and the y-axis is your low-level shear. When you get into regions 2 and 3, your chances are greater for a tornado. Last EF3 Duanesburg had a VM, or mesocyclonic rotational velocity, of 89 knots with a shear of 0.005 almost, and it was in this region, which is usually 100% tornadic. Also, an NROW study showed that basically NROW values, sometimes it's hard to discriminate between null events and tornadic events with an NROW value close to 0.8. So you shouldn't use it as a single discriminator. You should look at all the other data. But one thing I took away from our study that Brian led and I helped with is that basically for EF1 tornadoes, about 0.81 is the median value. If you're nearer to 1, you're in that upper 75% quartile. Better chance, 0.61 for EF0. So anything over 1 is a better indicator, but keep the median value in mind. But here's a loop of the event, and keep an eye on the cell here that moved across the northeastern portion of the capital region. You have this supercell coming out and spin up along this broken line here, and then you have this bigger line that sort of gets going and then sort of weakens as it moves eastward. We're going to focus on this area of convection from 2029 UTC to 23 UTC, especially between 2029 and 2130 UTC. So at 2009 UTC, there is a strong cell showing rotation with a bounded weak echo region you can see here, and an elevated core of 60 plus dBZs to 22,000 feet, 50 dBZs to 28 that we had ping pong ball size hail reported in Broad Albany in Fulton County. And basically this cell would continue to press eastward. We also saw the CC values drop to 0.85 to 0.9, which is a good indicator of hail. And these are we had a couple of ping pong ball size hail reported. This cell along the line that was showing a strong mesocyclonic rotation. 2124 UTC, a tornado warning had been issued because a hook echo formed and we saw pretty good reflectivity inflow notch and pretty good rotation. But all of a sudden at 2124, we had pretty good gate-to-gate rotation of 25 knots, a shear value of 0.029 based on the VR shear tool, about 27 nautical miles from the radar, and the couplets near Mechanical and Stillwater, 2 minutes before tornado touchdown. And again, the tornado warning was issued at 2111 UTC. 2126, very well-defined hook echo. The NROW value kind of spun up at 8.81 at 2108Z, then it kind of simmered down, then went back up, then it kind of came down, but aloft at the 3.1 scan was 0.93. But a tornado warning was issued for this area. The peak value is 0.85. It was one of the things issued by when I was on the warning desk, looking at that along with the VR shear. And then we also had reports of rotation of a wall cloud. There's a lot of spotters on this day, and we did have a tornado touchdown near Stillwater with trees down and one injury. So basically, at 2126 UTC, we had impressive gate-to-gate shear with a value of low-level rotational value of 46 knots, the shear value of 0.0865 over a 0.3 nautical mile diameter, 27 nautical miles from the RDA. TVS is near Stillwater. There you can see the reflectivity of the hook echo. The spectrum width was 21 knots. Usually anything over 20 could be an indicator of a possible tornado. Again, there's a high false alarm rate at times with spectrum width, but I figure I should show that too. And even the baby Yoda, the child, is very concerned at this point, this rather impressive tornadic coupling. The 30-minute low-level azimuthal shear tracks peaked as it got near Mechanicville and Stillwater around 0.015 seconds to the minus first. Studies have shown that when you get up around 0.015 or 15 times 10 to the minus third, that a tornado is more likely, and sure enough, it did peak. This was being looked at when the warnings were issued. We did have a tornado touchdown in EF1, about a minute or so, with a damage to a mobile home and 1 injury. The maximum speeds are 100 miles per hour. This is a view looking from east and westward, so you're looking from the east of the tornado or funnel cloud, and we had a lot of reports. We could even say tornado likely when we were issuing SVSs on the tornado warning. And going ahead about 15 minutes at 21:41, this particular study kept the tornado warning going. There was a tornado warning in effect here, even though it's showing here in GR2. The NROW values weren't as oppressive for about 6, 7, 8 minutes, but all of a sudden they spun up again at 21:41 as it moved towards Scatico. We peaked at 0.93, just below 1. And sure enough, we did have to issue, the tornado warning was in place. We had a home lose a roof and a shed destroyed and damage to a school roof in Hoosick Valley. Basically, here is the hook echo. The spectrum width peaked at 20-25 knots, and then we had gate-to-gate, a low-level rotational velocity of 44 knots with a gate-to-gate shear value of 0.051 over a 0.5 nautical diameter rate across the storm at a distance of 29 nautical miles from the RDA. And the radar beam is about 2 kilofeet above radar level, about, I think it's about 3,800 feet above ground level. Sure enough, again, following the tracks, notice this bob of weight here that the shear value peaked at 0.015 in terms of the MRS 0 to 2 kilometer above ground level, 30-minute low-level azimuthal shear track. So this is a right-moving storm, rather impressive, and the tornado warning was on it, and the track, it did peak around that time. And then we had a tornado on the ground, which is a little bit longer than this because the storm data was just getting refined when I was putting this together, that it's about on the ground for 3 minutes and 100 yards with over 1.25 miles distance, and it tracked, here's Valley Falls, even into Valley Falls. So it was a longer track tornado in EF1. Finally, there was this EF0. Initially, it was a microburst with a funnel cloud, but this storm did not have a tornado warning on it. It was a miss, but it had slightly higher NROW values. It's about, basically about 4,500 plus feet above ground level with this. It impacted Hartman. It's the village of Hartman with some trees down and trees on a home. A private meteorologist, Brandon Capasso, did the storm survey with Steve DiRienzo, or WCM, and the damage was mostly tree damage. And again, here's a picture of the brief tornado touchdown, about a minute. It did have the higher NROW values, but it wasn't as impressive, the gate-to-gate shear with this particular cell. So where do those two storms fit on the nomogram? The EF1 had a mesocyclonic rotational value of 58 knots for the Scatico cells with a shear value of 0.051. So region 2, 71% tornadic, mainly weak tornadoes, which was an EF1. And then it had about 57 knots with a shear value of 0.085, a little bit off the scale here because I probably should have extended to 0.5 nautical miles diameter. Again, that would be in region, more like region 3. And again, the lead times are 15 and 11 minutes in the 2F EF1, so high likelihood in group 2 or 3 of the tornadoes. So here are the storm reports for the day. Again, not a whole ton, but we had some wind, a sprinkling of wind, a few tornadoes, and a couple large hail reports, so 11 overall. So the results from this case study, a shortwave and prefrontal surface trough ahead of the cold front helped focus the severe convection. Again, prefrontal surface trough is very important in the warm sector for tornadoes in our area in severe weather. Moderate instability, high shear environments supported supercells and tornadoes. Low LCL heights, tropical lake environment with enhanced 0 to 1 kilometer storm relativistic values favor tornadoes with some back surface low in the Hudson Valley and Capital Region. Right moving supercell on a broken line produced the 2F1 tornadoes in the Capital Region, separate EF0 for west-southwest Glens Falls, and then application of the VR shear and NROW studies were useful in the warnings, and the MRMS 0 to 2 kilometer low-level azimuthal tracks provide some guidance in peak with tornado touchdowns. And that concludes my talk, and thank you for your time.
Thanks, Tom, for your great presentation. If there are any questions right now, you can definitely utilize the chat box.
It looks like, Christina, there is a question from Ross Lazier. And so Ross writes, great talk, Tom. For this case, there was a discrete, briefly rotating supercell earlier in the afternoon. Could that have played a role in lowering the LCL? through coastal development, and perhaps laying down a boundary for favoring tornado genesis in Saratoga County later in the afternoon.
Yes, that is possible. There was a splitting cell further west earlier in the day as it moved through the Mohawk River Valley. I didn't get into the details of looking at like the RAP of the mesoscale data, but putting down a boundary, it kind of went through like a phase change as it moved out of the Mohawk Valley towards like the juncture of the Mohawk and Hudson Valley. And the thing that was incredible is we had a lot of reports from people following this supercell and the one that produced a tornado. And it's not often we get to put, after our initial tornado warnings, a tornado is likely, and we get the ground truth. So the answer to your question is yes. It's just I haven't dove into the details of some of the mesoscale, what the mesoscale guidance showed.
Okay, thank you. I think we're about 2 o'clock now, so we can move on to the next presenter, which is the Sioux from the Boston WFO, Joseph Della Carpini. He will give a discussion titled May 15th, 2020, Severe Thunderstorms in Southern New England.
All right. Thanks, Christina. I guess everybody can hear me and see my screen?
Yes, we can. Looks good, Joe.
All right, thanks, guys. Appreciate it. First of all, hello to everybody virtually. I wish we could all be together this year. This is always one of the more fun conferences, but you know, it is what it is. So this was the May 15th, 2020 severe weather outbreak in Southern New England. This actually, being 2020 what it is, arrived about a week after we had our last snowfall for the season. So went right from winter into severe weather season. And as it turns out, our severe weather season, at least for now, closed out with the October 7th QLCS and derecho. So we had a couple of QLCS events to sandwich our severe weather season this year in Southern New England. I want to thank the contributors. They actually did a lot of the lifting for this presentation. Rodney, Hayden, Bill, Andrew, and Frank from our office. So I really appreciate their effort into putting this event review together. They always make me look good. Okay, so we're going to talk a little bit about the model guidance from this event, in particular the high-res guidance, the SHREF, and some of the CAMs in particular. And in doing so, we'll look at the synoptic and mesoscale environments for this event. And then, you know, kind of what happened, go through some of the radar imagery. This happened during the time of the Taunton that's the SLEP outage. It was out for a week or two, so we were relying primarily on the Albany radar. But in our conclusions and best practices, I'll also share some thoughts from Andrew Lecanto, who was working the radar this day, as to how he kind of managed working this event without the use of our primary radar K-Box in Taunton, Mass. So to begin, just to show you, SBC I think did a fantastic job, and you know, of course, collaboration with our office and neighboring offices, Gray, Albany, and New York. Slight risk for much of the Northeast, but also an area of enhanced risk from central New York into western New England. That really verified well. You can see all the wind damage reports line up nicely with it, and even one report of a tornado in Albany's area that day. So really, the forecast worked out very well, and we were able to message the threat effectively to our emergency managers and our core partners. But taking a look, just a couple of the graphics from the SPC SHREF, which we really rely on to kind of get us in the ballpark. You know, it's not always exact as to where the convection will end up, but it really does a good job in highlighting the potential threats and general, you know, threat areas. In this case, this is a 30-hour forecast from the SHREF, valid on 21Z, May 15th. And you can see the median SB CAPE is approaching 1,000 joules per kilogram. Into the lower Hudson Valley and into western New England. You know, pretty typical for a spring severe weather case. Our ocean temperatures are still rather cold for that time of year, so obviously it's a lot more stable as you get closer to the coast. And a lot of our early season severe weather events are focused across our interior of Massachusetts and Connecticut. So, you know, right off the bat, this is kind of telling us, okay, we're going to have to watch for some potential convection in New York State heading eastward, and, you know, probably weakening as it heads toward the coast, which, again, fairly typical for the springtime. The other thing I'll show here is the significant tornado ingredients, and this is something we like to look at quite a bit. It's a combination of several factors, you know, ML CAPE, the LCL height, helicity, kind of focused on the lowest levels, you know, 0 to 1 kilometer, 1.5 kilometers, along with the 0 to 6 kilometer shear. along with the probability of at least a 100th of precipitation. So as you can see, it's highlighting a fairly broad area from central New York on eastward into New England, and actually focused a little bit more on western New England here. So definitely, putting in our minds, back of our minds, that we're looking at a convective day with probably wind damage, but potential for an isolated tornado. In this case, yeah, it certainly did verify a little bit to the west of the main area, but this does a very good job in at least highlighting the threat that we may have to message the potential for at least an isolated tornado across parts of the area or somewhere in the Northeast. So let's go into some of the CAMs here, and something we really like to use is the HREF. And you can see here, this is the 24-hour probability, neighborhood probability of severe wind. And this was valid from 12Z Friday the 15th to 12Z Saturday the 16th. And the highest probabilities are focused across eastern New York into western New England, north of our forecast area, but still in the ballpark. But notice the probabilities drop off pretty rapidly as you head east. And this is an agreement with what the SPC SHREF had shown for those higher service-based capes. So again, this tells us we're looking for convection primarily across the interior, severe convection. And then looking at the max 2 to 5 kilometer updraft helicity, again, this is a good proxy for potential severe weather. It kind of agrees with the previous slide, showing that the highest threat for severe weather will remain across interior New England, eastern New York, and perhaps even a little bit north of our area, but still close enough that we need to keep an eye on western Massachusetts for the potential of severe weather. So here's the actual storm reports from May 15th, kind of zoomed up on New England, and you can see a large corridor of wind damage. Again, in one isolated tornado, but across the thruway in New York State on into really the kind of the Route 2 corridor in northern Massachusetts, also into adjacent parts of Vermont and New Hampshire. But notice also there was severe convection as far east into the greater Boston area, something that wasn't really pegged so much by the SHREF or the HREF in this case. So in looking at this case, we were to decide, what really happened? Why did the convection survive that far east in a kind of a synoptic pattern that's really not favorable for severe weather to make it into the coastal locations, due primarily to the stabilizing flow off the ocean. So in looking at some of the upper air, this is 700 millibar, the ensemble mean from the HREF. It's a pretty robust shortwave for spring, accompanied by up to 50 knots of, or just over, of mid-level flow. So this is kind of setting up, a high shear environment. And we think that it's that, stronger shear that really compensated for it. Will show is really just modest surface-based instability and marginal mid-level lapse rates. Usually with our New England severe weather, we can do a little bit of a trading between our ingredients. So on the days where we have, high cape, we can get away with maybe some weaker mid-level lapse rates or, weaker mid-level flow, whereas the earlier late season events, we tend to have more mid-level flow, higher shear environments, which can compensate for that lack of instability and weaker lapse rates. So it's a trading of several factors that usually come into play. It's very rare for us to have everything kind of come together really nicely with high instability, high shear, and strong mid-level lapse rates. So in looking at this case, and I remember this from a couple of days ahead of time, several of the CAMs were pretty aggressive in showing these discrete supercells forming well ahead of the QLCS, and this really raised some flags at our office. I remember we had some discussions more or less online because we were all teleworking, but kind of concerned about this because knowing it was a high shear environment, this looks potentially like a big tornadic day. And in fact, one of the CAMs, which I don't have shown here, I believe it was the NAM Nest, actually had a pretty good maximum updraft helicity right along the Route 2 corridor, and another one close to Worcester, which actually resembled the 1953 Worcester tornado. So certainly our attention was raised to that potential scenario of having these discrete supercells form ahead of the line. But it turns out they were much too aggressive in doing so, and most of our convection was associated with the QLCS itself, which was well forecast by the CAMs. So we wanted to look and say, what happened? Why did the CAMs really kind of fail in that regard? Well, it turns out, one of the things where there was enough shortwave ridging over New England at 18Z on Friday to really help suppress convection. It delayed the advection of moisture and instability further east into New England. And you can see at 500 millibars at 18Z, the surface ridge is pretty much parked over Massachusetts and Rhode Island. So that helped to really keep the deeper moisture and the deeper instability farther to the west. And you can see here on the MU Cape, this is off the HREF, but it's pretty close to reality. You can see the greater instability, greater than 1,000 joules per kilogram of MU Cape, certainly located farther to our west from Albany's forecast area and points west, with much less instability farther east into southern New England at 18Z. So likewise, that delayed the advection of the higher surface dew points, which you can see here. This is at 23Z off the RTMA. In southern New England, values are, I'll say in quotes, only the upper 50s to the lower 60s, which, in some cases is sufficient to generate convection. But you can really see the deeper moisture dew points getting to the mid 60s or focused back across eastern New York, Hudson Valley in particular. So it was the delaying of that higher dew point air that didn't arrive in southern New England until later in the evening, 10 p.m. to midnight. And it was offset with the timing of the convection. So that really prevented that initial round of discrete, convection getting underway or getting developed, which we believe really saved us from having a kind of a bigger severe weather day with potentially a little bit more of a tornado outbreak. So looking at some of the other high-res models, just to show the trend here, this is the HER version 4 at Friday 0Z. You can see it had already brought dew points into the mid-60s across most of Massachusetts by 23Z. And again, in reality, this wasn't realized until about 3 to 6Z. So it was the earlier arrival of this moisture that helped to spark off some earlier discrete convection. And even the NAM nest, a similar result, too aggressive with bringing these mid-60s dew points into southern New England. So that in itself helped delay some of the convection until the actual QLCS. So fortunately, our friends at Albany were kind enough to send up an 18Z sounding that day. And when we were looking at it in real time, we noticed a couple of red flags, and I'm sure you can see them too. First of all, dew point's only in 57, so in the upper 50s, and there's enough dry air there that it's a bit of a red flag for getting convection out ahead of that line. Relatively low capes, surface cape of 237, certainly not all that impressive. And, typical in southern New England, but fairly weak, mid-level lapse rate, 6 degrees Celsius per kilometer, not shabby, but certainly nothing that's going to overcome, the other two limiting factors. On the plus side, though, very good 0 to 1 kilometer helicity, which, we had anticipated. The model guidance did a good job at that. Obviously, bulk shear and the D-cape, too, really pointed to the potential for damaging winds. So it turned out to be primarily damaging winds with the QLCS as opposed to discrete convection with a greater tornadic potential ahead of the line. So next I'll show a couple of loops here. This is looking at the western part of New England from the Albany radar. Again, the K-box radar was down at this point. You can see a fairly healthy QLCS making its way across western and central Massachusetts. The warning box is going up as the line moves east. You can see just good reflectivity gradient on the leading edge. You can see some of the rear inflow jet notches where the wind damage was kind of concentrated, but by certainly most of the wind damage from the earlier image was across Route 2, where we had the better co-location of the stronger reflectivity and the winds aloft. But there was wind damage down into the Springfield area as well. And on the right, the velocity data, you can see fairly strong winds as well, although we're getting higher and higher up as we go east, but certainly the potential for damaging winds. And the next part of the loop is also from the Albany radar, and you can see, obviously it looks like it's weakening as it heads east. That's not necessarily true because obviously a greater distance from the radar, but the convection did maintain itself all the way into Boston. We did have the use of supplemental radars during this as well. First, the CASA radar at UMass Amherst, which helps us in Western Mass, and also the FAA's Terminal Doppler Weather Radar in South Weymouth, which is just south of Boston. I don't have the images shown here, but those were used as supplemental data sources, as well as the 1 minute GOES 16 data too was used. But you can see again, squall line makes it all the way to the coast. Weakening is shown, but it's not in the true case weakening. It's just getting a farther distance from the radar. So see, these are some of the observed maximum wind gusts from the ASOS sites across the area, and you can see again, best concentration really across northern Massachusetts, widespread 50 to 60 mile per hour winds, even a peak of 63 miles per hour at the Worcester Airport, which is an elevated site. Gusts a little bit less as you head farther south, but still, fairly widespread for Massachusetts. I'd say on the order 40 to 60 miles per hour in spots with the greatest concentration along this Route 2 corridor. And no event review would be complete without some nice damage photos. This is from Holyoke, Mass. From the Holyoke Fire Department. The roof of a building was actually lifted up by the strong winds, but was determined to be straight line wind damage. This is in Westford, Massachusetts, which is near I-495 in Northeast Mass. Some damage to a house. And a nearby weather station reported an unofficial gust to 86 miles per hour. Which will lead us to a microburst that was actually surveyed in Pepperell, Mass. This is near the New Hampshire border in Northeast Mass, where the star is located here. This was surveyed by Scott Reynolds from our Center Weather Service unit up in Nashua, since it was just a jump over the border for him. He surveyed the damage the next day, and there was a fairly good concentration of damage here in this yellow circle in Pepperell, with spotty areas, if you can see outlined in purple here. It might be a little hard to see, but he was able to confirm a microburst, all straight line wind damage with maximum winds on the order of 90 to 100 miles per hour, which kind of fits in with that nearby home weather station, gust of 86 miles per hour, and a path length of about 1,000 feet. And just a few more pictures. This is Brookline Street in Pepperell, courtesy of the Pepperell Emergency Manager. Again, a lot of tree damage, snapped uprooted trees. And also in Groton nearby, this was a nice photo from a drone given to us by David Hupp. It's fairly clear that this is all straight line wind damage from microburst. A little closer zoom up on the damage there, all lying in one direction, but still pretty impressive straight line wind damage to these trees. So in conclusions, the model performance, the CAMs did well in depicting the arrival of the main QLCS and indicating the main severe threat would be wind damage, but there were significant differences in the timing and consequently the severity of the storms, especially between the HER V4 and the NAM Nest. As we showed, the HER V4 was a little too aggressive in the coverage of the discrete cells popping up prior to the main QLCS, and we think that's perhaps due to the warm dew point bias, which was due to the fact that it was pushing that mid-level ridge offshore a little too quickly, and the NAM Nest kind of showed the same situation. So in hindsight, the dew points topping out in the low 60s instead of the mid 60s, not a huge difference, but we felt that was enough to prevent a more intense, perhaps potentially tornadic outbreak with those pre-QLCS discrete cells. As far as our operations, this was the first widespread event of the season. We had adequate staffing, typical 2 radar warning meteorologists. We have 2 DSS meteorologists, including one on mesoanalysis, and 2 handling social media and storm reports. We get quite a bit of those. As I mentioned, the KBOX 88D was down due to a scheduled SLEP upgrade. We had the supplemental radars, in particular the Albany, New York radars, New York City, the T-BOS, which is the South Weymouth, CASA in South Weymouth, and actually NBC Boston placed a mobile radar in Worcester, which we had access to. And also we made use of 1-minute mesosector satellite data. But just by coincidence, which was amazing more than anything else, we assigned QLCS training in the spring. We usually try a different topic every year. Sometimes it's tornadoes, sometimes it's supercells. This year we just chose QLCS, and by chance, we had a couple of rip-roaring QLCS events for the staff. So several of the staff actually used the QLCS training from Central Region to develop new AWIPS procedures and shared them ahead of time with the staff. So we were pretty much all up to speed and ready for our QLCS event. So I will not pat myself on the back for that. I will hand that to my training team for suggesting it. And finally, on operations from Andrew Lecanto. You can read the quote here, but from his perspective, he was really left with working with a lot of non-traditional sources like lightning and IR cloud top temperature trends as the convection moved closer to central and eastern Massachusetts, where the radar coverage was more sparse, to diagnose how strong the updrafts were. And finally, having our Skywarn reports of damage in a very timely fashion really helped as well. Having the ground truth indicating the weakening storms were still doing damage. To him was a big a tell as any data point he had to continue to warn, even in the absence of any significant lightning. So it really were those 2 things that really helped us with our warning operations as the storm survived all the way into the Boston metro area. So with that, that is my presentation. Thank you very much, and I will hand it back to my good friend Christina.
Thanks, Joe. Thanks for your great presentation and your lessons learned and insight. I don't see any questions. Brian, on your end, do you see any questions?
Not yet, but if anybody has one, you know, you can either write it in the chat or use the raise hand option and we can unmute you if you have a question.
Yep. Or feel free to email me later. Everyone knows where I am.
Definitely. I'll just throw a little tidbit out there, but as Joe mentioned, the Tornado Warning Improvement Project training, the TWIPS training, I think it's excellent. And Joe, is that the training that your staff took part of before this event took place just by coincidence?
Yeah, we did. We just decided to focus on it this year. And, you know, I'm sure for you guys too, it kind of paid off. I was talking to Mike Evans. It's like, man, you know, how many times of the training that you do pays off immediately? You know,
right,
not just the
absolutely.
QLCS, but especially with QLCS tornadoes. And we had one actually in Millis, Mass with the October 7th derecho. So that really paid off too.
Yes, and that was another incredible event. I think we have another talk on that coming up soon in a few sessions. But yeah, for all those non-weather service people out there, the TWIPS training is available on YouTube. I found it to be a fantastic resource. So even if you're not in the weather service, that training is available on YouTube, and you can just look up Tornado Warning Improvement Project from Central Region, and all 13 lessons, I believe, are available on YouTube. And they're fantastic. I really found them useful. So just want to throw that out there. But it looks like we're up to the next presenter. So thank you so much again, Joe, for your great presentation. Up next, we have another Sioux, this time from State College. Mike Jurowitz will give us a talk called Tools to Improve Tornado Warning Performance for Supercells, ZDR KDP Separation and Size Sorting Signals.
Christina, can you hear me?
Yes.
I was wondering if you could go ahead and give control of the screen to Scott Leffler from Penn State. We're actually going to tag team this. He's going to start it off, and then maybe we could throw the baton to me about halfway through.
Okay. I think Brian is in, he's kind of taking the reins of giving people the ability to share their screen. So I think Brian can take care of that for you.
Okay.
Okay.
There should be going over to Scott.
Okay, can everyone hear and or see a PowerPoint?
Yes, we can see it and hear.
Okay, beautiful. So we're good to go?
Yes.
All right, great. So like Mike said, my name's Scott Leffler. I'm a PhD student at Penn State right now. So we'll just dive right into the separation of these enhanced regions of ZDR and KDP and supercells. So just real quick outline, we'll give a little bit of a background on the size sorting theory and how it could relate to and does relate to the storm relative winds and potential for tornado genesis. Then we'll dig into the methodology of how we went about studying this in these supercells, and then give some results before summarizing things up and talking about where we want to go in the future. So just for some background, just to set the stage for everyone. So size sorting background comes from the very simple process of the fact that in terms of your distribution of raindrop sizes, your larger raindrops are going to have larger terminal velocities, terminal fall speeds, and therefore they're going to fall through a layer, just a given layer in the atmosphere, more quickly than your medium and smaller size drops will. And so I'm a fan of animation, so we have our large drop here in darker blue, and then a bunch of smaller drops in lighter blue, and then we see that the larger ones tend to fall through the given layer, which is just my PowerPoint slide, a lot more quickly and rapidly than the smaller drops do. And so the other part of this is, how does this manifest in dual pole observations? So just really quick, for those that aren't dual pole junkies such as myself, the two main ones that we're going to be looking at are ZDR, which is differential reflectivity. And that's just the logarithmic difference between the two reflectivities at horizontal and vertical polarizations. The key thing to look at is that it's a good estimate of median drop size, because as drops get larger, they become more oblate. The more oblate they get, the larger their horizontal dimension is to their vertical dimension, which, as you can look at the equation, will then increase ZDR. So we can use it as a good estimate of the drop size, and it's not sensitive to the number concentration. On the other side, we're also looking at specific differential phase, or KDP, and that's just the phase shift per unit distance between these two different polarized waves. In water, in rain, it's closely related to liquid water content, and then it is sensitive to number concentration, and it's also less sensitive to drop size than your ZDRs and your ZHs will be. Those are usually proportional to about the 6th moment, so D to the 6th, whereas KDP is usually sensitive to something between 4 and 5, a little bit over 4, typically. And so going back to this kind of simple schematic walkthrough, I originally had this just falling straight down into the vertical, but what if we add in horizontal motion? What if we add in winds in this layer? So because of that, the larger drops, again, they spend less time in this layer, so they're going to have less time to be advected by these storm relative winds. And because of that, the smaller drops, which spend more time in that layer, are advected farther than the larger drops are, which then leads to this separation of drops by size, or you could say they're sorted by size, hence size sorting. So we'll take us back to the original kind of graphics, but now we're going to add in just a left to right wind. Very simple here. Then as these fall out, the larger drop just doesn't spend as much time as these smaller drops do, so they get advected different quantities in terms of a horizontal distance. And so the end result is we have this separation between these two, and we have a sparse concentration of really large drops. And then on the other side, we have a larger concentration of relatively smaller drops, so smaller, more medium-sized drops. Well, we know that the larger drops, that's a good estimate. ZDR is a good estimate of median drop size, and it's not sensitive to number concentration. So this region is going to be characterized by high ZDR. And then the variable that is less sensitive to less sensitive to drop size and is sensitive to number concentration is KDP. So this region is going to be characterized by higher values of KDP. And so what results in this thing theoretically is a horizontal separation between enhanced values of ZDR and KDP. And that's the signature that we look at in this study. And just some background here, just for some observations here, just some past studies. On the left is a 4-panel plot of observations. The key takeaway here is this green outlined area, which is enhanced KDP, and this purple one, which is enhanced ZDR. And it's just important to show that they're not co-located. There's a little bit of separation between the two. You can also see here, this is just a very simple simulation here of similar to the schematic that I just showed of just precipitation falling and being advected left to right. And we have ZDR huddling kind of around the leading edge of this precipitation shaft, where the largest drops are falling the fastest, whereas KDP is pushed a little bit further back into the precipitation shaft. So we see this separation between high ZDR and high KDP. Okay, so enough of just kind of really basic theory. Let's get into the methodology of how we looked at this. So we looked at this in a bunch of observed supercell storms. So the supercells had to be within a certain range threshold to make sure that we had good low-level data. We weeded out anything with a correlation coefficient value less than 0.93 just to make sure that we weren't sampling non-meteorological scatterers. And then the other thing was that all 3 of ZDR, KDP, and correlation coefficient needed to be present throughout a particular storm's life cycle. So we did have to throw a few cases out because 1, 2, or all of these weren't present for a handful of volume scans, 1 or 2 volume scans. So we made sure that we had all 3 of these throughout the analysis period. And so what we're using is we're using an automated application, an automated algorithm, rather than just subjectively defining these regions and these areas. So what we do is a method from one of our previous studies, and we simply plop down in ours and the panels A and C. It's just, we call it an analysis box. It's basically just a region of interest. And then we just take all of the gates within that box, and then make sure they meet that correlation coefficient threshold, and then also meet a ZDR and KDP threshold so that we're really honing in on the high or enhanced values. And then all of the gates that meet that threshold, that comprises our enhancement region, and then we just take the median X and Y coordinates of these regions. And that gives us our centroids, and these centroids are what we use to quantify the separation throughout the analysis period. And so here's just an example, KDP on the left and ZDR on the right from one of our supercell cases. And then here is what the centroids from the algorithm shows, and it seems to hone in on these enhanced values and enhanced regions pretty well. And then just an example, here's just a schematic in terms of the two components that we quantify throughout these, just to give some context to the numbers that we'll show. So here's just a schematic showing the enhancement region and the centroids. But then the two components of what we call the separation vector is the magnitude of the vector, which is just the separation distance, the distance between these two centroids. And then we also take into account the orientation, which the orientation is taken as degrees either clockwise or to the right of the storm motion vector, pointing from KDP to ZDR. And so we track this. We do this at every volume scan, so every 4 or 5 minutes on average. So we do this throughout the analysis period. Here's just an example of tracking this throughout time. And then we can also get the numerics from this and quantify the separation distance, which is shown here, just an example of a time series of separation distance. And also we can do the same thing for the orientation angle relative to storm motion. So these are just examples of one case, and we do this type of analysis for a large number of cases. And I think this is the point where I will mute, and if we could switch it over to Mike, then he can take it away.
Okay, can everyone hear me and see my screen?
Yes, both of those are good, Mike.
All right, very good. Okay, so Scott set the table nicely for me, so I'll go into some of the results of our work now. Okay, so this is a map of all the different cases that we looked at in sum total 116 over probably a 5 to 7 year period. Good geographic diversity across all different parts of the CONUS, and a pretty good distribution too between tornadic and non-tornadic supercells, which is of course what we wanted for this case. And if you've looked at enough tornadic supercells, as myself and Scott and all the people in our research team has, probably hundreds and hundreds of them, you would know that really the values of ZDR and KDP that you see in any given storm can not only vary pretty wildly from storm to storm, but can also vary over time within the storm. So one of the beauties of the automated technique that we came up with is it employs something called an adaptive threshold. So it keys in on what the important ZDR and KDP values are for that particular storm. And this graph just kind of shows almost a PDF of the different values of each over time. So it tells you where they tend to live in general, but the values do vary over time. So that adaptive threshold technique has worked to our advantage. So these box and whiskers here, what you see on the left-hand side of the screen for in both of them, actually, we binned it into significant tornadoes, weaker tornadoes, and non-tornadic supercells. And the main point to take from these box and whisker plots is that the more discriminating parameter, if you will, is that separation angle as opposed to the separation distance. So although maybe you could argue for a slight bump up in the SIGTOR cases in terms of the length of the separation vector, where we had the most bang for our buck is that there seemed to be angle values much closer to, those separation angles were much closer to orthogonal in your much closer to orthogonal in your tornadic supercell cases. And you have more parallel angles with regards to angle with the storm motion vector in your non-tornadic supercells. So again, it's that separation angle that appeared to have the more discriminating value. And then these next two schematics will show that pretty nicely. Could go back and forth a couple times. Here is kind of a polar plot of where both the separation distance and the angles tend to live for your tornadic supercells in sum total, and then your non-tornadic. So if we flip back and forth, you can see a much closer, on average, to orthogonal separation angle in your tornadic supercells, and a much closer to parallel angle into the storm motion vector in your non-tornadic. And so given the number of cases and geographic diversity and all that we looked at, we were pretty happy with these results. And then these are kernel density plots. Again, sort of a polar plot type image, which shows you where the greatest distribution in terms of distance and separation angle tended to live, tornadic versus non-tornadic. And again, it shows basically the same thing. Much closer to orthogonal separation angles in your tornadic supercells and closer to parallel in your non-tornadic. And we also, we had different ways of showing this. This schematic basically shows the same thing. Your physical separation angle themselves, and then also the deviation from orthogonal. And really not a great deal of overlap here between your TOR and your non-TOR cases. So again, we were pretty happy with these results. And then we also binned these results in 5-minute bins with either with respect to the time of tornadogenesis in your tornadic supercells, or to the time of your maximum azimuthal shear for your non-tornadic cases. So although there's a little bit of ebb and flow over time, again, you can see that the story here is pretty much the same all throughout. Much more orthogonal separation angles in your tornadic versus non-tornadic cases. So in summary, again, we looked at well over 100 discrete supercell cases across the CONUS, and early returns would indicate that there's some real promise here for this technique in being able to discriminate between tornadic and non-tornadic supercells. And for all of us who've had our behinds in the hot seat issuing warnings, historically we have not had a lot of great tools in real time to help us discriminate. So it appears that there's some real promise here, especially with regards, again, to that separation angle, the more orthogonal angles in your tornadic supercell cases. So as far as where we've been and where we're going, we were lucky enough to get a publication in Geophysical Research Letters this past spring. So that paper is out there. We have begun the early stages of a follow-up submission to Weather and Forecasting. This paper should be a little bit more operationally oriented. We plan to have a lot of case studies in there, so we're looking forward to getting that out in the literature. The real holy grail, though, going forward is getting this technique into the hands of the warning forecasters. So we kind of have a two-pronged approach at this time. The ultimate goal is to get some sort of objective automated technique into AWIPS. But that process of getting anything into AWIPS has a lot of bureaucratic red tape, tends to take a long time. So our hope is, we've been working with the Tornado Warning Improvement Project team out in Central Region, and we're going to meet with them again in a couple of weeks to try to develop some GR2 analyst place files. So to try to get some of these objective AI type techniques where a warning forecaster could look at in GR2. So likely the GR2 analyst application will come first, and then maybe after we can get some hazardous weather testbed evaluation, hopefully over time we'll get this into AWIPS as well. And then in even more of a future-minded frame of reference, and then it's another little schematic here. We hope to look into the possibility of seeing if higher radar tilts, if there's any value in assessing this technique, say for 0.9 degrees instead of just the lowest elevation tilt. So that's something we plan to look at in the future too. You know, that would open up the benefits of this to a lot more real estate because, you know, not everybody lives within a certain, their houses aren't within the radar beam only being a certain height above them. So if we could glean any value in higher radar tilts, that would be a good thing too. So that's another future item. And with that, if time allows, we'd be happy to take any questions.
Thanks, Mike and Scott. That was a great presentation. Now, I don't see any questions on my end. Brian, do you see any questions from the audience?
Yes, we did have one question sent from Robert LaPlante here about, and I know, Mike, you did briefly mention this, how are the centroids computed, and is there a manual technique to produce for the radar operator?
Yeah, as far as how they're basically that automated technique, it's if you draw, like Scott was saying, we draw an area of interest in a particular supercell, and it's smart enough to look at the ZDR arc area in a supercell and kind of the KDP foot area in the forward flank, and it's able to determine the mathematical centroids. As far as a warning forecaster doing that on the fly, is it possible to do? Yes, but there's a little worry there in that there would be some subjectivity on exactly where the centroids of these dual pole features are, and that could maybe bias the distance and the angle a little bit. So we're really hopeful that we can get something more objective out into the field, not only for purposes of defining it more, but I think it would just be faster for the warning operator. They have so much info being thrown at them in a short period of time that it would be nice if they had some nice visual aid where they can pick these signals up quickly. So hopefully, Bob, that answers your question.
Okay, thanks, Mike. Brian,
Yep.
any other questions?
No, that's it. And Bob said thanks.
Yep.
Okay, great. We can move on to the next presenter, who is another Stu, this time from the Albany, New York office, Mike Evans. He will give a discussion titled Application of Diagnostic Techniques from the Tornado Warning Improvement Project to 2 tornadic convective cases in the Albany, New York County warning area.
I just got to unmute yourself, Mike.
Yeah, now can you see my screen and can you hear me?
Yes, looks good, Mike.
Okay. All right. So yeah, I'm going to follow up on a few of the themes that we've heard over the last 45 minutes with this talk, showing a couple of examples of applying some of this stuff for some storms that we just had in the last year in eastern New York and western New England. And seems like I can't advance. Oh, okay. All right. Anyway, so this is just an outline. Then I'm going to talk very briefly about the tornado warning verification and this tornado warning improvement project. Again, since that's kind of been reviewed a little bit so far, and then the 2 events that I'm going to show some radar and some stuff from May 15th of 2020 and August 2nd of 2020, and then finish with summary and conclusions. Okay, this is a graph that probably a lot of us have seen, showing that National Weather Service tornado warning verification has been pretty flat over the last several years, and that's kind of the reason why there's been an emphasis on trying to improve our tornado warnings. Both our probability of detection and our false alarm ratios have been fairly flat over the last several years. And of course, we've had methods for diagnosing tornado potential based on radar. They've been around for many years. I think Tom showed this one. It basically just has the radar operator looking at the magnitude of the rotation that they're seeing on radar and kind of correlating that to the occurrence of a tornado. And that can work fairly well at times. And then there's also been studies, this is one from a fairly recent one from Smith et al., 2015, that kind of combines the rotation that you're seeing on the radar to environmental parameters. In this case, on the x-axis, you see rotation, radar rotation, and on the y-axis, you're seeing the significant tornado parameter. And so the idea is sort of combining the information that you're getting on the radar with information from the environment. And that can also give you some indications on whether or not you're likely to see a tornado or not, given a significant looking storm. But again, based on the verification that we're seeing, it looks like this stuff only can take us so far. And one of the problems that comes with looking at rotation on radar is that this is from some recent studies by Markowski, Richardson, and it shows that really the low-level mesocyclone and the tornado can often be two distinct features. And typically when we're looking at rotation on the radar, we are looking at the low-level mesocyclone. The tornado itself is often too low and too small to be picked up by the radar. And so that can be a problem where we're evaluating the rotation associated with a low-level mesocyclone. That can still be a very useful thing, and certainly the intensity of the low-level mesocyclone does correlate to the probability of a tornado. So I certainly would never advocate not looking at rotation on radar to try to determine the potential for a tornado. But there's more to it than just that. So then we get to this whole thing about the Tornado Warning Improvement Project. This was developed by a team of meteorologists in the central region starting around 2015. It was based on a combination of published research and the knowledge of several highly experienced radar operators. There was a series, as Christina was saying, there's a series of YouTube videos that have been developed and organized into a curricula in the Commerce Learning Center. And this is filtered out into several conference presentations over the last several years, including this one. So just the Tornado Warning Improvement Project kind of divides tornadoes into QLCS tornadoes and supercellular tornadoes. For QLCS tornadoes, the idea is to first apply something that's called the 3 ingredients method to a storm that you're looking for that's developed along the QLCS. Not going to go over all of this, but the idea is that you basically want to locate areas of balanced or slightly shear dominant regimes. So you want your little mesovortex potential tornado to be kind of along the leading edge of the updraft downdraft convergence zone of the storm. You don't want it to be back behind that. You don't want it to be necessarily out in front of it, but you want it to be kind of along the updraft downdraft convergence zone. You want your environmental shear to be normal to the line, and then you want to look for bows and local surges. So once you apply this 3 ingredients method, then you can look at your storm of interest and look at these competence builders and nudgers. Look for things like reflectivity dropout regions, paired front rear inflow notches. Again, it's important to look at this updraft downdraft convergence zone. You want to look for an inflection point or an entry area where the updraft downdraft convergence zone is actually entering into the line. So you'd probably want to focus in that area in this case. Line breaks is another thing to look at. And then of course, you want to look at mesovortices themselves, cell mergers, interactions with boundaries, things like that. So based on that, I wanted to show a tornado that we had. I know Joe looked at this case in New England. We had severe weather out in eastern New York as well on this day, May 15th, 2020. And here's just some basic maps from the event. Here's what the radar looked like around the time of a tornado. The time of interest here was just north of Saratoga Springs. You can see the storm kind of blowing out a little bit right there. Kind of a rear inflow notch that you can see here. some weak rotation on the radar at this time, and normalized rotation on the GR2 analysts was showing up at a value of about 0.49 at 3,000 feet. That's really not a very high value, not a value that would typically get you very excited. But we had an EF1 tornado in Saratoga County, just to the north of Saratoga Springs. And looking at some of the things that we could see from this tornado warning improvement project. First of all, this was at the time when the tornado was just getting ready to touch down. A few things that we were able to see and that radar operators should be looking for, in addition to just rotation, possibly a somewhat favorable environment, are these descending rear inflow notches as the lower reflectivities coming into the back of the line. The paired front rear inflow notch right here is also showed up very well in this case. Sometimes you can use spectrum width to get a good handle on where the leading edge or the updraft downdraft convergence zone is. In this case, the maximum spectrum width was right on the leading edge of the line here. It was bowed out. There we go. Bowed out ahead of the line over the southern part of the line, but then entered into the line over the northern part. And so again, this would be possibly an area of interest right here, called an updraft convergence zone entry point. And finally, it looked like that there was some kind of a boundary on the that this line was intersecting. So boundary ingestion was yet another possible confidence builder with this particular storm. So that gets us past May 15th, and of course that storm did produce a tornado. Going on to supercell tornadoes, a lot of the updraft or a lot of the tornado warning improvement project has kind of focused on the stuff that Mike just presented on ZDR arcs and size sorting. And so I'm not going to go over all this because I think Mike did a good job and Scott did a really good job presenting that. Again, kind of the key here is that you want to look for this ZDR arc. And when you have a ZDR arc, that's an indication that you've got some size sorting of your droplets associated with the storm relative wind. And then again, Mike and Scott went through all this, but the idea being that if you compare where the ZDR max is to the KDP max, that's an indication of the storm relative flow. And boy, I got a very sensitive enter button here. But the idea here is that the storm relative flow, when you have an angle near 90 degrees between that vector that kind of represents the storm relative flow and the vector that represents the storm motion, when that angle is near 90 degrees, that's a favorable condition for the development of localized sort of storm scale, storm relative helicity. And so the idea being that we'd like to kind of see, we'd like to kind of look for that in these supercellular type events to see if we get maybe some more confidence for a tornado warning. So I'm going to look at a case from August 2nd, 2020. Deep trough moving across the Great Lakes, warm front extending from northern New York down into western New England. And that image there in the lower right, I think is the STP, or no, it's actually the significant tornado parameter. You can see it was maximized right along the warm front in southeastern New York into western Connecticut. And on this day, we had 4 tornadoes that developed along that warm front in western Connecticut into southern Massachusetts. And again, they kind of developed along the warm front and then moved kind of to the east-northeast. So what I'm showing here is that those tornadoes were all in association with kind of a long track, low-top supercell that developed over the mid-Hudson Valley and tracked east-northeast across northwest Connecticut. The images that I'm showing here on the left show KDP, and I'm going to try to have a really light touch here or else my slides are going to advance, but a maximum of KDP just west of the Connecticut line. And I put a circle right where I think the maximum of KDP is. And then in the lower left, I've got that maximum of KDP represented by the circle, and the lower left is the ZDR. And so you can see that there is actually a separation vector pointing from northeast to southwest, from the KDP max to the ZDR max, while the storm motion was off to the northeast. So there's a large angle between the storm motion and the separation vector at this time. And to the right, I pretty much did the same thing. I showed where the KDP max is in the upper right, and then I overlaid the KDP max with the ZDR maximum or ZDR in the lower right. And you can see that the separation vector is pointing from northeast to southwest, and the storm motion vector is pointing from southwest to northeast. So they're about at a 180-degree angle for each other. Now, a little bit further in time at 2144 Z, you can see it looks like there's been like an eastward surge in the high values of ZDR into western Connecticut. And so that now the angle between the separation vector and the storm motion is about 90 degrees. Because the KDP maximum you can see is here. The maximum of ZDR, that's just too sensitive. The maximum of ZDR is just down here. And so now there's about a 90-degree angle. And that 90-degree angle maintained itself from 2144 through 2201Z. And that was one of our tornado touchdowns that occurred at 2209Z with a storm just after this, what I'm showing on the right there. So I could show the entire evolution of this storm, but I don't know that I have time. So what I'm going to do is I just kind of plotted the evolution of the angle is the blue line, and the evolution of the NROW is the orange line. And I on this graph here with time moving along the x-axis, and you can see when the various tornadoes dropped touchdown. And of interest here was when the EF1 touchdown. You can see that the blue angle line was right around 90 to 100 degrees. There was a time period right here where the blue angle line was around 90 degrees and the NROW was still relatively low. So it seems like at that time, the angle between the separation vector and the storm motion probably gave us a little bit more heads up, a little bit more lead time than just looking at NROW would have. Now, the one last thing that I want to show here is that can show you some of the difficulties sometimes in applying this methodology is the storm that Tom showed from August 29th, 2020. And that was the supercell that produced a tornado. It's going to produce a tornado fairly close to Stillwater right here. So here's where the supercell just before it produced a tornado. And I got KDP here on the upper right. And it's kind of hard just eyeballing this to figure out exactly where the KDP max is. I mean, it looks like there's maybe one max here. There's maybe one max a little bit to the west. And also it's kind of difficult to figure out exactly where the ZDR max is and to really actually even identify a really well-defined ZDR arc in this case. Now, if I go forward in time, this is right when the tornado touched down. It looks like the ZDR arc did sort of, or at least a maximum of ZDR did kind of develop. KDP is kind of strung out here. There's really no really good, well-defined maximum, although it looks like there might be one right there. So my main point of showing this last case right here is that it's not always perfectly clear cut on determining exactly where your ZDR maximum is, your KDP maximum is, and that's why I think some of the automation things that Mike Jerwitz was talking about in his last talk might be really useful for a case like this, because sometimes it's kind of hard to just eyeball this, especially in real time when you've got a lot of other things to look at and you're kind of under the gun for a possible tornado warning. So finally, I'm at my summary here. So again, warning for tornadoes remains a challenge in the Northeast US. I think everybody would agree with that. Both QLCS and supercellular tornado warnings are prone to false alarms, along with occasional missed events. It does look like recommendations from the Tornado Warning Improvement Project and related research appear to hold promise by allowing radar operators to evaluate aspects of the storm scale environment conducive to tornado genesis. Again, things like descending rear inflow notches, the development of storm scale, maxima of storm relative helicity. All these things can be kind of implied by looking at radar. And so I think there's a lot of potential there. But again, challenges, especially with the last technique that I showed, challenges can sometimes occur with the interpretation of noisy and varying fields. And that's where I think some of the automation that Mike suggested could really come in handy. So with that, I will take any questions anybody might have.
Thanks, Mike. That was a great presentation. Now, I don't see any questions on my end. Brian, do you see anything from the audience?
No, no questions yet.
Okay, well, I guess for the sake of time, we are at 3 o'clock. We can move on to the next presenter. We have a forecaster from the Binghamton, New York National Weather Service office, Mitchell Gaines. He will give a talk on discussing the October 7th, 2020 severe weather event across upstate New York and New England.
All right, can everybody hear me and see my screen okay?
Yes, looks good.
Yes, we can hear you.
All right, great to hear. We're going to be talking about a event with this talk that's not too long ago, only about a month or so ago, a QLCS event which tracked across upstate New York and into southeastern New England. My name's Mitchell Gaines, as Christina mentioned, a forecaster at the Binghamton, New York office. Also co-authors as well, Lily Chapman, another forecaster at the Binghamton office, and Jared Klein, the SU at the National Weather Service in Binghamton. You can see below, these are from the Albany, New York forecast office event review of some pretty extensive tree damage around the Albany, New York area. Taking a look at the event review here from the Storm Prediction Center, the W's are for reports of damaging winds, either in the form of wind gusts that met severe criteria, 50 knots or over, and also for downed trees, power lines, and the actual damage caused by the winds as well. And there was one tornado there in upstate New York, west of Albany as well, but our focus is going to be pretty much solely on the straight line winds. This QLCS complex, of course, being in October, classified as a high shear, low CAPE event, tracking from central New York around the Syracuse area, Interstate 81 southeast into the Albany area throughout the afternoon hours, and into southeastern New England by the early evening hours. So this went through a pretty populated swath of area, especially from Albany eastward. Power outages were over 650,000 for the event, with around 250,000 power outages in the Albany area. So we're going to take a look at the Storm Prediction Center outlooks. Initially starting off as a fairly broad marginal area across northern New England, but gradually shifting southward and becoming more focused on the day of the event, in particular with even being upgraded to a slight risk across Massachusetts after the QLCS began to develop. Pulling up a graph here of the top wind gusts from the New York Mesonet. This is the maximum 24-hour wind gust. With this system, they were fairly strong synoptic winds statewide, but heading into, you can see that swath from up in the Tug Hill Plateau, southeastward, a little bit heading east of Utica, and down toward the Capital District of Albany, fairly decent cluster of 40 to 60 mile an hour wind gusts accompanying this line, squall line QLCS. This is also courtesy of the Albany, New York office, going to loop the radar a few times through. See here that it started as developing around the Syracuse area, continued to mature into the afternoon hours and early evening as it moved through Albany and into portions of southeastern New England. I'll show that one more time here. And this image from the late morning, early afternoon, all the way until the early evening hours. Also to point out here, there were quite a few forecaster challenges with this event, particularly over our forecast area. You can see I showed the Albany radar from the event review that the Albany office did, but you can see here that the video is blank for both the Binghamton, New York area and an adjacent radar up in the Tug Hill Plateau, TYX. So there was actually various challenges with the Doppler radars for this event in question. I'm going to break that down a little bit more as we move on in our presentation. So the meteorological environment. See, the first set of these graphs is primarily surface maps with the jet stream in the bottom right-hand corner. See, the first map was from the mid-morning hours. You can see that there was a triple point low pressure system across southeastern Canada, which eventually was followed by a cold frontal passage during the afternoon, and eventually that cold front moved into southeastern New England by the early evening, and a fairly robust jet coming into the picture as well, with a sharp trough across New York State, favorable position in the jet dynamics wise to where potential for strong and severe storms. But you see the same with the 500 millibar height in the upper left as well. You can see with the 700 millibar, that's in the lower left-hand corner, that there is at least a little bit of low-level moisture that's coming up into this trough axis and head of the front as well. Well, it's not tremendous moisture advection. There is some moisture advection that is occurring out ahead of the system. Also, you can see that there is a pretty deep upper level trough that is moving through across New England as well. And we're going to find out that all of these had a factor in producing this fairly widespread wind damage event. So to break this down a little bit soundings wise, we first take a look at the soundings from 12Z the morning of the 7th, several hours before the storms moved through the Albany area, and then several hours after the storms moved through our sounding site here for Albany, New York. You can see in the morning, not really a lot to write home about. Any instability, of course, is going to be your lowest in a typical situation at around the 12Z time frame when that balloon goes up in the morning. But you can see already from 1 kilometer all the way up to 6 kilometers, abundant amount of shear, looking at anywhere from about 60 knots, 0 to 6 kilometers shear by this point, which if you go toward later in the afternoon and the early evening, it increases even a bit more to around 65 knots of shear. 1 kilometer, 3 kilometer shears take off from around 20 to 40 knots all the way up to around 50 knots after the passage of the QLCS. What this research focused on with this event was the steepness in the low-level lapse rate. So we see that Cape environments overall are fairly low, only a couple hundred joules. That D-Cape actually stood out a little bit more at around 300 joules per kilogram. We looked at the low-level lapse rates in particular. You can see there toward the evening hours, the inverted V profile. That's fairly classic when you have steep low-level lapse rates. Well, also referencing a event review that the Norton office did as well, referencing the mid-level lapse rates for this event too. So you can see here, this is a loop of the HREF models and all their ensembles ranging NSSL, ARW, NNM, NAM-NEST. So quite a few of those. They picked up fairly well in the late morning hours on mid to late morning on an area of rain that moved through New York and into southeastern New England. and then more uncertainty and differences within these various cams developed with a broken line of convection throughout the afternoon and into the early evening. Also a bit interesting to see as well that some of them developed actually two distinct lines of convection, which, and you have that going on, they tend to compete with each other for the available energy and dynamics to become strong to severe. Again, this high shear, low cape event, going back in the literature some on these type of events, started off in 2008, going back and looking at some research there with a higher degree of false alarms with tornado detection. Conventional forecasting techniques by 2010 determined not to be as successful with only looking at the cape values alone as a poor discriminator for tornadoes. Now moving on to a little bit more of a research after 2010, this also references that because of the low top, which I'm going to go over that with the satellite data as well and extend that to the radar. At shallow convection and mesovortices, everything's at the lowest tilt. So radar, as it gets further out from the actual radar site, the beams go higher and higher, and sometimes some of this low top convection is actually underneath the radar beam. So case studies of this, ironically by the previous speaker, Mike Evans, were done in the 2003 to 2009 timeframe. And within these case studies, it was also hit that dry air intrusion fairly hard. And break that down to another HLSC climatology event in the southeastern United States from 2006 to 2011, this one done by Sherburne and Parker back in 2014, that the most skillful parameters in determining these HLSC events from being run-of-the-mill, a couple of trees down here and there, to being a fairly more widespread event, as we saw with this case back on October 7th, were the low-level lapse rate 0 to 3 kilometers and the mid-level lapse rates as well. So touching on forecaster challenges here a little bit, both the radar feeds at Binghamton and TYX were offline for the event. That radar issue, the radar issues compounded based on the facts in the literature mentioned. It's hard to pick up on that low top convection. So upstream reports from the Buffalo office were very helpful for our warning forecasters with this event, and use of other data sources such as satellite, where that radar data isn't there. You have to look to other avenues and other resources in order to be able to make effective warning decisions. So here I have some notes from the forecaster on the satellite data warning decision. So the forecaster primarily used visible infrared sandwich, RGB, and lightning data. Lightning data, particularly referencing my former Sue at the Mount Holly office, Al Cope. Oftentimes you can see when the storms are becoming severe, a fairly sharp uptick with lightning. So the forecaster was looking at the lightning data, visible IR sandwich imagery, RGB, and the RGB makes use of the 10.3 clean IR and visible bands. But even the satellite data, I'm going to go back there a little bit. Even the satellite data, though, had its limitations because the convection was shallower. So what the warning forecaster could see, he could see a narrow band of colder cloud tops developing west of Lake Ontario by 18Z, with the coldest cloud tops staying, of course, with the line along the north of the New York Thruway. But this gradually became more washed out as it continued moving off to the south and the east in that 19 to 21Z time frame. So which actually added a little bit of difficulty with the warning decision, as some of those key factors with the satellite data were also in and out too throughout the event. Our key discriminator here, the 0 to 3 kilometer lapse rates. So when the line develops by the early afternoon hours across upstate New York, it's fairly normal. And as you can see, there's a local min where that line moves through, and then the lowest lapse rates by the time the line gets into southeastern New England are getting fairly darn steep, despite a fairly minimum Cape event and high shear. Just looking at those on the surface, there may be more of a, from a forecaster perspective, more of a instability concern. But then when you factor in these low-level lapse rates as well, that's when that can help to overcompensate for the low amounts of Cape, and that's really a highlight here from this research study done. And put that in perspective as well, we took a look at a deeming here a null case from what was 3 days later. So I was on the mid shifts for both events on the 7th and the 10th of October. So of course the event on the 7th, we can see that the lapse rates were a favorable aid for severe weather. But here you can see that this case 3 days later, same time of year and everything, the dynamics are pretty much, I didn't break down every single graphic here in the interest of time, but see here that overall the low pressure system's further north, another fairly dynamical setup, but closer to the better dynamics in northern New England, the lapse rates never got anywhere close to as steep in the lowest levels compared to the event on the 7th. So if we take a look at the bottom right-hand corner image, you can see that only a handful of events compared to the dozens upon dozens of reports with the event on the 7th occurred across northern New England, across northern Vermont and New Hampshire, and a couple of clusters. So while we had similar dynamics, similar Cape profiles, the lapse rates did differ from one event to the next year, going over the course of only a few days apart. And you can see the Storm Prediction Center as well did collaborate with them on this, and we did recognize a fairly similar setup on the 10th to the 7th, which the one on the 7th was a ramp up to gauge the overall potential of the event, while on this one it was potentially more of a ramp down, kind of biting on some of those other factors, and the lapse rates perhaps heading a little bit underneath the radar, pardon the pun, on that one too. And breakdown here, a couple minutes left looking at the clock. So summary and future research dynamics were favorable in both events. The low-level lapse rate stood out for the 10-7 event. Also referencing that Norton event review as well, that the mid-level lapse rates also backing up the literature were fairly robust and stood out for that event on the 7th. So overall, this small case study sample between two events on the same week panned out to match up with the previous literature. These events are still highly challenging for forecasters. Again, any slight change in the time of the year, a couple hundred joules of Cape either way, changes in the lapse rates, change a few parameters here and there, and that can make the difference between these high-end cases such as the 7th and more of that lower-end null event on the 10th overall. So potentially could you develop more of these case studies to produce a more robust database, something worth looking into going forward. And a couple of references and acknowledgments too of the work shared throughout the presentation. And have a few acknowledgments too. Brian Tenninger, a lead meteorologist here at our office, helped with a few of the graphics on the presentation. Our radar operator for this event was Brian Greenblatt, a forecaster here at the Binghamton office. Also want to acknowledge some emails that were forwarded to me from the Albany University map discussion listserv. And also want to acknowledge the Albany and Norton event reviews for this event as reference material for this case study here. And also want to thank NROW, the NROW steering committee, for their time to allow me to present this case study to everyone. And with that, it looks like we have just enough time, maybe if there are questions out there that I can answer.
Thanks, Mitchell. That was a great review of a very remarkable event. Now, I don't see any questions in the chat box on my end. Brian, do you see any questions?
Let's see. Yes, Joe Villani has a comment. So here, Joe, I can unmute you, or you can unmute yourself. You should be able to.
Oh, thanks, Brian. Can you hear me?
Yes. Yep. Can you hear you, Joe?
Yes. Hi, Mitchell. Great presentation. Definitely an anomalous event for this time of year. Just wanted to make one comment. We did notice, taking a look for you forecasters here, comparing the October 7th to the 10th event, and that the dynamics were a little different, and that the main core of the upper trough was kind of coming right over us on the 7th, where it was really displaced more towards like northern New England on the 10th. I don't know if you had seen the similar thing. So we, even though, like you mentioned, the lapse rate difference too, but also I think the forcing was also quite different and much stronger on the 7th compared to the 10th.
Yes, the overall forcing was stronger on the 7th compared to the 10th, so that was a little bit of a factor as well. But I think everything, as you said, the trough axis coming in a little bit further across the Albany area was definitely one of the, even though you saw that the low-level lapse rates across southern tier New York did get fairly steep further north, where some of the better dynamical factors were, lapse rates really didn't quite get there. So it's more, not exactly the same area, but more of a look at northern New England compared to more down into the Albany, Binghamton, and southeastern New England. So more or less a time comparison there with those two, but yes, the regions were slightly different, and definitely the dynamics were a bit more impressive on the 7th, but still a fairly dynamic setup on the 10th too.
Okay, thank you. Sounds good.
Okay, thanks, Joe, for your question. Are there any other questions from the audience? I don't see any on my end. Brian, anything that you see?
No, I think we're all set for now.
Okay, great. Thanks, Mitchell. I do want to give a shout out to the New York Mesonet for the October 7th event. I was at the Albany office that day. I was one of the forecasters on shift, and the New York Mesonet was absolutely crucial in our assistance in really properly warning for this event. The observations we received from the stations upstream in the Mohawk Valley were instrumental in our warning operation. So I do want to give a big shout out to the New York Mesonet for just its very, very useful information as forecasters were trying to diagnose this event. So just want to make that note. But other than that, we are at the break for this session. We will come back at 3:40, and we will be on the Tropical Storm Isaias session with some really great talk. So be sure to come back at 3:40.
Okay, so we have 3:40 here. I'm going to have Christina come back, and we'll continue with session E.
Thanks, Brian. Hi, everyone. We are back for the Tropical Storm Isaias session. First up, we have a forecaster from the Albany, New York National Weather Service office, Brett Rathbun. He will give a discussion titled a recap of I just lost my screen. Sorry about that. A recap of Tropical Storm Isaias and its hydrological comparison to Irene and Floyd across the NWS Albany County warning area.
All right, thank you, Christina. Can you guys all hear me and see my screen okay?
Yep, you look great.
All right, perfect, thank you. Good afternoon, everybody. So again, my name is Brett Rathbun. I'm a meteorologist at the National Weather Service in Albany, New York. And I'm just going to be doing a quick recap of Tropical Storm Isaias across the Albany County warning area, and also do a little bit of a hydrological comparison as well to some other tropical storms that have impacted our area in the past, Irene and Floyd. All right, so just to do a quick overview, again, we'll just do a quick recap of Isaias. Then we'll do a little bit of a hydro comparison to Irene and Floyd, and then finish up with some final thoughts. All right, so quick recap. Again, this started out as a potential tropical cyclone 9 in order to get some watches and warnings out for parts of the Caribbean. It eventually became Tropical Storm Isaias on the 29th of July, 2020 across the Caribbean. It then turned northward and then tracked up the East Coast, making landfall across the Carolinas as a hurricane on the 3rd of August, and then it continued moving up the coast, moving across the interior Northeast as a tropical storm on August 4th. Basically, Isaias brought quite a bit of rainfall and some strong winds to the entire county warning area. So here's just a quick track summary of Isaias. Again, you can see it did form across the Caribbean, became a hurricane as it moved northward of Hispaniola across the Bahamas, and then took basically a northward and then northeastward turn up the East Coast, again making landfall right along the border of North and South Carolina as a hurricane, and then continued up across the interior Northeast. So here's a quick radar loop summary of Isaias. This runs from midnight to 8 p.m. on August 4th. The main key in this radar loop is that you can see that there was a northward advancement of rain ahead of the main center of circulation, with a generally light to occasionally moderate to heavy rainfall. Most of that was pretty much confined to the eastern part of New York. The worst of the rain and the wind then affected eastern New York during the mid-afternoon hours, pretty much right during the afternoon-evening rush hour. Most of western New England was generally affected just by one convective band of showers associated with the main center of circulation with some gusty winds. There was also an isolated tornado threat present in this region as well, but luckily we did not have any confirmed tornadoes. Here's just a review of the rainfall that our area received from Isaias. Again, pretty much nearly the entire forecast area picked up at least 1 inch of, I was just saying, much needed rainfall, and we'll get into the reasons why shortly. The heaviest rain pretty much fell in a 3 to 6 hour period, again, pretty much during the mid-afternoon hours, stretching from the eastern Catskills and Schoharie Valley through the Capital District in Albany and then into the Lake George, Saratoga region, where it's pretty common to see rainfall amounts of 2 to 5 inches. There were a few locally higher amounts as well. Down here in Ulster County, we did see a report of 7 inches in that location. But again, you can pretty much see that there was pretty much one big stripe of heavy rainfall pretty much right across the middle part of our area. So again, here are some of the rainfall totals that received at the climate sites that we have in Albany. We have Albany, Bennington, Vermont, Glens Falls, Poughkeepsie, and then Pittsfield, Massachusetts. Albany picked up 3.92 inches of rain from this event, and it was a daily record rainfall. Glens Falls also set a record rainfall as well, picking up 2.81. You can see kind of across western New England, Bennington and Pittsfield, generally about an inch, inch and a half. For Poughkeepsie was actually a 2-day rainfall. Some of the rain began just before midnight on the 3rd, before we got to August 4th. So about 1.19 inches of rain fell on August 4th. For Poughkeepsie, it was their second wettest day on record. for this day. Their current record is still 2 inches from 1969. And as you go into Albany, the previous record from Albany was 1.4 inches set in 1915. And Glens Falls just barely beat out their previous record of 2.41 inches, and that was set back in 2018. So as we said, that was a daily rainfall record at Albany, and that actually set a record to be the 4th wettest day on record for Albany. You can see here 3.92 inches. It just beat out, basically there's just 3 other events that beat that out, and 2 of them we will discuss later in the hydro comparison. The wettest day on record was from Tropical Storm Floyd, 1999, and the second wettest was from Irene in 2011. So going through some of the impacts of Isaias, we'll start off with the wind gusts. Basically, it was a pretty windy day across the region, especially as the main center of circulation moved through. Wind gusts basically peaked generally between 30 and 50 miles per hour across much of our area. The strongest winds again occurred during the afternoon hours, pretty much as the center moved through, and it was also at the same time as when the heaviest rainfall fell. There are numerous reports of downed trees and power lines that occurred as a result of this event. And actually some parts of the area were without power for days following the storm. This was especially across the Litchfield County, Connecticut, which looked like they did get hit the hardest out of our area. You can see we just barely missed out on some of the even stronger winds down across Upton's area, and I'm sure they will cover that in our next presentation. Going into the flooding from Isaias, basically flash flooding was mainly confined to urban areas around the Capital District. We did have flood advisories issued for the Capital District sometime between 3 and 3:30 in the afternoon. And as the heavy rain moved in, we upgraded to a flash flood warning just prior to 4 o'clock. We at least received about a dozen reports of flooded and closed roads, and also some vehicles stuck in floodwaters to the NWS. The table on the right shows the hourly rainfall that accumulated at the Albany airport. Pretty much started from 3 o'clock to 7 o'clock, and you can see in those 5 hours, 2.85 inches of rain fell at that time. Again, it was pretty much right during the afternoon rush hour. Remember, the total rainfall was 3.92 inches. So in this 5-hour period, that was about 3/4 of the entire rainfall from the day. And despite the heavy rainfall, believe it or not, there was no river flooding across our area, and rivers didn't even reach action stage. So the main purpose of this study is we'll just do a brief synoptic and mesoscale analysis. And then, as I said, we'll get into some hydrology. So looking here, 250 millibars. This animation basically starts 0Z on August 1st through 12Z on August 5th. So the main highlight here was basically a building upper level trough from the Great Lakes to the Gulf Coast, as there was a strengthening southerly upper level jet across the Northeast as Isaias was tracking up the coast. Isaias was likely to hold some of its intensity being in the right entrance region of the upper level jet, where upper level divergence was present. This interaction with the jet would basically gradually begin its slow transition into an extratropical cyclone, which was achieved right as it reached the US-Canada border. Moving down to 500 millibars now, pretty much kind of focusing this as the main steering flow for Isaias. And you can see that there's Bermuda High strengthening and stretching across the Western Atlantic, with also an upper level trough stretching from the Great Lakes down to the Gulf Coast. And basically between these two, Isaias only had one way to track, which is in between these two features, which basically took it right up the East Coast. And down to the surface, basically the Isaias was steered northward up the East Coast, again on the outer periphery of the Bermuda High, and also east of a pair of low pressure systems and fronts that were located to the west. Isaias eventually emerged with a non-tropical low, again as it reached southern Quebec early on August 5th. So during our forecast discussions, we were actually highlighting that there were some similarities of Isaias to what previous C-STAR research announces as a predecessor rainfall event. So what is a predecessor rainfall event? Well, basically it is a mesoscale region of heavy rainfall found poleward of an advancing or recurving tropical cyclone. Usually these regions are formed formed in the equatorward jet entrance region of a 200 millibar upper level jet, and also east of a 700 millibar trough. These can lead to significant inland flooding before or even after the main precip shield of the tropical cyclone moves through. Some other highlights of a predecessor rainfall event. They usually occur kind of around 1,000 kilometers poleward of the recurring tropical cyclone. They do occur most commonly in August and September, and again, Isaias occurred in August. They usually occur approximately 36 hours or so to the arrival of the main rain shield. This one was more or less, kind of around 6 to 10 hours. So you can say it's close, but it may not exactly be meeting the exact criteria of a predecessor rainfall event. But again, it had quite a few similarities. We'll just take a look at the soundings that we had in Albany for August 4th. So this one is from 12Z. Pretty much the main features to highlight here was pretty much a moist column all the way up to 200 millibars. And unfortunately, we had limiting angle issues, so we lost our signal above 200, so we couldn't get any farther up than that. We did have skinny cape and also some higher PWatts. This was around 1.64 inches at this time, but it was going to continue to increase. And again, note that PWatts were going to continue increasing closer to 2 inches, in some cases even above 2 inches, by the afternoon as the main precip shield moved through. Freezing level is right around 12,000 feet, so this would basically be a warm rain process. But basically all these ingredients favor what would be a potential flash flood situation, which we were, again, concerned about. As we get into 0Z on the 5th, so Isaias had already moved to our north and precip had begun to end across our area. But again, the low levels remained quite moist. PWatts began to drop down under 1.5 inches. And you can see that the drier air gradually built in into the mid-levels. Looking quickly at 700 frontogenesis, on the left is starting at 18Z on August 4th, to the right 0Z on August 5th. So basically this is covering the afternoon hours. This is taken from the 0Z run of the NAM on August 4th. So you can really note in this layer two distinct regions of frontogenesis. The first one on the western edge, which tracked up across the eastern Catskills through the Lake George Saratoga region toward Burlington, Vermont. And you can note it was actually strengthening during the day as well. And this likely resulted in the heaviest rainfall totals being located in those areas. The other region was on the eastern side, which led to pretty much the main convective band of showers across eastern New England. And not added to this presentation, but there was some high shear and also helicity values, especially across western New England, and that led to the isolated tornado threat in this region and the eventual issuance of the tornado watch. If we go down to 850 millibars, again, it's pretty similar to the previous slide, where you can see the area of strong frontogenesis associated with a band of heavy rain along and just to the west of the storm track, which went through the hardest hit areas. And then the convective frontogenesis band, actually east of the center, wasn't present in this level. So this was more of that was more of a 700 millibar frontogenetic forcing. All right, so just to do a quick recap of the synoptic and mesoscale summary. Again, Isaias tracked along the western periphery of the Bermuda High in advance of an approaching upper level trough, which allowed it to go up the east coast. This storm did have some similarities of a predecessor rainfall event per previous research. This was definitely a potential for flash flooding, given the ideal ingredients for a flash flood event: skinny cape, moist column, and a warm rain process. And again, the frontogenesis was a pretty good indicator of where the heaviest rainfall occurred. All right, so now we're just going to do our hydro summary for Irene and Floyd. So to the left is the Irene track, to the right is Floyd. You can see they're pretty similar tracks to Isaias, some differences, and also there were some differences in intensities. Irene was actually a widespread flood and river flood producer, and Floyd, despite it actually being the wettest system and also setting the daily record rainfall for Albany, there was only flash flooding and no river flooding with Floyd. So here is the US drought monitor maps. These are again in advance of Isaias on the left and Irene on the right. Unfortunately, we couldn't get an archive image for Floyd. So you can really see on the left side for Isaias, there was drought area going on across our area. Pretty much all of the Albany area was either abnormally dry or in a moderate drought. For Irene, you can see nearly the entire area was droughtless outside of northern Herkimer County. The archive images, again, like I said, don't go back to Floyd 1999. And since these don't show abnormally wet conditions, we will turn to the Palmer Drought Severity Index, which is here on this slide. So basically what the Palmer Drought Severity Index is, it uses readily available temperature and precipitation data to estimate relative dryness. Dries are in the yellows and reds, and wet are in the greens, and this is a unitless value. So each of these maps were captured the month before the tropical storm's arrival, so it would not skew the data. You can see here for Isaias for 2020, it was generally a neutral index for most of the area, but there was a moderate drought category you can see across northwestern Connecticut. Now, if you go to Irene, it was pretty much a completely different story. Almost the entire area was in a neutral to even moderately or very moist conditions, according to arrival of Irene. And for Floyd, you can see there was widespread dry conditions across pretty much the entire Northeast, almost the entire Eastern United States. That was either in a moderate to severe drought based on this index. So here are the yearly precipitation trends for Albany, again, pretty much starting from January 1st through the end of the event on the right. And we basically have 5 lines on this map. So the green one is the 2020 accumulation. The brown line is the normal rainfall. The blue line is the highest or the wettest year on record, which, believe it or not, was actually for Irene in 2011. The driest year on record in red from 1964. And just to add Floyd in here, that is in pink. So if you zoom in, because all 3 storms occurred pretty much in very similar times of the year. You can see, again, remember Isaias is in the green, Floyd in the pink, Irene in the blue. You can see here for Albany, you can clearly see the spike in the precipitation graphs after these storms went through. So to clarify it in table mode, you can see after Isaias, rainfall before the storm arrived, Albany was about 5 to 5.5 inches below normal for rainfall. After the rainfall from Isaias went through, the departure was still below normal, but only about 1.5 inches. Irene was a completely different story, as we said. It was a very wet year. We were around 7.5 inches before Irene arrived. After the rainfall was over, our yearly departure exceeded 12 inches. And for Floyd, we did have a below normal precipitation departure before it arrived. After the rainfall moved through, we did end up having a slightly above normal precipitation departure, but only about 1.85 inches, so not too extreme. Now, as we move to Glens Falls, we'll click in here. Again, fairly similar precipitation departures, again, prior to Isaias and Floyd below normal. And actually, after they went through, the departures remained below normal. And again, while not as extreme as Albany, Glens Falls still had above normal precip prior to Irene, and then basically had a nearly 7-inch departure positive after Irene moved through. And finally, for Poughkeepsie, there was a very large precipitation departure before Isaias, almost 10 inches below normal. And this is actually close to the driest year on record from 1964, as you see by the lines. They only received 1.37 inches of rain, so really that did nothing for this area to try to help the drought conditions. Floyd, again, following the rainfall, still had a below normal average precipitation year, but it was very close to normal at that point. And Poughkeepsie received over 7 inches from Irene, and that brought the precip departure to 10 inches. So finally, we'll just do a quick recap of the percent of normal precip. This is basically kind of covering a year in advance of the storm. So on the left is the percent of normal precipitation for the past 12 months, or the 12 months before the storm. And then to the right is 6 months, and you can see for both of these maps, generally near to below normal precipitation in advance. And then on this slide, on the left is the 3-month beforehand. And on the left is the precipitation for the month when the storm impacted our area. You can really see that there was just a continuous dryness prior to Isaias across this region. Stream flows and river levels were very low, and that probably aided, even with all the heavier rainfall, that rivers were not able to overexceed their banks. And for Irene, pretty much the exact opposite. You can see kind of in the 12-month and 6-month, generally near to above normal precipitation before the arrival of Irene. And as we get into the 3-month and after Irene moved through, still generally near to slightly above normal precipitation. But then August was a very wet month. Most of the area had almost double their normal rainfall. So to summarize, the hydro section, again, Isaias and Floyd, which are non-river flooded systems, basically entered a region of below normal precipitation and drought conditions, and also pretty much lower stream flows and river levels. Despite the heavy rainfall following the storms, it just wasn't enough to break the precipitation deficit and cause them to flood. And again, the only impacts were from flash flooding. Irene, which was a river flood system, again entered a region of above normal precipitation and anomalously wet conditions, and their rainfall was enough to flood many rivers and lead to widespread flooding. So really just some final thoughts here. Again, the tracks of Isaias, Irene, and Floyd, very similar. Below normal rainfall in advance of Floyd and Isaias probably failed to trigger river flooding issues, whereas above normal rainfall in advance of Irene did. And again, wind was pretty much the main impact of Isaias, with numerous reports of downed trees and power outages, especially as you get across northwest Connecticut. And it was probably associated with the rainfall in advance of Isaias, pretty much softening the soils and allowing trees to fall apart a little bit easier. That's all I have. Hopefully I left time for maybe a question or two. If you have any questions, you can feel free to email me, and thank you very much.
Thanks, Brett. That was a great review. I think we do have to move on, I think, to the next presenter, but certainly feel free to email Brett if you have any questions. We're going to continue with the Isaias theme. Next up will be a forecaster from the New York City National Weather Service office. Devell Johnson will give us a discussion titled, "Not Just a Tropical Storm, Hurricane Isaias and Its Impacts to the Greater New York City Metropolitan Area."
All right, can everybody hear me okay? See my slides okay?
Yeah, you look great.
All right, awesome. So good afternoon, everyone. My name is Devell Johnson, and I'm here on behalf of the New York Tropical Team, just to talk about Hurricane Isaias and its effect on the greater New York City area and some of the lessons learned from the system. All right, so we'll break this up into 3 different sections: the before, the during, and the impacts. And then the lessons learned after Isaias came through the area just on August 4th, 2020, earlier this year. So let's start off by going through some of our office pre-Isaias messaging and some of the pre-event activities that began on July 30th and lasting all the way through the actual event. So kind of mentioned earlier in the previous presentation, Isaias started as a potential tropical cyclone Tuesday, July 29th, just east of Lesser Antilles. And for those of you who may not know, the potential tropical cyclone is the Hurricane Center's wording for describing a disturbance with meteorological is not yet a tropical cyclone, but which poses a threat to the threat of bringing tropical storm winds and hurricane conditions to the land area within the next 48 hours. So doing so allowed the Hurricane Center to issue tropical storm warnings for the Caribbean islands. And it was right around about 11 a.m. on Thursday the 30th, so a few days later, that Isaias strengthened to a tropical storm, and the forecast was now taking it just east of Florida and then right along the East Coast. And with that, that put us in the cone of uncertainty. So that really made us want to ramp up our messaging for the event in support of our partners. So our support messaging started first with social media on Thursday the 30th. You can see the tweet here from our office, and noting that at the same time we actually had severe weather that night. And it was then by the next day we had started doing our full-on briefing packages for our partners on possible forecast hazards and potential impacts ramping up to the event. We even had formal over-the-phone briefings, webinar briefings with our core partners, and we really wanted to continue to hammer home this message that the storm is on the way, because this happened over the weekend and it's going to be happening in early the next week. We even had a slight risk of severe weather on Saturday to deal with. So all this, that wasn't related exactly to Isaias, but it highlights the importance of target messaging for Isaias versus our current hazards that we had ongoing. So like I said, we began amplifying that messaging for Isaias during the weekend. We had tropical storm watches that were issued for much of the area. On Sunday the 2nd, upgraded to tropical storm warnings by Monday throughout the entire area. We also had coastal flood watches for the area. We had flash flood watches across the interior. And at this point, we had pretty good indications that the heaviest rainfall would be across the western portion of our areas, which is where we had our flash flood watches. We also had coastal flood hazards for the expected surge that was possible if the surge had coincided with high tide. So I wanted to show you what our briefing schedule looked like. We had dozens of phone call and video call, conference calls, webinars, consultations with our hundreds of emergency managers, public safety officials, utilities, hospitals, as well as phone calls with media and the public. This all started, like I said, Thursday and then ramping up right through Tuesday of the event, and even continued for the days after as we supported the recovery efforts. I just want to give a huge thank you to our warning coordination meteorologist, Nelson Bass, and our Sue Dave, and our MIC Ross, who handled the majority of these calls. I also want to show you what our operations schedule looked like. We had to coordinate with the Hurricane Center, the Weather Prediction Center, Eastern Region, and as well as the surrounding offices. We had to do the supplementary upper air balloon launches, continuous DSS through phone briefings and conference calls, consultations, all sorts of things. And this all just to emphasize our near-term forecasts and our warnings operations that were ongoing at the time. And remember, this tremendous workload was occurring during our COVID protocols. So really, to even achieve our all-hands approach, we had to request that our ETs set up additional workstations in our office cubicles to maximize social distancing. So the workload was challenging, but as you all know, we have passionate forecasters dedicated to the National Weather Service mission. So I'm going to shift and briefly talk about the forecast leading up to the event and the day of the event. So showing here, we have the GFS Ensemble member tracks at 0Z on July 30th. So this is 5 days out. We had a pretty well cluster of the members depicting a track upwards along the East Coast. And at this time, we were pretty confident, because even if Isaias were to take a turn going a little bit more out to sea, New York City and Long Island would still see coastal effects. So we were really planning on seeing some impacts at that time. The intensity guidance was pretty much consistently showing a tropical storm strength. With some of the hurricane models, you see the HMON and the HWRF showing a low in Category 1. The official intensity forecast was on the lower side of the guidance, but still solidly within the tropical storm range. Again, this kind of goes to show the difficulty in tropical cyclone intensity forecasting, which is still an area of research. So, but by Sunday morning, so this is August 2nd, 2 days before landfall, we're seeing the tropical storm wind speed probabilities showing about a 60% chance of experiencing tropical storm force winds. And so by this time, we were well in the path of the storm, and we were well aware of what was going on, of course. So how did the Hurricane Center do? Isaias tracked right through the Caribbean islands following this 8-day chart and headed up the East Coast. The blue shows the tropical storm speeds, tropical storm force winds. The yellow is the higher end tropical storm force winds, and the red shows the hurricane force winds. So this does show that that Isaias obtained hurricane force strength at least twice during its life cycle, once over the Bahamas, and then again right before making landfall along the coast of North Carolina. So just a quick view of the GOES satellite imagery showing Isaias shifting through the northeast. You can give a note to that clearing area right on the right front quadrant of the storm. This is where we had a lot of our convection and even a tornado that was generated. It's pretty much a classic feature of transitioning tropical systems. And here's the radar mosaic. Impacts began early Tuesday morning of the August 4th. The area, we can see that we had quite a few short fuse warnings that were issued, several special marine warnings, the flash flood warnings that were issued as well, even the tornado warnings that you'll see at the end of the loop. And we were watching this heavily throughout the entire day, just to be sure that we're monitoring, especially for that dry slot in particular. That's a typical area where you'll see tornadoes form, and we'll talk more about that later. And I want to show this one because it's some of my favorite graphs here. This depicting the hurricane pressure curves. These graphs show the data from the New York Harbor buoy, which was caught right in the passage of Isaias. We had this 15 millibar pressure drop over the next over 10 hours. Wave heights recorded 16 feet, and then peak wind speeds of 70 miles per hour. And it showed that Isaias was a quick storm, but it packed quite a punch for the area. And I'll talk more about the impacts in just a little bit. But before I do that, I wanted to mention our big near miss that we had. This graph shows data from Jamaica Bay, which is right along the south side of Long Island. And if you see here, I'm not sure if my mouse shows up, but we had about 4 to 5 feet of surge occur at low tide. So if this surge had occurred at high tide, we would have been seeing the surge that would be comparable. It would be not only major storm surge for Jamaica Bay, but comparable surge as to Tropical Storm Irene and Hurricane Sandy. So this is just goes to show why the National Weather Service focuses on messaging the reasonable worst case scenario, because had this storm been maybe 6 hours earlier, 6 hours later, we would have had this storm surge on top of high tide, which would have been quite devastating for the area. So the final segment, I'm going to talk about the impacts that we had from Hurricane Isaias. And here first, we're looking at the MRMS rainfall estimates, showing that most of our rainfall occurred over eastern Pennsylvania, northeast New Jersey, portions of the lower Hudson Valley, and really particularly over Long Island, we had less than an inch fall. And again, this was because of that dry slot. And it's a reminder that every tropical storm is different. And at the time, Isaias was moving 25 to 30 miles an hour. And that doesn't leave a lot of time for rainfall accumulation. So that was one of the bigger factors in that. However, because of its speed and that dry slot, we had an increased threat for winds and tornadoes. So speaking about our winds, we had widespread prolonged tropical storm force winds that were recorded throughout the forecast area, particularly in Nassau and Suffolk County, where we had hurricane force gusts. And again, we likely had some of these areas that had high wind speeds, even inland. They just weren't recorded. So and in this image, this shows all of our damage reports that we had. The vast majority of this damage was, again, downed trees, uprooted trees, fallen power lines, and this kind of goes to show that most of our high wind events are really northwest, northeast winds from mid-latitude cyclones or nor'easters. And so the trees around here can be hardened to that prevailing wind stress, those prevailing wind stress conditions. But when we have these strong south winds, as far as tropical systems are concerned, it can be quite impactful for the Northeast. And this is likely partially due to the trees not being hardened or building resistance to south winds. And this was especially true for the summer when the trees have full canopies, and this increases their surface area exposed to wind stress. But regardless of all that, really, whenever you have 70 to 75 mile-an-hour wind gusts, you're going to have considerable tree damage, no matter what direction the winds are blowing from. But all things being considered, it's likely that this increased damage was from the south winds. I just want to show some images of the damages. Like I said, those trees. These trees didn't appear to have deep root systems, which is common for urbanized environments. We had trees that were down all over the city, all over Long Island, but still, these fallen trees can fall on the cars, they can fall onto homes, fall on the power lines and stuff, and still cause considerable damage. We even had 2 recorded fatalities related to fallen trees. So I wanted to talk about the power outages as well, because we had a vast amount of power outages from Isaias, totaling around 2.5 million people who are without power at some point during the storm's life cycle. For our area, only Hurricane Sandy caused more outages than Isaias, and even after the storm was over, we had over 300,000 customers that were out of power. And some customers even going without power for over the week. And then, of course, you have to mention this, but many issues can be noted whenever you have power outages. Improper generator use, carbon monoxide poisoning, the summer heat coming up for people having lack of air conditioning, store closures, all sorts of things that are happening like these. And these factors are at play when somebody's considering whether or not they want to ride out the storm or choose to evacuate. So things like that are very important. And so I wanted to, those are some of the widespread impacts. I wanted to briefly look at one of our specific impacts, was the tornado that happened in Westport, Connecticut. So though Isaias produced quite a few rotating storms throughout its landfall, only one for our area was confirmed of the 3 tornado warnings that were issued. And on this radar loop, you see the storm relative velocities on the right, and you can see that circulation, those inbounds and outbounds that occurred. And then let's see here in the next slide, I have the MRMS rotation tracks showing how that storm cell formed over the sound and tracked inland to produce that tornado. So overall, the tornado was likely very short-lived, on the ground for about a minute. However, in that time, it caused significant damage. We rated it an EF1 based on the loss of roof to the home, the branches and broken tree branches on the upper canopy there. The wind speeds 95 to 101 miles an hour, and only a path length of about 50 yards. So even though it was, like I said, it was short-lived, it caused some significant damage to this 2-story beach home. And of course, as if most of you know, the social media is a big help. It's an amazing tool. We actually had this tornado was spotted and filmed coming on shore by a private sector meteorologist, and it proved quite useful when it came to confirming the tornado later on. I would love to play the video for you, but wasn't able to quite get it to work. But if you follow that, you see Scott Pecorello. You can follow him on Twitter or find him, and you're able to kind of view that video. So we learned a lot from Isaias. But I wanted to hone in on 3 key points. The first, we really relearned how to deal with multiple hazards prior to a tropical system. We had those severe storms and the slight risk ahead of Isaias, and then messaging these multiple hazards can be difficult. But thanks to our early start and our relationship with our partners, we were able to message the threat appropriately, and this really helped get that message out there early. And then we of course increased our staffing for the briefings and the tropical products. Again, this is important because you don't want to burn out your meteorologists with these multi-day long fused events. And it's also crucial to share the workload so that no one's overwhelmed. We really want to make sure that our forecasters are working at their peak. And then finally, Isaias showed us how the damage that can be done from a high-end tropical storm. It's been a while, about 8 years since Sandy, 9 years since Irene. So our hope now going forward is to use Isaias as a recent benchmark for future training and tabletop exercises with our emergency managers partners and our surrounding area partners. So we can really put our best foot forward when it comes to our tropical weather. So with that, I conclude my presentation, and I just thank you so much for having me. Thank you to the committee for having us. And feel free to contact me or any other members of the tropical team if you have any more questions or need more information. And thank you all again. And with that, I open the floor for questions if there's time.
Thanks, Devel. That was a great presentation on Isaias. And I don't see any questions. Brian, do you see any on your end?
No, none come in, but if anybody has anything quick to say, you can raise the hand or send the message in.
Okay, I guess we'll move on to our next presenter, but certainly feel free to email Devel if you have any questions following his presentation. Okay, next up is our final presentation for the day. This is given by Nicholas Leonardo from the School of Marine and Atmospheric Sciences at Stony Brook University. The title of his talk is Sources of Large Track Errors in Ensemble Forecasts of Hurricane Isaias 2020 as compared to past tropical cyclones.
Can you all hear me?
Yes.
Okay, and you can see my screen now?
Yes.
Excellent. All right. Can I shrink this? Is this? How do I get rid of this?
You look fine. Everything looks good on our end.
Okay, sure. Excellent. All right, so sorry. Anyway, yeah, my name is Nicholas Leonardo, and I am a postdoc student of Professor Brian Cully up at Stony Brook. And I'll be presenting more updates on my previous PhD work, looking at large track error forecasts for tropical cyclones, or TCs, and seeing how Hurricane Isaias of this year compared to these past events that I've analyzed. So, oh, there we go. So despite overall improvements in said forecasts of hurricane and tropical cyclone tracks, you can still have these occasional forecast busts with track errors much larger than 300 kilometers. Now, errors in this magnitude in the along track direction can be problematic in that they can greatly impact the timing of landfall, while those in the cross track direction can affect the location. So the overall question I'm trying to answer is, are there any commonalities to these forecast busts? So previously I've shown at the last few talks here at NROW are that there are some commonalities I found in the GEFS and ECMWF, the largest along track and cross track errors from these ensembles. To summarize in these diagrams, the largest negative along track errors I found correspond to TCs interacting with the mid-latitude 300 millibar troughs, that the model is underpredicting the TC's divergent outflow, and the subsequent amplification of the steering trough and its PV gradient. And more recently, I found that similar mechanisms can explain large right-of-track cases at lower latitudes, and that the model is instead over-predicting the rainfall and the upper-level divergence extending north of the TC, corresponding to excessive mass removal and hence mid to low-level height falls penetrating the ridge, and thus causing the ridge to break and allowing the TC to drift further to the north during the first 24 hours of the forecast. So then the question is, can we relate some of the errors in TC tracks this current season to these historical biases? That is, are there along and cross-track biases systematically throughout the track forecasts of different stages of, say, Hurricane Isaias and its life cycle? And if so, how do they compare with other past events? And what factors might have contributed to the track errors of this case? And does the ensemble track variability show consistency with synoptic patterns similar to those identified for previous cases? So just as a summary, which has already been shown, again, Hurricane Isaias, it reached tropical storm strength on the 29th of July and made landfall around, on August 4th. Around the time, I would say it started undergoing, or around the onset of extratropical transition as it crossed inland. So what I have here now is the 72-hour and 120-hour cross-track errors of the GEFs in red and the ECMWF in blue as a function of initialization date, where you can see, despite this sort of diurnal oscillation, that by and large the GEFs at hour 120 was more than 100 kilometers too far right of track. And then meanwhile, in the along track direction, it's I mean, I won't have time to go over this the spike that you see here for this one forecast on the initialized on the 30th, but you can see that overall there's this trend in which after the 30th of July that the ECMWF starts having negative or slow biases in the along track direction, followed shortly after by the 72-hour forecasts of later cycles following this trend as well. Hence, I'll be breaking down this talk into two parts. First, focusing on the cross-track errors for earlier cycles, in particular this cycle on 0Z, the 28th of July, in which the GEFs developed a pretty significant right-of-track bias, I would say, compared to climatology, reaching around 200 kilometers by around hour 48 or so. And unfortunately, the ECMWF data was not available for these earlier cycles, at least the tracker data. But at least when looking at this relative to the GEF's climatology, as I said, when you look at it compared to the 2008 through 2019 distribution of day 3 through 5 cross-track errors of non-transitioning events, that 200 kilometers falls right near the upper quartile of the distribution. And so I'll be just focusing on the GEFs from here on, at least for this part, and looking at this forecast more carefully. I ended up looking at the ensemble members and breaking them down into two subsets of 4. These being called leftmost and rightmost, based on their 120-hour cross-track errors, and that you can see that these rightmost members in red separate from all of the leftmost members. That is, they're all more right of track than any of the leftmost members by hour 60. And in this regard, there also seems to be some correlation with the TC intensity with the subsequent cross-track displacement. In that an hour 48, you see that the rightmost members are all stronger than any of the leftmost members. And more evidence is that when you look at the integrated kinetic energy, the rightmost members have more energy than any of the leftmost at hour 48. So that's just to say that the rightmost members have broader, stronger wind fields, which are consistent perhaps with a larger beta drift, or perhaps feedbacks from the outer core of the TC interacting with the large-scale steering environment, as I alluded to earlier. So looking at the synoptic field of this forecast, what I often do is I look at standardized differences, in this case of the 4 rightmost minus the 4 leftmost GEFs member fields. dividing this difference by the full ensemble standard deviation such that these are all unitless. So just as an example, I show this figure in which I composited various other right of track cases throughout the years, in which I show the composited standardized differences in 700 millibar heights as shaded, and the deep layer mean steering difference vectors. This calculated after removing the TC wind from the wind field. So this is just showing, much like in the diagram I showed before, that more often than not, between hour 12 and 36, the rightmost members of these cases tend to have lower heights to the north of the TC and along the southwest extent of the steering ridge. And consistent with that, you have in the steering difference vectors this cyclonic circulation that implies that the rightmost members are being steered more to the north and east over time. And so how does Isaias compare to these composites? Well, for that forecast, looking at the standardized differences in 700 millibar heights, that at hour 12, you do see some hints of negative height differences in which the rightmost members have lower heights, and that these differences grow as you go forward in time to hour 24, reaching statistical significance as indicated by the green crosses. And this is consistent then with the environmental steering differences, if you look closely, forming this cyclonic curvature that's consistent with this portion of the ridge eroding and the steering flow taking the TC, or at least in the rightmost members, further to the north and east over time. So, as I said before, I argue that this is being caused, at least in part, by feedbacks from the outer core convection north of the TC. So what I have here now are standardized differences in the precipitation rate, which, while a little noisy at hour 12, they do indicate that you have this positive region, which persists as you go forward in time to the north of the TC, indicating that over this region, the rightmost members have more rainfall. And just another way of looking at this is if you look at the precipitation rates of the leftmost and rightmost members separately, as well as, compared against I-merge analysis estimates, as well as the 300 to 200 millibar divergence as contoured and compared against the CFSR, what you'll see is at hour 24 of this forecast that the rightmost members already have some hint of this region of having more rainfall and upper level divergence over this region more than 300 kilometers north and east of the TC than either the leftmost members or even the analysis estimates. And this becomes even more apparent as you go forward to hour 36 of this forecast. The problem is, though, what's causing this difference in the outer core convection? Now, for other cases I looked at, this can be tied to the near initial or initial moisture field, in which generally the rightmost members tend to have more low-level moisture to work with. Unfortunately, for this case, it's not so clear that, yes, the rightmost members, when looking at these standardized differences at hour 0, the rightmost members have 0.5 to 0.8 standard deviations more moisture. However, the differences are not statistically significant at the 95% confidence level, not even at hour 24. So thus, I've been looking more recently into some other factors or combinations of factors that might be contributing to this difference we're seeing in the convection of this case. So then moving on to my analysis of along track errors for later cycles, here I show for the 0Z August 1st cycle that the GEFs in ECMWF both had 96-hour along track errors of minus 640 and minus 730 kilometers respectively, that they were both slow biased. Now, for the interest of time, as well as to relate the results I'll show here to a paper that I published with my advisor earlier this year, I'll just be focusing on the ECMWF, which in that regard, you could see that this case is actually, well, it falls within the lower quartile of the distribution of prior along track errors between 2008 and 2019. So it's a sizable slow biased case. And there we go. And so again, focusing on this ensemble, once again, I break it down into two subsets of 10 members, the 10 slowest and 10 fastest, as defined by their along track errors at hour 96. And so that you can see here that the slowest members separate from all of the fastest members, that they have more negative along track errors by hour 72. But this time, there doesn't seem to be as much of a relationship between the TC intensity and the subsequent along track displacement, as the two subsets are constantly overlapping throughout the forecast, at least not directly. So then, instead, I look at standardized differences between the 10 slowest and 10 fastest ensemble members. My thing froze, sorry. Between the 10 slowest and 10 fastest ensemble members, in which case here I show as an example, a composite of various other slow bias cases throughout the years of composited differences in 300 to 200 millibar PV advection, as shaded, and the irrotational winds, as given by the vectors. So this is showing that between hour 36 and 60, much like I showed in one of the diagrams earlier, that the slowest members tend to have weaker irrotational winds or weaker divergent outflow, implied by these vectors converging. And they this corresponds then to the PV advection being induced by the irrotational wind being less negative or more positive along this trough ridge interface. Well, as you can see through this PV gradient associated with the steering trough. So then how does Isaias compare? Well, for this forecast, it's interesting to note that even at hour 0, when looking at the differences in the 300 millibar heights, you already see that up in Canada, along this incipient shortwave, that the slowest members already have higher heights over this region, as well as lower heights over the Gulf, and then at hour 24, along this developing ridge. So there's already a difference between the slowest and fastest members in the amplitude of this trough. However, it's around hour 36 that you also start to notice that something is happening when you look at the PV advection by the irrotational wind, that there are differences in which how the TC divergent outflow is interacting with this PV anomaly associated with this little shortwave that's just right off the Carolina coast, that afterwards moves on, and at which point you start to see that there are differences in which the divergent outflow from the slowest members is weaker. And thus you have less negative or more positive PV advection modulating this PV gradient associated with the steering trough. So this difference in the irrotational wind I can at least explain, in that it corresponds to differences in the precipitation field yet again. So what I show here are standardized differences in the precipitation rate at the top, in which you see at hour 12, you already have that the slowest members have less rainfall than the fastest members, and that these differences just they persist throughout the forecast, and that these are consistent with the slowest members having weaker 850 millibar moisture fluxes to the north and east of the TC, even at hour 0, and that these follow the TC as it begins to wrap up. And basically, it begins to, or shortly before the onset of extratropical transition, and thus affecting the distribution of convection. So, in conclusion, the earlier stages of Isaias had slight right of track errors that may have had similar causes to past cases. That while this TC was initially not very well defined for a lot of these forecasts, or at least compared to some other cases I looked at, the GEFS has a right of track deflection likely driven by a combination of beta drift and steering flow errors south of the subtropical ridge. And that for the latter, the 700 millibar heights along the ridge and near Isaias fall more during the first 48 hours due to greater divergence aloft associated with outer core TC convection, which may have corresponded to differences in the initial moisture field near the TC. And so for these deep tropical TCs, one should closely monitor the evolution of convection to the north of the storm and the ridge height responses during the first 24 through 48 hours. Now, for the later stages of Isaias, there were very clear slow biases that also somewhat resembled past cases, in that there was an upstream 300 millibar trough ridge couplet which failed to accelerate the storm. However, while there were differences attached to the couplet even at hour 0, these differences were exacerbated, at least in some way, by an underprediction of Isaias's divergent outflow, which further impacted the couplet's amplification by around hour 48 to 72. So thus one should monitor these extratropical interactions, applying ensemble sensitivity to the TC track with upper level PV advection and precipitation fields to see if there's a consistent relationship. And then you can perform a bias correction upon new observations becoming available later on to confirm whether if the fastest members of these forecasts should be given more weight by virtue of having a more correct representation of the precipitation field and the subsequent feedbacks with the steering environment. So with that, I will take any questions. Thank you.
Thanks, Nicholas, for the great presentation.
80.
I don't see any questions in the chat box. Brian, do you see any?
No questions have come in yet. No,
no questions?
No, it's not.
Okay.
All right. Well, thanks, Nicholas, and thank you, Christina, for being the session chair for this afternoon sessions. And that will bring us to the conclusion of day one here of NROW. Definitely thank all the presenters that we've had today. It's been really great. I know it's definitely a little different than being in person. We haven't been able to have those conversations at the breaks and lunches like we always do. But I'm glad we were at least able to have some back and forth and some questions. And I think we're going to have a really good day tomorrow. Tomorrow morning we start at 8:55 with some remarks and some logistics, and then we'll be into some of the cool season events for tomorrow, so starting at 9 a.m. The other thing I just want to mention, I don't know if I mentioned this at the beginning, but we are having this recorded. So if there's any talks you want to watch again or you missed some, we're going to have the recording available after the conference is done. So thanks everybody for a great day one, and we'll see you tomorrow morning for the day two of NROW. And we also have a keynote tomorrow afternoon as well. That should be really good. So look forward to that. And again, if anybody had any technical issues or questions, please send us an email or send us a chat, and we'll definitely try to get it fixed. Otherwise, see you tomorrow. Thank you.